Okay, let's try to take our seats. Okay, Everett, you ready? All right, yeah, so welcome everyone to the 2026, our 31st annual CSM workshop, and to open this exciting week, Everett Joseph, the director of NCAR, is going to say a few words of welcome.
'31st annual, wow. This morning I was trying to figure out what number it was. So good morning, everyone, and welcome. It's really a pleasure to welcome you to this CSM workshop. And to those of you that have traveled here to Colorado, welcome to the pleasant weather. I came back last night, actually early this morning, from DC, where last week it was like in the upper 90s to 100. Eric is here too. Eric, it was miserable in DC last week. So I too am happy to be back here. I want to start first by thanking the organizers for making this possible. It's not an easy feat to put on a big meeting like this, and our organizers do an amazing job as they do every year. And I'm told that we have over 400 people registered for the workshop, both if we do the combined in-person and online registration. And we have people from all over the country, as we always do, and from across the world. And that turnout, especially in these times that we are, is really and breadth of institutional representation that's in the room, in the virtual room, is really a testament to how important CSM is to this community, to our community, and to the fact that CESM doesn't really belong to any one institution. It's really a community effort, has always been and continues to be a community effort. And here at NCAR, we're incredibly proud. We're incredibly proud to serve as this nexus to bring this community together. But it's really your experience, the experience of this community, your collaboration, your contribution that really makes this an exceptional capability, an exceptional model. So thank you very much. I want to acknowledge that it's been a challenging year for our community, for you, for those of you that are U.S. scientists, and a challenging year for us here at NCAR, and a challenging year for the CSM team. I'm hesitating a little bit because I see my boss walking into the room, trying to be incognito. But yeah, it's been a challenging year for us and for this community. And I really want to, first of all, thank you all on behalf of our staff for really the amazing support that you have shown for NCAR over the last 6 to 7 months. It's making a difference, and it's especially making a difference for us, for our staff, in terms of our staff morale. And we are humble. I'm humbled by the support that we've seen. But in spite of those challenges, NCAR, we haven't stood still. We're making great strides, and so proud of what we've accomplished as an organization across all our labs. But I'm really proud of what this team, the CSM team, has accomplished and continues to accomplish. The release of CSM 3, which I'm told by John and Dave is imminent, if it hasn't happened yet. And that's one of the strides that we've made, among others. It's configured really to outperform CESM2. Again, I'm told by John and Dave. I'm assured by John and Dave it outperforms CESM2. And as you all know, CESM2 was an incredibly capable tool. It was an incredibly capable model. So this accomplishment of outperforming CESM2 is really a big achievement and a tremendous effort. CSM3 introduces new capabilities that really lays the foundation for CESM MLE. I'll talk about machine learning in a minute. And this is a hybrid physical and machine learning model that is built in collaboration with the LEAP project. And if you don't know LEAP is Learning the Earth and Artificial Intelligence and Physics. It's an NSF STC, or Science and Technology Center, led by Columbia, and Dave has, at NCAR has been the lead on behalf of NCAR. And this has been really, truly exciting collaboration that we've had with Columbia, and incredibly valuable for CESM that's enabling this evolution of the model. CSM3 also lays the foundation for development of high and ultra-high resolution configuration that will really enable us to probe regional studies with great fidelity. It also enables us to provide data sets for AI training, something that I'll talk about in a minute. So this environment of challenge, in this environment of challenge, I really want you to know that we, the leadership, we're committed to doing everything we can at NCAR to sustain support for our community facilities. And that includes our community models, not just the shiny stuff, not just the shiny objects, but we're committed to supporting our community models. And we're really appreciative of this year FY26 congressional appropriation that invests in science. And also we continue to appreciate investments from NSF for FY26 that continues to support NCAR and continues to support our facilities and other facilities in our community. So we'll continue our commitment, because we know that your access to our tools really leads to discoveries with far-reaching benefits for society. That's really important to us. We're committed to that. We're committed to doing everything possible in our power to ensure that these discoveries, the advancement of fundamental science continues. So the challenges this past, year, this past 7 months, has us at NCAR sort of reflecting, circumstances like these cause you to reflect, right? And so it has us here at NCAR really reflecting on our origins, our origin story, which a lot of you know, and reflecting on what are we here for? What were we designed to do? What were we built for? You know, as many of you know, NCAR was founded in the 1950s, and we were founded out of what? We were founded out of national need at the time. The question then was how to realize the potential of weather forecasting, how to bring it into being, right? How to operationalize it for the benefit of society. That was really the question around that time in our community. But accelerating the fundamental research that would improve weather forecasting required what? It required investment in community infrastructure. That didn't exist at the time, the kinds of infrastructure that we have today. But it didn't just require investment in infrastructure. What else did it require? It really, at the time, required coordination across our research community, across our universities. The community really needed powerful computing capability to develop and test models, as we have today. It needed airborne platforms to conduct in situ measurements for improved process understanding. And in terms of coordination, it needed a place to convene, right? To learn from each other, to build collective expertise, not to be isolated, right, in ivory towers across the country, to co-develop and to collaborate. That was the situation more than 60 years ago. And in some ways, the formation of NCAR was really an experiment at the time. It was an experiment. We weren't sure that it was going to work, or they weren't sure it was going to work. And the question being asked or explored was, what could the community accomplish if universities across the country were more coordinated? What if the nation invested in major infrastructure that was needed to advance the fundamental science, to build that infrastructure, that underlying infrastructure to enable fundamental research? And what if we made that infrastructure openly accessible, not just to the R1s, but to a graduate student at a small institution doing research? We made it openly, we democratized the access to that infrastructure. And we've answered that question. NCAR is again, by the outpouring that we've seen, is a success. And CESM itself answers these questions, and is evidence of that the payoff of that national investment. Today, CESM is really the most widely used Earth system model in the world. And it has been and continues to be vital in shaping our understanding of the Earth system variability, and many of Earth system's interactions and phenomena, such as cryospheric climate interactions and the ENSO, and the impact of ENSO on weather around the world, which is an important question today, right? And that, the important point here is that didn't just happen because of NCAR alone. It didn't happen just here within the walls of NCAR or here in Colorado. That happened because of this community. Again, that community coordination that I talked about, it really happened because of that government investment. It happened because of coordination across our community. It happened because of the history of this workshop. 31 years. And I remember my first CESM workshop as an early career faculty, fresh out of graduate school. And in those days, they had it up in Breckenridge. I think it was the first one in Breckenridge that I went to. I met Jen Hurl, probably. And that was, as an early career scientist, fresh out of graduate school, coming to NCAR, I was amazed at the people that I met, the people I interacted with, the science that was discussed. And so that was really inspiring for me and set me on my career path. Welcome to, by the way, welcome to the early career scientists that are here today. This is a wonderful experience. So today, we find ourselves at an inflection point. And not unlike the one that led to NCAR's founding more than 60 years ago. The U.S. experienced $192 billion in disasters over the last decade. Communities, as we all know, are experiencing more weather extremes on a more regular basis than ever before. And we, the research community, we're being called on to provide answers to these challenges that we are facing. And to really advance our science in ways that really that are needed by communities and needed by sectors of communities, that are needed by farmers, grid operators, emergency managers, that need actionable information on timescales from minutes to decades to really enable these communities to prepare and adapt to these disasters. And so much like the advancements in instrumentation like radars, supercomputing, and other technologies that empowered us to advance weather prediction during the years following our founding, we have new technologies today, right? We have new technology, amazing technologies today at our fingertips to really help us accelerate our understanding. And AI, as you know, is a dynamic and really powerful space that's really unharnessed. And it's really shaping how we approach the challenge of weather and climate science. Leveraging AI is going to help us be more adaptable and more nimble in in answering questions to our science. Being able to run simulations from minutes to days rather than months is really a changing, really the capability of what is possible. And so at NCAR, so this is as we all know, this is a crazy space. It's a very dynamic space. So what are we doing at NCAR? At NCAR, we're working to be very clear-eyed. I like to say that we're not in the emulator rat race here at NCAR. We're really working to be very clear-eyed about what AI can do and can't do for our science. What are the science questions that we can't answer today that AI will help us to understand better? Those are the kinds of questions that we're asking. And it's clear now that AI won't be the death of physical models. A couple of years ago, people were running around saying, well, physical models are dead. And we understand that that's not the case. We know there will continue to be a need for physical models at the core of our research, particularly when we're looking at longer timescale problems. And again, for helping to train, for training data sets for AI training, especially on a global scale in areas that are observationally sparse, that'll continue to be observationally sparse because it's too expensive to get data there. And I'm really excited, and it's really exciting to recognize that this community, the CSM community, has the expertise to lead in this space. And I'm really looking forward to seeing the outcomes of the AI ML cross-working group sessions that'll happen here this week at this week's workshop. We know that you have the understanding needed to determine where machine learning genuinely improves our physical models and our science, and where it doesn't. And I'm really excited because this will be particularly helpful to us here at NCAR. Again, as we try to navigate this very dynamic space, we're really working hard to meet this AI moment here at NCAR. In that regard, NCAR, we continue to build on what we call our AI strategy, and at its core, the effort really focuses on providing leadership in what we're calling community AI. So we haven't gone far from what we're here to, that reflects that we haven't gone far from what we're really here to do. Community AI, it's really what we do best, enabling the community. And so that's where our sort of philosophy is in terms of AI. How do we enable the community? Again, to do these really hard problems that now are unattainable, but may be attainable through AI. So a way to think about this is think about it as how we approach community modeling, how we have approached community modeling. And so our goal is to build an integrated framework of data infrastructure, and data is really important. And at NCAR, we think we have unique capabilities in that space, and we're really working on scaling our data infrastructure and making it available, again, openly accessible to the community. And, also a part of our integrated framework, adjacent to our data infrastructure, our computing resources, software tools, modeling systems, and training. Training is critically important. I'm really pleased of how we're thinking about training here at NCAR for our experts and across the community. And that's all designed to help research across domains to effectively harness AI with an emphasis, and we have principles. We're approaching it with principles, with an emphasis on reproducibility, scalability, broad accessibility, again, democratization, not just the haves versus the have-nots, right? And responsibility. Responsible AI is big in how we're approaching AI, and we've heard that from the community. We just completed a workshop of over 300 participants, and what we heard loud and clear is responsible AI from the community, from you. Go to our website, and you'll find information about what we're doing with respect to AI. But we need your input, and so I'm really looking forward to the discussions that will happen here in the AI/ML working group, but I'm sure that will happen across this workshop. And so I'll wrap up by saying that the development and research that will be shaped this week is significant, as significant as it has been over the last 31 years. The impact will be even more significant, especially at this inflection point where we find ourselves here in terms of science, in terms of technology, in terms of, the funding of science, how science is funded. This workshop really represents a community that is dedicated to furthering national resilience through partnership, through community. So thanks again for being part of that, and I wish you an insightful and productive week. So thank you.
Great, thank you, Everett. All right, so thanks, Everett, for those excellent remarks, reminding us of how vital CSM continues to be even under this current situation. So welcome again, everyone. I'm really glad to see a full room. Obviously, it's been a tough year, as Everett just mentioned, and we will talk about that a little bit, but it's encouraging that we're still here, and I really appreciate all the work you do. So I'm glad to have everyone here in the room and online. And so let's get started. So I'm going to give the traditional state of the CSM talk with way too much in it, as also is traditional. These will be posted online, so I'm going to go through some of these things quite quickly, and you'll be able to go back and review them at your leisure or check the CSM website for more information. Okay, just a reminder on the code of conduct. We want to be respectful, collaborative, consider everyone's opinions, communicate openly, and be mindful of others. And if there's any issues, reach out to me or Elizabeth if you have any problems. And I just want to start off with thanks before I forget it. There's a lot of people, as Everett mentioned, that goes into putting this workshop together. First and foremost, Elizabeth Fairclough there last year at our 30th annual workshop there with some Spirit, 30th annual Spirit. She's absolutely critical. I'm sure you guys have all gotten many messages from her. The CGA administrative team is really important, and we've been able to receive some funding at the late stage from NSF. We're very thankful for that. Eric and those at NSF were able to provide support to this workshop to allow especially some early career scientists to attend. And of course, UCAR Multimedia and Event Services always play this amazing role of organizing this workshop. If you get overwhelmed, it is an overwhelming week. There's a ton of talks, a ton of posters. We do have some quiet room places you can go, outdoor seating, walking paths, so please take your time and take breaks when you need to. And in this world of, where we're sort of forgetting about environmental stewardship, it feels like, we wanted to remind people that we can do our little bit. I know a lot of people flew here and we're all driving cars and we're burning a lot of fossil fuels, but nonetheless, we can take the opportunity to recycle while we're here. So let's just remember to do that. It's not a big step. Okay, so a few agenda highlights before I get into in the talk. So we have exciting plenary talks coming up after the break with Duncan Watson-Paris on differential modeling, James Dunn talking about providing risk-relevant hazard information, and Gretchen Mullendorf from M-Cubed giving some updates on MPAS. We have a very big poster session. I think we have over 50 posters and reception that's starting at 4:30 today, so please come and see all the exciting science. And as Everett mentioned, the cross-working group sessions, I think we got a really nice set of cross-working group sessions this year. We increased the amount of time devoted to them because it seemed like people were really enjoying it, and they were actually all oversubscribed in terms of people trying to get into those sessions. So we're looking forward to those on Tuesday afternoon and Wednesday morning. And then tomorrow afternoon, we're going to the Pattern Break Brewing for a happy hour, self-paid happy hour. That's the old Sanitas Brewery for those who are here and remember that. So fortunately, that's up and running now with Pattern Break Brewing. And then on Wednesday, we have our wrap-up and discussion, and you can bring your questions and discussions then. And just want to remind people here, especially online, that if you want to ask a question when you're online, use the Slido system to ask a question during any session. And then last in this opening, I want to just introduce people to a couple of upcoming CSM-related events. We have a lot of tutorial activities. We really like giving our tutorials and helping the community get up and running. So the CSM tutorial is coming up next week. I want to kind of highlight a kind of cool thing that there's now two tutorials planned in South America this fall. I'm going to try to teach a tutorial on my own in Brazil. That's going to be interesting. And then also there's a tutorial in Argentina in October. And this is part of an activity to try to build up a CSM South America consortium, sort of expanding our reach into South America more deeply. And there are several other tutorial activities going on over the year. Okay, so I want to start off by thinking about CSM impact. It's been sort of thinking over this year as there's been pressure on NCAR, on getting a lot of questions and concerns from people about the health and the viability of CSM if funding cuts happen. And hopefully the funding cuts don't happen and it's not an issue, but it does allow an opportunity to reflect, like Everett said, about what is CSM. And this is a slide that I put together to try to, as I'm sort of thinking about what CSM means. And so when you think of CSM, you often think of it as a code, right? It's a big piece of code. It's 4.5 million lines of code. It's massive. But really, CSM is so much more than the code. And in fact, the code on its own, that's easy to protect. What we need to protect, if we need to protect it, hopefully not, is this CSM ecosystem. And that's, this CSM thrives because we have this intertwined team of NCAR and community scientific and technical staff that, together deliver innovative and impactful science, improve simulation quality, new model capabilities, and community simulation data sets through time. And so these groups have to all work together to produce this. And this is an obviously AI-generated image that tries to capture that I've been sharing with groups who want to hear about CSM impact. And you can't tell here on this particular image, but it created an NCAR with a third tower. So maybe that's good news. We're expanding rather than contracting. Nonetheless, I think this is important reminder for me to, about why we're doing this and how we work so effectively together. And so then, you're trying to think of examples of what we're doing, that are impactful. And I'm just highlighting a couple of science examples that illustrate why CSM is so critical for humans and for understanding of the world. And here's an example from work by Claire Desser about the changing nature of El Nino teleconnections. And so what she did and colleagues did was to run a series of SMILE type simulations, so the seasonal forecasting system, one with the 2023-24 El Nino using anomalies relative to this period 1979 to 2024, and a second set of simulations where you detrended and ran with the anomalies that were based on that detrended data set. So like as if you had the 2023 El Nino, but in the 1980 background SST state. And what she found was that our canonical view that we get this strong Aleutian low, so on the bottom right there with an ENSO, it wasn't happening in the 2023-2024 El Nino when you've had climate change added on top of it. So this is indicating that maybe, there's the long-term trends in SSTs are changing the way ENSO is affecting the world, and that then has implications for things like the Southwest U.S. precipitation, which is usually strongly affected by ENSO and wasn't as much in the 2023. So this is, important implications for prediction example. Second example I like is coming out of work by Alice Vivia, Kristen Krumhart, and others, looking at how we can use CSM data in this case, the CSM large ensemble, to inform future ecosystem on benefits or stressors. And so the cool thing is CSM produces a lot of things, things that many of us aren't even aware of. Obviously the things we know about sea ice and NPP, but also things like Mesozoic biomass and Mesozoic loss rates, detailed information that can then be used to drive impacts models. If you want to study penguin growth rates or krill growth rates or fish biomass. And what they've been able to do using the large ensemble is to ask questions about the time of emergence of when you see a change in any of those systems. And so you've done it for Antarctica, looking around the world, and you can see in this particular region there in Antarctica, you're seeing the impact on penguins is likely to start showing up, basically now. Impact on fishes will be actually positive and go in the other direction, will show up, emerge from noise in a few years. And et cetera, et cetera. So a really cool way to use CSM data to help us, for impactful things, and then you can make decisions then about like conservation and where you want to prioritize your conservation activities. Another in the kind of a similar vein is the Holders Life Zones work that Auditorium and Foster has been doing. This is splitting up the land area vegetation zones into different eco zones, ranging from polar desert down to tropical desert. And what she found in this work is she actually had to add some new zones. So she's calling them hypertropical desert, hypertropical dry forest, and hypertropical forest. So we are going to enter, most likely, if climate change continues, into realms that the terrestrial vegetation has never seen. So that's an interesting thing to be thinking about. Then she can ask questions like, using, again, the large ensemble, how are those ecozones transitioning? So if you look at tundra zone, you can see that it's transitioning into cool temperate forest, boreal forest, or some of it's staying tundra, and there's also some polar desert that's turning into tundra. So this is really helpful to understand what the potential changes in our ecosystem is going to be. And you can repeat that for the boreal system and the tropical system. And here you can see in the tropics that nearly 50% of the tropics on land is going to move into a zone that doesn't exist in the Holders Life Zones today. So we presented this data to the Nature Conservancy, and they're super excited about it, and they really want to use it in their conservation activities. And then a third example I think is interesting is, looking at high resolution simulations. John Facila has done some work to show that you get a much better representation of sea level variability and trends compared to observations when you run with the CSM, when you look at the Mesa Clip simulations than you do with a standard resolution. And this is going to be absolutely critical, again, if you're trying to understand impacts and trying to understand, building codes and building decisions. You really need to know the regional signature of sea level change. And the CSM1 high resolution is indicating that we probably have a model that can do a better job than the low resolution. And then lastly, in impact, I'd like to ask everyone it's important. Impact is more and more important. We need to make sure we're documenting everything that we do to be able to prove to the world why we need to be here. And so just a request to really be careful about citations, whether it's model description data sets or DOIs for actual model data sets, et cetera. When in doubt, cite all that apply as our new model. Okay, so now I want to turn to CSM3 development and spin up. So as I've said over the last several years, we have major upgrades to CSM2, new emissions-driven capabilities, interactive Greenland ice sheet, new ocean and wave models, new atmospheric dynamical core, plus an option to run the MPAS dynamical core, and lots of new physics across all the component models. I'm not going to go into the details. The full list of changes is available at csm.ucar.edu, where there's also a presentation that I gave at AGU, which goes into some of the changes more deeply. So the status update, CSM is finalized, I say in quotes, because we're still finding bugs and dealing with hopefully small issues. And we're spinning our way up towards the mission-driven capability so we can run our control simulations and release the model. And I don't want to highlight specific people because this is really a team effort, but there have been 3 people who have been really, without them, we would not have been able to do this. So I really want to highlight the work of Cecile, Gustavo, and Adam, who have been absolutely critical, dropping everything else they're doing, essentially every day with the new crisis of the day to help us get through this difficult period. So thanks a lot to them, but really thanks to the whole team. And CSM3 development, as you've seen over the last couple of years, has been just as challenging as with prior versions, with old and new biases, difficult to resolve, pathological behavior, and tuning trade-offs. And I'll get into this in a bit. But fortunately, preliminary indications are that the final version of CSM will represent an improvement over CSM2 in many metrics. I'm going to start into that. So starting with the CMAT package developed by John Fasulo, which analyzes a bunch of different metrics. And so the way you've probably seen this before, but basically red is good, and the left column is the best overall simulation. At the very left is the newest variant of CSM3, the last historical simulation that we ran, that we've proved to ourselves that we have a good simulation. We're ready to go, and that is outperforming all the CSM2, which was already performing as well or better than any other CMIP6 model. So this is good news. Throughout much of the development cycle, we were not seeing this, so we were nervous. I think I said last year, I'm not sure we're going to be able to beat CSM2, but we've been, due to the hard work of the team, we've been able to beat it now. So this is good news. And here's another example of, I'm not going to go through the details here, but you can look at them on your own to say that CSM3 is beating CSM2, which was among the best, if not one of the best, CMIP6 models. So each bar there is a CMIP6 model and a different diagnostic. The blue dot is CSM3, our latest historical simulation, and the light colors is the CSM2 large ensemble. And so for precipitation, where it's good or maybe slightly better, we're getting really good improvements in stationary waves, especially in the southern hemisphere, and our global divergent circulation is as good or better as it was in CSM2. So good news on a lot of metrics there. And so also last year was not looking so good. It's looking pretty good now in the latest version. The variance is simulated quite a bit better in CSM3 than it was in CSM2, so that's good news. And on the maps on the right, you see that the variance looks more like the real world in terms of spatial pattern, although we do have enhanced variance in the southern hemisphere that we are still doing a little bit of work to try to tamp down. But in the ENSO region, it looks like much more realistic. We're doing a little bit of final tuning in the portal vortex. It's been looking good, and it's still looking good, and so we're just sort of fine-tuning here. But we're really excited about what the polar vortex looks. It's a pretty big improvement compared to, and it's been a long-standing challenge, but it's much improved in CSM3. And on the land side, we did a lot of work on trying to tune the model, and using automated tuning efforts by Lenny Hawkins and Daniel Kennedy and Katie Dagan and others. And what we're seeing is a good indication that tuning effort, where we focused on tuning the biomass, the GPP, and leaf area index, has led to a significantly better model than we had for CSM2. That 330 is the number we used for the latest version. And then we have a good-looking historical trend in our GPP, indicating we're most likely going to get a good emissions. I'm not going to cover this one. And there's also indication from the land side that we're getting some improvements. Blue again here is good compared to CSM2 in terms of the simulated forcing. We call it forcing. It's a simulated climate at the surface is looking better across most diagnostics. So that's also good news. And then finally on diagnostics here, the Ocean VGC, this is a table that shows different metrics that they use to look at the Ocean VGC, and we are within the observational range for every single metric, except for the bottom one, the atmosphere iron flux, and the Ocean VGC team is working to try to resolve that one. I think it's related to the amount of iron and dust that is a somewhat tunable parameter. So this is all good news, looking good. And we have a new dust emissions representation that gives a much more realistic spatial pattern of the emissions, and has been tuned up to replicate the global emissions quite well. So we're seeing big improvements in the dust AOD, with high dust AOD in the over the Sahel as it should be, and a reduction in the sort of the bright spots over Australia and the South America, which shouldn't have been there, in the bottom left diagram there. So good news on the dust emissions too, which has big implications for aerosols, of course, and chemistry. And then one of the last ones I'm going to show here is the improved equatorial processes by including the kinetic energy backscatter. So this is a parameterization in MOM that was able to allow us to predict or see the emergence of the Shishuya jets in MOM with this backscatter parameterization that didn't occur in either POP or MOM6 without this. And this is important for the ocean circulation, but it's actually critically important for the ocean BGC, where you get big bias reductions in both the oxygen and the nitrous oxides. The green light sheet is also looking quite good. This is the error in the green light sheet for ice extent and ice volume, and we have a much reduced error in the ice extent and volume, so it's down to a 7% error in ice extent and essentially zero bias in ice volume, and a very small drift, which means that we can turn on, and we have turned on, the green lit ice sheet in the CSM3 spin-up simulations. And we're also starting to look at initialized predictions. So Steve Yeager and colleagues in their system prediction working group have done some test simulations, SMILE type simulations, where they are trying to assess whether or not how CSM3 is going to look in terms of its seasonal to decadal predictions. And so this is a preliminary comparison of a 10-member ensemble of CSM3 compared to the 20-member CSM2. And you see that it depends on your El Nino. So in the 1997 event, CSM3 is looking like it's overcooking things. And so we need to try to understand that more. But in the 2007 sort of double La Nina, the CSM3 is actually doing a better job than CSM2. So this is going to require more work to understand where and why the different simulations are doing. Okay, so we are working now towards spinning CSM up. So this is a chart that I've created to try to help us understand this process. I don't expect you ever to read through it. It's quite complicated. Just to say it's a multi-step process, and each one of those steps requires multi-steps, it turns out. But we are working our way through this to be able to, hopefully by near the end of summer, have a fully spun up simulation. So this is where we are. We're on step 3. We're doing this sort of long ocean spin up on the fully coupled simulation to get getting to the point where the ocean circulation is spun up. We've also run historical simulations, and we're also done the ocean biogeochemistry tuning, as I just mentioned, and then soon we'll be able to transition to the ocean and land carbon spin-ups, which take a decent amount of time. And then by the end of summer, we're hoping to have these models fully spun up and start running the PI control. Which then brings us to CMIP 7. What can we do for CMIP 7? Well, our focus has been on CSM3 finalization to date. We didn't know when we were going to finish, but now that we have a sense of when we're going to be ready, we can make our detailed planning. And we know we're going to prioritize the deck and some set of the pretty large number of scenario MIP simulations, and then we're going to have to see how much time and computing time we have to do additional CMIP 7 fast track simulations. And one of the issues is, I'm not going to go through numbers, is the model is quite expensive because it's this mid-top model with extra layers, more expensive ocean model, and so it is an expensive model, and that does impact how much we can do. Okay, I want to spend just a few minutes here thinking about how we can do better next time if we can do better. And so CSM development, as I said, has been just as difficult as it has in the past. We tried many different things over the cycle, but really we have not been able to shorten the timeline at all. And this is frustrating for everybody. And as we know, there's lots of new science that we want to bring in all the time. We need hopefully can find a way to be able to get to new versions faster. This is the situation. Can we shorten the timeline to new versions? If this is a cycle, we have new physics knowledge or new understanding of the system, somebody brings in a new parameterization or a new capability, we do model development, we do coupled model integration and testing, then we couple model simulation, evaluate and learn. That cycle is currently taking, in my opinion, and the opinion of many people here, too long. So can we find ways to shorten that? Make it go faster? There's certain things that are going to be hard to deal with. The pathological issues like the pathobehavior, like the lab C freeze, which is the now famous thing that we've been dealing with for 20 years and came back again this cycle multiple times as it did the last cycle. And you never know how you're going to resolve those, but I just want to mention how we did resolve it this time for those who are curious. It turned out, and we don't know exactly why yet, but when we turned on the prognostic joint flow size distribution in the sea ice model, that allows ocean and turned on the ocean waves being damped by the ice and affecting the prognostic joint flow size distribution and the ocean mixing. When we turned that on, we saw we wanted to do that anyway for improved physics. It has lots of benefits that you can read there on the bottom right. But we'd actually been considering not doing it because it was computationally expensive. But Dave Bailey smartly said, I'm just going to run a simulation and see what happens. And it turns out that was the first time we've ever seen a lab C freeze unfreeze when you turn that on. And so then we said, okay, well, I guess we're going to keep this parameterization and pay the cost. And since then, we have not really had the lab C freeze. So we need to understand why this is. How you get around these kind of situations is going to be, there's no real solution to this. You maybe have to get lucky. So that's one thing we have to keep in mind as limitation. But nonetheless, in ways, are there other ways we can think about to go faster? Automated or semi-automated calibration, I think, is probably critical. It's not even probably, it's going to be critical, right? We can't rely on the hand tuning to get to new model configurations as we've had to do in the past. And so we've made a lot of progress. LEAP has done a lot of work on this and has inspired a lot of work. There's been other efforts, as I mentioned in the next slide. And so I think we're getting to the stage where we have built and we can test robustly new workflows and methodologies to come up with automated calibration, at least for the component models. And we actually did start using this in the CSM3 development. It benefited from semi-automated CAM7 tuning activities. So the LEAP project initiated several perturbed parameter ensembles, PPEs, emulation, and tried to calibrate CAM. What we found when they tried to do that is that it looked like it was really promising. It was going to reduce biases in CAM-only simulations, but those gains were typically lost when we turned to a coupled simulations. So we're not totally surprised by this. We were hoping that wouldn't turn out that way, but that's the way it kind of turned out. But we were able to take advantage of this thing called quad tune. It's coming out of Vince Larson's group at the University of Wisconsin. And because it's so computationally cheap, it's a really simple method where you break the world up into these 20 by 20 degree bins, so very, very coarse, and look at the biases in those. And with only 2n plus 1 in the number of parameters, the number of PPE simulations needed, you can actually do some calibration of the model. And so that is a small enough number, if you have like 10 parameters or so, that you can actually feasibly run that kind of thing in a couple of configurations. And that's what we did, and they made good progress. In the end, we ended up using those parameter values a little bit hand tweaked beyond that. We also need to think about what metrics are reliable in short simulations. The top of atmosphere radiative imbalance, we know historical work on this by Cecile and others have indicated that you need to run pretty long periods of time before you have confidence in that. And if you're trying to tune to that and you have to run 30 years, that's a limiting factor. There's also been nice work by Meg Fowler and Rich Neal and others to try to assess how long of a simulation you need to understand whether an ENSO diagnostic is providing good information or not, or whether it's just noise. And so in the uppermost one, the western extent of the positive SST anomaly, the fact that it's blue throughout and it's not changing much indicates that with a relatively short simulation, you can get a good fine-tuned understanding of where that western extent is. But if you're looking at something like the skew of Nino 3 SST, even out to 200 years, you haven't gotten a good, robust answer for that. So that's a good thing for us to understand. As we're going forward, we should stop expecting we can get all ENSO things on short simulations and understand what we can get from a short simulation if that's how we're going to calibrate. So there's lots of things that we've been thinking about. Can we shorten the timeline? We have lots of ideas. There's a couple of calibration methods that we're thinking about, and I showed an example. The use of emulators to speed things up. A much faster model if we can. Obviously, a faster model means everything goes faster. Differentiable code, and we'll hear about that in a little bit from Duncan Watson-Paris and the benefits of gradient descent methods you can use with differentiable code. Much accelerated spin-up value methods or initialized prediction PPs. And so I think we need to think about this. If we want to accelerate our science, we need ways to make a better, faster turnaround. I think we're poised to make progress on this in the coming years. Okay, so now turning to what we're doing next. Hopefully we'll have a CSM3 later this year. What are our next activities? So high resolution activities. So we've seen with the MESA CLIP simulations, big benefits of running at a quarter degree atmosphere resolution, 10th degree ocean type resolutions, substantial improvements and more accurate depictions of extreme precipitation, sea level change, tropical cyclones, southern ocean surface temperature trends, et cetera. So it's really critical. We just skipped it for CSM2. We need to develop a high resolution configurations for CSM3. It's really high priority. And we've started to work on that. So towards that, we've started working, the CAM group, the AMWG has started to work on CAM7 development simulations at 25 kilometers. And they're seeing really good benefits to tropical cyclone mean climatology improvements. And so what you see is the OBS there and the tropical cyclone hemisphere density track. And then you see the biases in those from the CAM5. And there was actually pretty strong biases in CAM5. If you look down to CAM7 final, probably not final is not the right word, but CAM7 tuned, you're seeing it, those biases have gone quite a way. And if you look on the right, is a Taylor diagram indicating the same thing, that the CAM7 tuned version that they have now is competitive with, say, the IFS and is not too far off from Era 5. So that's good news. They're also starting to do work on the ocean in terms of the ocean high-resolution MOM6, CESM 12th degree simulations, coupled with WaveWatch 3 at a low resolution, and seeing good results there too. And so on this diagram, this movie that Gustavo sent me, you start seeing some impact of the tropical cyclone tracks of the wind speed there. And so there's good progress here on the surface wind speed, and they're doing work to try to tune and calibrate this model too. And one thing that, here's a good news and bad news. So in terms of those preliminary simulations, we're seeing this equatorial undercurrent is overly strong, showing there on the left, too strong compared to observations, and the tilt isn't very realistic. So that's not great, hopefully correctable. But it's interesting that these Shuya jets that I mentioned earlier emerge in these high-resolution simulations without this sort of backscatter parameterization, which you don't need at a 12th degree. They emerged with MOM6 at high resolution, and they didn't emerge with POP. So that's kind of a good news. So there's lots more to learn about these simulations, but we're starting to make progress, and somewhere down the line, we haven't decided when yet, we'll get to coupling these. We also have work on kilometer scale grid lengths, and this is nice work by Adam Harrington and others, where we've been doing the diamond simulations, short simulations, about 40 days, and in this situation where you turn off deep convection completely, this no deep simulation, you get this popcorn regime, and Adam and others have found that if you turn on the mass flux scheme from Club to deal with shallow convection, you can actually get the emergence of organized convection. And this is bringing CSM sort of in line with some of the best models in terms of their kilometer scale representation of convection. So that's good news. And the Diamond 3, the 1 year long simulations are running at about 50 or 60 days in, and they're going at 4 simulated years per day. So we got a little bit of time before the full year will be done, but that's exciting news for the CSM activity. We also have two big projects, Storm Speed and Turbo, which are both working to bring in new, especially GPU capabilities and new dynamical core capabilities in the case of Storm Speed to hopefully accelerate the model. And those projects are both moving along quite nicely. I don't have time to talk about it in too much detail. And here's an animation coming from the Storm Speed project where they've regionally refined down to kilometer scale resolution in the inner core domain, and we see these really narrow, deep convective cells as observed along the leading edge of a cold front, and very strong winds that are behind the front, again, as observed. So the simulations are looking really nice with this DOE non-hydrostatic dynamical core in CAM. And on the ocean side, we have the accelerating the regional modeling through the crocodile activity. We've got Python tools that enable users to very quickly and easily set up a regional MOM6 configuration. So that's a pretty good, powerful new tool. And then also tools to help compare ocean models and observations using data simulation under the hood. And we're excited about the crocodile workshop coming up this summer, where we're getting users to play with some of these tools. And these are 3 examples from the last year's workshop of students who just within that few day tutorial and workshop were able to get these really cool new simulations going. So looking forward to that. So Everett mentioned, so that's a high resolution. So I think we're making good progress. We will accelerate our efforts or increase our efforts on high resolution once we get CSM3 low resolution released. But we're also making a lot of progress on AI/ML and exploiting this, sort of from a community perspective. How can we use AI/ML to benefit CSM, and thinking carefully and deeply, and not, as Everett said, getting into the rat race of emulators, but really thinking about how we can improve the usability and the quality of CSM. And so I've been talking about this many times. We are using through the LEAP activity and also sponsored by M² Lines, supported by M² Lines, we are bringing new machine learning algorithms and high fidelity models and observations together to build new ML-based parameterizations, also to build these new ML-enabled parameter optimization, as I mentioned, to build the next generation CSM, harnessing ML and data to enhance CSM. So we had our second annual hybrid Earth system modeling implementation workshop just last week, and this is an effort between LEAP, M² Lines, NCAR staff, and also the ICON group, Veronica Eyring's group, has been coming over for the last 2 years to really talk about all the challenges that come with hybrid modeling. And it's been really powerful to compare experiences across 2 major models, dealing with some of the technical and methodological challenges that go with trying to bring to build a hybrid or system model. So, the idea is collaboration and knowledge exchange. And we're seeing some success. I'm not going to go through this slide in the interest of time, but we're seeing some success with some of these new parameterizations. We're really showing potential for significant benefits. And this is an example from the warm rain microphysics. So these are the parameterizations that are sort of in progress under development across the world, either from the LEAP project, M-squared lines, or other. And two things I want to highlight. One is that we've built in this F-torch capability into CSM across the entire CSM, and that allows us to connect to the PyTorch, which then allows you to access to all the machine learning capabilities that are available within PyTorch. And so pretty much all of these different activities are now relying on PyTorch, and we've had new groups come in and successfully use this bridge. So that's we're excited to see that. They span the different components, and so we have activities going across the atmosphere, land, sea ice, ocean, and land ice. And last week we heard from 10 different projects, so I think it's good news that we can have 15-minute presentations from 10 different activities, all with quite a bit of evidence of progress. And so several of those presentations will be repeated here, so you can see them this week. But based on what we decided last week, is it seems like this set of about 5 or 6 parameterizations are essentially ready to be integrated, and we're going to try to get to at least an AMIP type simulation ASAP. I'm not sure exactly when that is, but maybe later this summer, early this fall, our first AMIP simulation with these multiple parameterizations. So we've done AMIP simulations with just single parameterizations, but it's a new challenge when you're trying to bring multiple ones in together. The other activity is emulators, and thinking about how we can exploit emulators to advance our science. And so I'm sure you've seen the presentation by now about the Camulator built off the credit platform developed in CISL with the Miles group that DJ Gagne leads. And so this is the canonical view of image that Will Chapman always shows of the Camulator. I'm not going to show his movie because I didn't have access to it, but nonetheless, you've probably seen it. But what I want to say is our goal, so we've demonstrated, Will has demonstrated that we can build an emulator at CAM that's quite robust and long rollouts and all the issues you're trying to resolve, conservation. The question then is, can we move beyond that and build what I'm calling a flexibly coupled AI CSM? We don't know exactly what the final name will be, or maybe a CS emulator, but build emulators for each one of the different component models and then couple them together. This seems like something that's feasible. There's groups here at NCAR and around the world who are trying to do these things. It does seem like it's possible. And so if we get to that, then we have the ability to do things like, try to emulate the Mesa Clip simulations or CSM3 simulations, each one of the components, and then couple them together, and then be able to do things much, much faster if we want to run ensembles, for example. So, or we could be doing things like this, which is what Will Chapman is working on now, which is taking the Camulator and coupling it into the CSM system and running coupled simulations with a real physical ocean model and sea ice model coupled to an emulated atmosphere model. And what he's shown here is that the green is the Camulator and the red is the CSM2. That the model is doing okay. I mean, there's lots of things you got to look into, but it maintains long-term stability. The seasonal cycle looks reasonable. The mean state biases remain controlled. It's not blowing up, and coupling does not destabilize the emulator, so the emulator can handle it. So I think this is good news. This is sort of telling us that we might be able to get to a situation where we can really think about flexibly either building a fully coupled emulator or just component model emulators or even parts of models as an emulator. And that's, I think, the space that would be really exciting if we got to be there and be a leader in sort of this flexibly coupled AI CSM. And there's been some progress also on a MOMulator. Here's an example where they were able to emulate a regional MOM6 using the credit configuration. And then lastly on AI, before I get close to closing out here, is the other big thing is all the code generation tools, right? Claude Code is becoming extremely powerful, I'm told. Obviously, I don't do anything, but it's extremely powerful. It can do things that nobody thought was possible. And so we're going to need to think about how to exploit this and what it means for us. And I'm sure we're going to have conversations during this week and in the coming months and years. And And we've already seen some activities across the CSM that are showing the potential to maybe translate CSM into different languages to get benefits. And then one of the benefits might be that you want to get a differentiable code, which allows you then to do parameter optimization really fast and other things. Or you might want a more accessible model, or just modernizing ESMs to be able to run on different architectures. So we've had a graduate student has been successfully converted the CLM multi-layer canopy code from Fortran to JAX using multiple agents. Different agents doing different things. So there's a translation agent, there's a testing agent, there's a repair agent. You'll have to hear from her. I can't remember if she's speaking this week, but she's given several talks here recently. And so it's good proof of concept. It's replicating CLM multi-layer canopy model, essentially exactly. So can we expand this? I think maybe people are already going to try. Okay, so then finally, while we're doing all that, we do want to keep making our physics better, right? There's a lot of technology where we're going high resolution, we're AI, ML, but as Everett said, it's not the death of physical models. So we have to keep in mind we're still trying to build better physical models. And so one way we're doing this is through this CESM project, which is working to deliver an isotope-enabled CSM version 3 to do comprehensive modeling of isotopic water cycle and also powerful water tracking. And so this is a relatively new project, but the work is underway, and in roughly a year to two, we should have a CSM3 water isotope-enabled version. So we're excited about that. An example from the chemistry group, inline photolysis scheme is available within CSM3. It's not going to be in the default, but it does allow us to do new science, and in particular, online calculation of impact-relevant diagnostics like the UV index. So you can imagine this would be pretty powerful to have this in a prediction system, as an example. And there's many other activities I just had a chance to highlight too. So I just want to finish with what I kind of see as the vision. I'm trying to think about what our vision should be for a faster, more agile, and more skillful CSM. And so this is a slide that I put together for different contexts. But as Everett pointed out, the world needs more reliable climate and weather information at a range in time and space scales to understand the risks, to prepare for disasters, and to learn how we can respond to a changing planet. And so this is the vision I think we can be thinking about. So we want to make the model development cycle faster, so we need to be thinking about ways to do that. We can try to exploit AI for that. We want to have enhanced multi-scale capability, whether that's through AI or whether it's through physical models, and probably both. We need to make better use of observations, and most likely we're going to need to consider how to modernize our code either through AI-assisted or other means to build a better and more agile CSM. So that's it. I want to thank you for your attention. It's a lot, I know. I sort of apologize, but also I also want to capture the breadth. I think that's what's exciting about CSM. So thank you. So if anybody has a burning question, I can take it. Historically, it's too overwhelming for people to think about all this right in the first talk of the session. Good. Oh, cool. Yeah. Yeah, of course, yeah. It's not on there, but yeah, systematic evaluation is obviously critical. It needs to be embedded within all this, and we had a pretty detailed conversation last week with Veronica's team about improving our evaluation methods, and there's been a lot of work historically over the last decade or so in improving and systematizing that. So yes, it should be in my vision. I kind of take that as implied that we need to do that, but it's a good point. Okay, so now we get the fun part. We get to recognize the work of our colleagues for the CSM Distinguished Achievement Award. So this year, I'm very happy to announce that the winner of the Distinguished Achievement Award is Charlie Coven from Lawrence Berkeley National Lab. Charlie, please come up. So here's your award. We're going to do pictures later, but
okay. Wow.
Yeah.
Thanks, Steve.
Welcome to the club. So we had a lot of good candidates this year for this award, but it's my pleasure to give this award to Charlie. Throughout his career, Charlie has combined his exceptional scientific creativity, intellectual breadth, and curiosity to make transformative contributions to CSM. from pioneering representations of permafrost carbon dynamics that help distinguish CSM as a leader in coupled carbon climate science, to co-leading the development of the FATES, which is the next generation vegetation ecosystem modeling framework that will form the basis of the next generation CLM. Charlie has repeatedly reshaped how we represent land processes and earth system models. Beyond his scientific innovations, he has been a dedicated leader, a community builder within CSM. He's now on the SSC, and influencing model development, CMIP activities, and IPCC assessments. His work has really advanced both the scientific foundations and the future direction of CSM, making him an exceptionally deserving recipient of this recognition. And as many of you may know, Charlie and I are very good friends. We've been good friends for 20 plus years through our permafrost climate work. And I just want to say this is not rigged, right? I just get one vote in the overall process. So just want to assure you, it's just by chance that Charlie's up here. But I'm glad to see it. So Charlie, congratulations. And now the penalty.
Thanks, yeah. Thanks, sir. Thank you. And yeah, thanks everybody. This is definitely, yeah, I'm not 100% sure what I did to deserve this, but I'll take this as an opportunity to talk about the importance of Earth system modeling and something that I've been sort of banging my head against for the past few years of why it's so hard to break the TCRE relationship. So this photo here is one that I took up in the during the sort of orange sky day in the Bay Area, up in the hills above Berkeley. Sort of, as we're looking into the future of this climate change. What do we see, given everything? And I should also say that it's particularly meaningful to receive this award this year. As Everett said, it's been a difficult year for everybody, particularly everybody here. But yeah, so thanks for honoring me in this. I want to start out with a huge number of thanks. I know I've forgotten some people, so apologies to those who have forgotten. But just this is the work I want to talk about is really at the heart of Earth system modeling. There's so many people from the FATES team, the CLM and CESM team, the BGC working group, CMIP collaborators, Abby and Ben in particular, who I've been working with on this a lot. So just thanks to so many people. It's really the community in the CESM is really what makes everything work. And so, like Everett, I actually want to start off this talk by going back to kind of like where are we coming from. And I want to start with the Bretherton report, or the Bretherton diagram, made by from this report that Francis Bretherton, the former NCAR director, led this report for NASA in the 80s. It was now 40 years ago, and it really set the question of Earth system modeling, the goal of Earth system modeling. And the idea is, thinking about CO2 as part of the Earth system, coupling all these different parts of the system, moving beyond, at the time in the 80s, physical climate models, to something that's much more about the coupling of the physical climates and the biogeochemistry with people as a sort of somewhere in there, so possibly a forcing. And this really, this 40 years ago, this kind of set the goal of Earth system modeling that has, we've been following ever since. I should say, there's actually like a bunch of there's no good scans of this diagram, despite it being really important on the internet. So I actually got the thing out of the library from UC Berkeley, and it's actually like a really good report. Like if you're into like particularly the 80s graphics, it's super cool, and it's but it's it's a really far-seeing report from 40 years ago that still we still haven't achieved the goals. And I say this is the simple version of the Bretherton diagram. I'm going to come back to this. There's a more complicated version, which I'll get into later in the talk. And okay, so where are we within CESM? And I want to start also with a thanks to my mentor and PhD advisor Inez Fung, who sort of made this first version of an Earth system model in the CESM with the CSM 1.4 carbon cycle that she led, in which she won this award for almost 20 years ago. So about halfway through this period of the Bretherton diagram, sort of outlining the idea of an Earth system model, it's been part of the CESM ecosystem. And she also led this effort that she called the Flying Leap, because it was this leap into the unknown, which now we call C4MIP, the Coupled Carbon Cycle Climate Model and Comparison Project, which I'll sort of talk about the legacy of in this talk. Okay, so I'm going to start off the importance of Earth system modeling by talking about this chain of causality between CO2 and climate. And there's a bunch of links in this chain, and each of these links are really important to sort of think about how they relate to each other. So the first link in the chain is CO2 emissions. Right, people are burning fossil fuels, putting CO2 in the atmosphere, and so that's kind of the first link of this chain. You can see that emissions have risen over decades. As a result of all those CO2 emissions, we got CO2 concentrations building up in the atmosphere, and that's like the next link in this chain. So, we can see the Keeling curve, CO2 concentrations, continually, inexorably going up, with all these other patterns like seasonal cycles, et cetera. And then the next link is climate change, right? And we know that global warming is happening. We're closing in very quickly on 1.5 C. We're basically like somewhere in the midst of crossing that critical, threshold that was only like 10 years ago that we had really set that through the Paris Agreement as a threshold not to cross, and we're already basically in the process of crossing that. And then the next is climate impacts, right? And this is, the people's lived experience of this is really kind of what matters. And for example, if you think about it from policy context, the Paris Agreement follows this change in reverse, right? So it basically says, there are certain global warming levels that it is unacceptable to go beyond. 2 degrees, the consequences of that are too great, and therefore we must try and limit global warming to those levels. As a result of that, sort of working backwards, therefore we need to get to, we need to zero out emissions by, midpoint of the century, so that we can avoid these harmful impacts that would happen if global warming crosses these certain levels. Okay, so now I want to go through each of these chains in order and sort of talk about like the things that happen along them. So between these first two links, between CO2 emissions and concentrations, this is where all the biogeochemistry happens, right? Only about half the CO2 that we emit stays in the atmosphere. This could change. So from, we have these annual reports from the Global Carbon Project that show, all the fates of atmosphere. And so, half of what we emit stays in the atmosphere. The other half gets split between the land and the oceans. And, there's been a relatively constant fraction over time. These sinks have grown with our emissions. But this could change, right? There's nothing that says the airborne fraction has to stay about a half. And this is why we build Earth system models. To couple all these processes in to ask, well, how will the atmospheric CO2 airborne fractions change? What will the result of that be? And the results of that from the models that we have is that we do expect things to change, right? We expect that, in particular, that the more CO2 we emit into the atmosphere, a greater fraction of that CO2 remains in the atmosphere. And this is in a figure from the most recent IPCC working group, the Summary for Policymakers, Figure 7, showing that this airborne fraction, we expect it to decrease with greater amounts of emissions on different scenarios. So this is an important part of the climate change problem. Okay, now I want to talk about the next two links in this. It's between CO2 concentrations and climate change. And so you can imagine, a figure here with concentrations on the x-axis and temperature on the y-axis to sort of link these two pieces. And I'm going to ask, how does this relationship between these two things tell us about what might be needed to stabilize temperatures? And so you can imagine like two curves in this space. There's sort of a short-term climate response and a long-term climate response. And we typically quantify these two things with these two metrics defined at 2 times CO2. We've got the transient climate response and the equilibrium climate sensitivity that capture both this short-term response of just basically warming the atmosphere versus warming both the atmosphere and the ocean, and under longer time scales. And okay, so where are we right now? So we're somewhere on this sort of short-term climate response. We're emitting CO2, 10 petagrams of carbon per year, and so we're moving to the right in this space because CO2 concentrations are increasing, and as a result of that, temperature is changing, right? But you can imagine if you're thinking about climate policy and mitigation, there might be some point at which the CO2 concentrations stop going up, and so then what happens, right? We know over time that you're going to have to move from the dashed line to the solid line, just because one's a short-term response and one's a long-term response, and so there's going to be a tendency of the system to move from the one line to the other. And historically, the way this has been thought about is, well, okay, so that means you've got this committed warming, because at any given CO2 concentration over time, the long-term warming is higher than the short-term warming, so there's going to be some concentrated, some commitment of warming at a given CO2 concentration. But the interesting thing is that natural carbon sinks are always happening, even in the absence of human responses. Basically, carbon is responding to prior emissions, and so it's going to tend to pull things down and move things to the left here in this space, right? And so there's this other metric that we use, zero emissions commitment, that kind of balances out these two things, or that arises as a result of these balances. On one hand, you've got the tendency to move from the dashed line to the solid line because of this shift from the short-term to the long-term climate response. On the other hand, you've got this tendency for natural sinks to kind of pull the system to the left. So what actually happens if we can get to net zero, and this is why sort of net zero equates to climate stabilization, is that you move from the dashed line to the solid line by moving to the left rather than upwards. And this is kind of a crucial insight from our system models. Okay, and so now let's sort of bring these two pieces together, right? So let's skip the CO2 concentrations entirely and just look at the relationship between climate and cumulative CO2 emissions. We've got the super complicated system of the carbon cycle and the super complicated system of the physical climate system. And if we couple them, you expect a like doubly super complicated system, right? But what actually happens is instead of getting a doubly super complicated system, you get actually something that's much simpler, which is that it's basically a straight line between cumulative emissions and temperature change, right? So it's linear proportional with a single straight line, and it's emissions pathway independent, right? All of the different emissions pathways that we use into the future all lie on top of each other. And so instead of getting something much more complicated, you actually get something that's much, much, much simpler. And this simplicity of this relationship came out of this first set of C4 MIP experiments that Ignatius and others organized with three important papers from 2009 that sort of identified this proportionality and its implications for remaining carbon budgets. And this proportionality has held up ever since. And this proportionality is called the TCRE, the transient climate response to emissions, or to cumulative CO2 emissions. And it basically sets the slope of this line. And technically what's shown here is an effective TCRE because non-CO2 forces are also present. Strictly, TCRE is only for CO2, but it's such a strong feature of the system that even in the presence of non-CO2 forces, it also kind of holds. And then the pathway independence piece of this suggests that if we stop moving from left to right in this space, then we'll also stop moving vertically. And this, again, is the zero emissions agreement, right? Basically, if this is perfectly pathway independent, then we expect no further temperature change. But there's maybe some small amount of zero emissions change that would happen if we stop moving from left to right. And again, the reason why this zero emissions agreement is small and we don't know its sign is that it's balancing these two opposing tendencies that are in the Earth system. If you zero out emissions, two things happen. One, the atmospheric CO2 concentrations tend to decrease, but because of ocean and land sinks, which continue but weaken in time, and then you've got continued ocean heat uptake as well, which then weakens over time. And so you get this transition in this sort of atmospheric energetic balance from losing heat into the ocean to losing more heat into space as CO2 tends to decrease. And those two things cancel each other out to give you kind of a zero warming after you get to net zero emissions. And then, again, this is super important for policy because these two relationships allow you to construct a carbon budget for climate stabilization. So, the Paris Agreement says we want to stay below 2 degrees and endeavor to keep things below 1.5 degrees. So you can pick your global warming level that you want to stay below. You have this slope from this TCRE line, which we're somewhere along it. And so basically all you need to do is then sort of subtract out for whatever warming you might expect after zero emissions, and then use that to sort of to go across in this line and tell you how much cumulative emissions you can emit for any point to any point in the future. You know where you are now and the difference between the remaining carbon budgets. This is extremely important for a carbon for a climate policy perspective. Okay, so the question I want to ask is: are there limits to the CCRE proportionality and its pathway independence, and if so, what are they? And for example, as I showed before, we're closing in on 1.5 degrees C right now, which is the goal of the Paris Agreement. So what if we want to get back to that, right? Does the same proportionality hold if we want to move from right to left in this space? As one example of a possible, possible sort of climate implication of this. And in the most recent IPCC report, what we said was that there's limited evidence supporting this quantitative application of TCRE to this, sort of right to left move, i.e. we don't really know if this works. Since then, I've been looking at experiments to try and understand where are the limits of this TCRE proportionality. And so on the bottom left is super high emissions going out to the year 2300. So 5,000, 6,000 petagrams of emissions, just enormous amounts of emissions, and as a result, enormous amounts of global warming. And weirdly, this the linearity of this holds even out to past the middle of the next century. So it's under sort of crazy high emissions trajectories, even out past 2100, the linearity of this holds. So it's incredibly robust on this, to anything at all policy relevant on the high emissions side of things. What about on the low and change to negative emission side? So that's what we show on the bottom right, and it shows that basically if you go out and come back, it actually holds pretty linearly to there. But then you see that some of the models show some nonlinearity. Some of them are above on the way back, and some of them are below on the way back. And so there is some pathway dependent on our negative emissions. And interestingly, it appears to be closely linked to the ZEC. So if you design a metric, say the temperature asymmetry at 200 petagrams less than the maximum cumulative emissions for each of the models, and you diagnose that for each model, and then plot it against the zero emissions commitment, which is how much warming you get after an abrupt cessation of CO2 emissions. Those two things agree with each other about as well as anything in our field, right? So this is the one-to-one line, and they basically, the zero emission commitment is predicting with very high fidelity any of this overshoot asymmetry and this very non-idealized, in the presence of non-CO2 climate forcers, et cetera, the dynamics of the Earth system. So there is some pathway dependence on our negative emissions, and it seems to be closely linked to the ZEC. But there's lots of other things going on in these scenarios, right? Land use, non-CO2, the fact that emissions are inferred from concentrations, and therefore not all the models see the same emissions. So we thought we wanted something simpler. So what we did is design an idealized experiment to test some of this. And the simplest way I can think about it is a symmetric, continuous emissions-driven experiment to infer this reversibility. So basically, let's assume that cumulative CO2 emissions follows a Gaussian curve, which means the annual CO2 emissions follows the first derivative of a Gaussian curve, which is what you see on the left, right? So there are a few features of this, right? So you've got some year into this where you get a peak emissions rate, slightly higher than our current peak emissions rate of 10 petagrams of carbon per year. You get to a net zero at some point, in which the cumulative CO2 emissions stop rising because the annual emissions get to zero, and then some hypothetical idealized negative emission technology, which, to be clear, doesn't exist on the planet right now, but you can imagine, future generations getting, CDR or BECS or whatever to actually work in some way that allows them to pull CO2 out of the atmosphere. And the sort of logical end case of this would be, well, what if we pull out all of the CO2 that we previously put into the atmosphere to get to a point of cumulative zero emissions? What would happen under that? It's just kind of the most extreme possible version of this. Okay, so we take this and do an emissions-driven CESM2 forced by this idealized CO2 emissions time series and ask what happens under this scenario. Okay, so to get the results, so here's our cumulative emissions curve, peaking at 1,000 petagrams of cumulative emissions 150 years into this idealized scenario. Okay, so and I've normalized all these other things to sort of peak at the same vertical level. So CO2 concentrations, interestingly, CO2 concentrations peak before cumulative emissions peak, which is to say that at the top of this curve in the cumulative emissions, which is that's the point at which you get to net zero, the atmospheric CO2 is already declining at that point. And the reason why is because if at the point of getting to net zero, if you've stopped emitting CO2 to the atmosphere, but the natural land and ocean carbon sinks are still active, well, that means the atmospheric CO2 has to be declining, and that was why the atmospheric CO2, leads emissions and peaks decades before emissions peak, and then warming lags that atmospheric CO2. Right, so there's about a couple decade lag of the climate of the global mean surface temperature from atmospheric CO2. But interestingly, those two things kind of offset each other, which is so as a result of this, climate is basically roughly in line with the cumulative emissions. It actually seems to peak slightly before cumulative emissions. So in this particular configuration, you get to peak warming before you get to net zero. Of course, there's more to the climate system than global warming. Global precipitation lags global mean temperature. And I'll be talking about this on Wednesday in the BGC working group session. Turns out the reason why this is intimately tied to the set of processes and energetic processes that are why net zero equates to climate stabilization. Okay, so how about in this sort of temperature versus cumulative emissions space, right? And so our hypothesis is that under the warming piece, it'll follow this TCRE line, and then it might be offset by the zero emissions commitment under negative emissions. And we know both of these two things from previous experiments that we've done, and that's basically what happens, right? So the red line is the smooth response to this, and the key thing though that was a surprise from these experiments is that this transition from the TCRE line to the TCRE plus ZEC lines occurs well before net zero. So previously the idea of ZEC is that what it's a measure of is the warming that happens after net zero. The way it's calculated is the warming that happens after an abrupt change to net zero. And so in this transition from this gradual transition to net zero, the ZEC actually manifests as a deviation from the TCRE relationship well before you get to net zero, and then persists throughout this long period of negative emissions. And so the ZEC can't be thought of as this committed warming that happens after net zero if it starts to influence climate before net zero. Instead, the way to think about ZEC is a general measure of the path dependency of the temperature to cumulative emissions relationship under strong mitigation. Okay, so all that's with CESM2, which is one Earth system model. We wanted to extend this to the full, much larger set of Earth system models. And so Ben Sanderson led this effort to sort of revamp the coupled Earth system experiment, sort of an idealized Earth system model version of the DEC experiments to be like the simplest possible emissions-driven set of experiments. And basically, the idea is to do either positive emissions, just hold emissions constant 10 petagrams per year, or zero emissions to go from 10 petagrams of carbon per year to zero at year 100. And with these two experiments, you can then calculate the TCRE and the ZEC directly as from the temperature trajectory of this. Or then negative emissions, which in this negative emissions experiment is basically just sort of a straight line version of the previous one that I was just talking about. That there was sort of Gaussian cumulative emissions experiment. The idea is you emit positive emissions for a while, and then you gradually, in this case linearly, go through net zero emissions to negative emissions, and then hold things constant. And so so on the left is what it looks like in CO2 space. CO2 emission space. In the middle is what it looks like in cumulative emission space, and on the right, because of this proportionality of global warming to cumulative emissions, you expect those two things to be proportional. And so we did this for 10 CMIP6 generation Earth system models. I should say that we've also gotten this into the CMIP7 fast track because we think it's really useful and important. And the models do basically what you expect them to do. You get warming, then flattening, and then warming, then reversal under these two things. And crucially, under this most extreme reversibility experiment across 10 Earth system models, this TCRE proportionality still holds across the ensemble mean all the way back to this cumulative zero emissions, right? So in the ensemble mean, the red is like the ensemble mean, and I've normalized this for the TCRE across the models. So everything's kind of forced to go through this point of 1.0 and 1,000 petagrams. So which is why all the red lines, sort of line up. But if you normalize it like that, and you look at the reversibility, it's basically follows, the ensemble mean basically follows the same proportionality back to cumulative zero emissions. Which is like it's just a shockingly simple system for given the extremity of the experimental design. And again, across the models, the ZEC predicts much of the overshoot asymmetry. So some of the models are perfectly linear, some of them have some nonlinearity, and of the ones that have nonlinearity, much of it is predicted by this zero emissions commitment. This idea that zero emissions commitment represents offset from the TCRE, and so it represents basically the only sort of pathway independence in this system, that you can diagnose it from zero emissions, but it holds across this much broader set of ranges, including all the way out to cumulative zero emissions. Okay, so this is to me, this is the fundamental problem that I want to come back to. So ESM experiments suggest this incredibly wide range of validity of this TCRE relationship, but how much confidence should we actually place in the result? Here's where I want to come back to the more complicated version of the Brotherton diagram from this 1986 report. And already at the time, if you look at it's sort of in parts of this box on like the terrestrial ecosystem, they talk about things like plant stand dynamics, right? So like disturbance and recovery and successional dynamics. Like that has not been part of our system models though so far, right? Nutrients are, but like decomposers, right? With mimicked in land in the land model, we're only just getting into some of this. So like we have not at all gotten to the point of representing all these things that 40 years ago, the Brotherton report was saying, well, this is obviously what you need to put in your system models, right? And we're not even at that level of complexity yet. 40 years later, we're just still getting to this stuff. And so if you look at some of these, the set of processes across the CMIP6 Earth system models, and some of the things that might plausibly give rise to nonlinear dynamics or more complicated emergent dynamics than just a simple straight line, we know that there are a lot of things missing, right? So CESM is one of the more process-rich things. We have a fire model, we have permafrost carbon, we have nitrogen cycle. We haven't had dynamic vegetation. But many of the models have all red boxes or only a few of these things. And crucially, you shouldn't think of these as all just on their own. They all interact with each other in really complicated ways. And so we want models that are comprehensive and validated, et cetera. Okay, so this is where I'm going to plug fates as an approach that might increase the complexity of these models up. Oh no, it's my animations. Oh no, I've broken the whole thing. Uh-oh. I broke the whole system. Sorry, everybody. Anyways, what it's showing is this movie of vegetation growing over time. Okay, good. It came back. Thank you. And crucially, so what FADES does is it represents this subgrid heterogeneity by tiling the world into disturbance patches that are dynamic in time. So disturbance is always happening. It's always creating newly generated, newly disturbed areas, and you've got all these plants that are growing on these disturbance patches, competing for light, competing for resources, and so you get this emergent dynamics of ecosystems, structurally complex ecosystems emerging from this relatively simple set of rules of plants competing against each other. And we think that this is the kind of thing that you need to include in Earth system models to get these disturbance effects. And so we can now take this FADES model. So that was just like I was just showing in a single site, in a single tropical forest site. We can now run it globally with land use and look at these interacting natural and anthropogenic disturbances. So what this is showing is the age distribution since disturbance of the land surface. So in green is just primary land, so only natural disturbance. In the blue is secondary land, so places that have been logged or abandoned agriculture, so an interacting between natural disturbance and anthropogenic disturbance. So we can now sort of talk about the age distribution since disturbance of the landscape over time and how it changes. With fire, other types of disturbance we expect with global warming, we expect that to be important for getting this age distribution, pushing things into a younger state and possibly a more dynamic state. And that's the kind of thing that might plausibly change these dynamics, at least on the land side, away from these linear systems. Of course, in other parts of the Earth system, there are many other things that might make it behave more or less linearly. But just an example of like the kind of thing that we're excited about this is that we can now talk about interactions, or we will, once we have all this stuff working, we will be able to talk about things like interaction between fire, disturbance, and permafrost, right? So in the Arctic, you've got much of the Arctic is covered by ice-rich permafrost. If you burn off the active layer, what happens is you burn off the insulation. Or sorry, if you burn the insulating organic layers, you burn off the insulation, you will deepen the active layer, which is the part of the permafrost that thaws every year. As a result of that, you're removing carbon effectively from this frozen solid form, deep in the soils, to something that thaws every year. And we expect that that's the kind of thing that could lead to very rapid loss of rapid thaw of permafrost and possibly rapid loss of carbon as a result of that. And so it's the kind of thing that might plausibly give rise to something nonlinear in this system. All right, so with that, I'll just end. Conclusions, this TCR relationship is it's the central theoretical result of Earth system modeling. Of course, I'm using Earth system modeling here in the sense of coupled carbon climate modeling. And it's extremely important for informing climate policy. Even across a really wide range of emissions pathways, this TCR relationship appears to hold robustly. And most deviations are captured by just this one second order term, ZEC, which also holds across a fairly wide range of scenarios. But the key question is, how much can we actually trust Earth system models, right? Is this simplicity of this TCR relationship, is it a real emergent feature of the Earth system, or are we getting this simplified and biased result because our models are incomplete? And I think that just goes to show there's still so much work to do to understand this basic, most fundamental question of do we trust our models in this what I would argue is kind of one of the most important predictions that they're making. And so I think, I'll end there. Thanks, everybody. I think that's from the last one.
So, first of all, congratulations. You've done great work, and it's really exciting to see the sort of Earth system modeling come together, and having a sort of deep perspective on what this kind of modeling can really offer. Something I've been curious about, and I don't hear people talking about, is you mentioned removing carbon dioxide from the air to get to zero, to reverse emissions and so on. And then there are other people who wanting to pull the carbon dioxide out of the ocean. But it seems to me as though I haven't heard anyone say that it actually matters which way you do it. Because it seems to me as if you pull the carbon dioxide out of the air, then the ocean will start outgassing. And so the carbon dioxide concentration in the air would go down a lot more slowly if you pull that out of the air and not out of the ocean. Is that true, or has there been any conversation about that?
I would argue we haven't done all the experiments we need to do to answer that. I mean, I think, for example, if you take carbon, it matters enormously where you put that carbon, right? If your mental model is storing carbon in vegetation, that's not a long-term solution because vegetation turns over. If you're taking the carbon out of the vegetation, and through biomass energy with carbon capture and sequestration or something like that, and then using that to store it under geologic, in geologic sequestration, there's still an opportunity cost, right? That carbon that you're pulling out of the vegetation isn't going into litter pools. It's not going to the soil because you've taken it and now put it into these geologic reservoirs. And so there's going to be some loss of carbon there, right? There are these, if you take carbon out of the ocean, there's probably other sort of, opportunity costs and things that wouldn't have otherwise happened. The result of it. So I think the answer to that question, I think there's a lot of like subtlety in terms of these interactions, and I think the hope is that in the not in CMIP 7 but in a CMIP 8 timeline, we can have these instead of treating carbon dioxide removal as this exogenous process, we specify it as a mechanistic thing. We say, we apply BECCS to X million, hectares, and we apply ocean CDR in this place, using this, and we have, ocean alkalization, et cetera. We put the actual mechanism, and this is starting to happen, but not, I think, in a fully integrated way. And so I would say the European modeling groups are probably ahead of us on doing a lot of these experiments, but it's certainly, I would argue that these are the experiments we need to be doing.
Thanks.
Thanks. I feel like there's some conflation between irreversibility and long memory in the system recently. I like these plots because they kind of sidestep that. But I was wondering, do you expect longer timescales as you are coming back down that curve, particularly coming from ocean memory and heat storage?
Yeah, I mean, basically all these things become out of sync with each other. And I think the desynchronization of like global mean surface temperature and globally integrated precipitation is one example of this, right? Where the different pieces of it all kind of fall out of synchronization with each other. And so, for example, at the point of reaching, cumulative zero emissions, right? You've pulled all the CO2 that had previously been emitted. CO2 concentrations are well below the pre-industrial amounts, but even though the planet is warmer, right? So there'll be a lot like there's basically no time-independent mapping between CO2 concentrations, global mean temperature, and global mean precipitation. All three things are fundamentally fall out of synchronization with each other under any of these things. And so the relationships between them will change. So if you're a plant, you care a lot about CO2 concentrations. You also care a lot about temperature and precipitation. All three of those things will always be changing. And basically, like because we perturb the system to the extent that we already have, there's no stable solution foreseeable at any point in the next several centuries. It's just the system is perturbed. So even if we were to try and reverse it, we might be able to reverse global mean surface temperature change, but we wouldn't. But the set of relation, that climate would not look like the pre-industrial climate, et cetera.
Great. Thank you, Charlie. Let's take your award.
Oh yeah, which is this.
This one, yeah.
Thanks.
Okay, so next up we have, and last before the coffee break, is we have the Graduate Student Award. And so I'm pleased to announce that Genevieve Clow from the University of Colorado is the recipient of the CSM Graduate Student Award. Genevieve. So Genevieve's research has advanced our ability to compare CSM simulations with satellite observations of the ocean, addressing long-standing challenges and understanding how climate variability and change affect marine ecosystems. She developed the chlorophyll observing simulator package with CSM2 and developed innovative approaches to quantify satellite sampling biases and evaluate the detectability of extreme phytoplankton bloom events. Her work has strengthened CSM model evaluation capabilities and provided important insights in the productivity and variability of the ocean. Congratulations, and we'll have pictures afterwards, but and here's your award.
Great,
and
you.
Take it away.
Right. Okay. Hi, everyone. Thank you so much for having me today. I'm really excited to present my work on on development and applications of simulated ocean chlorophyll observations in CESM. So this work was completed while I was a graduate student at the University of Colorado, where I was advised by Nikki Lewandowski and Jen Kay. And we also worked extensively with Mike Levy and Keith Lindsay at NCAR. And so I want to start by thanking them for all of their contributions. And today I'll show how we developed a new tool within CESM that makes the model output look more like our satellite observations, and how this tool can then be used to both improve model evaluation and to better understand observational limitations. Okay, so this work focuses on bridging the gap between how we model and observe marine phytoplankton on a global scale. Phytoplankton are microscopic single-celled organisms that photosynthesize, meaning that they get their energy from sunlight, and this makes them the base of the marine food web. So they're grazed on by zooplankton, which then support higher trophic levels like fish. And phytoplankton also help store carbon in the ocean, playing an important role in Earth's climate. Because phytoplankton are so important, we need to monitor them on a global scale. And one of the primary ways that we do this is through satellite observations of chlorophyll. Chlorophyll is a photosynthetic pigment in phytoplankton that makes the water appear green, and its concentration can be estimated from ocean color measurements. So it is a commonly used proxy for phytoplankton biomass, which is harder to measure directly. And in this talk, I'll focus on observations from Aqua Modis, which has provided a long and relatively stable chlorophyll record since 2002. So this animation is showing monthly chlorophyll from Aqua Modis. The green colors indicate regions with high chlorophyll, such as coastal upwelling regions and the North Pacific spring bloom. But you'll also notice that there are large areas with missing observations shown in gray. And these gaps arise because satellites cannot always observe the ocean surface due to many factors, including clouds, sea ice, or insufficient sunlight. And high latitudes in continuously cloudy regions may experience months at a time without a single observation of chlorophyll. And because missing observations are related to certain environmental states, missing data is not completely random, which can lead to systematic biases over time that affect how we interpret these satellite-derived chlorophyll products. So Earth system models are, of course, another important tool that we have for studying phytoplankton, especially for investigating future climate impacts and the carbon cycle. In CESM, chlorophyll is simulated within MARBLE, the marine biogeochemical component, using 3 phytoplankton functional groups and 1 zooplankton group, which grazes on all of these phytoplankton. And this map is showing the climatological mean of the surface chlorophyll from a hindcast simulation using the ocean model POP2 at 1 degree resolution. So in order to have confidence that our models realistically represent key processes, we first need to validate them using real-world data. And for ocean biogeochemistry, satellite observed chlorophyll is the longest data set that we have for model validation. However, this is not a direct comparison due to the inherent differences between the model and satellite observations. And this introduces some uncertainty in our estimates of model bias. And the 2 differences that I'll focus on today are that models are resolved at all depths, but satellites can only see the surface values of chlorophyll. And models also produce chlorophyll values at every location and time. Therefore, they provide us with true means. But in the real world, satellites only see a snapshot in time each day, and these daily observations are heavily impacted by data gaps. So to address this problem, we developed a new tool in CESM called the Chlorophyll Observation Simulator Package, or CLOSP, which was inspired by COSP, a satellite simulator for clouds. CLOSP samples the model as a satellite would see it, therefore generating a model output that has missing data. And it accounts for cloud cover, sea ice, and high solar zenith angle, all of which prevent satellite detection of chlorophyll. And it takes the surface level model output, which is the mean over the top 10 meters. Additionally, we have implemented a simplified swath that mimics the sampling pattern of the Aqua satellite. And CLOSP has been implemented in both a fully coupled and hindcast simulations of CESM. And so in the fully coupled simulation, CESM uses modeled cloud cover for data masking, whereas in the hindcast simulation, we use real-world observations of clouds from ISCIP. So previously, CESM would produce a daily model output that looked like this top map with values at each location and time. And then later on in the talk, I'll refer to this as like the standard model output. And this standard model output was then compared to our real-world observations. But now with CLOSP, we have a model output that is more similar to what we are able to observe in the real world. And we'll call this the modeled MODIS chlorophyll. So CLOSP enables us to make two new comparisons. First, we can compare the modeled satellite observations to the full field model output to estimate satellite sampling bias. So this sampling bias arises from incomplete observational coverage, where certain conditions of the ocean are more favorable for viewing than others. And in this work, we specifically focus on sampling bias and do not simulate uncertainties associated with the chlorophyll retrieval itself. And second, we can compare the modeled satellite observations to those from the real world to improve estimates of model bias by making a more direct comparison. And so this slide highlights that CLOSP gives us these two new capabilities, both quantifying observational bias and improving estimates of model bias. Okay, so our first application uses CLOSP to improve model validation and better understand the impact of satellite sampling bias. So here I'm going to present chlorophyll results, but we also performed the same analysis for IR-based SST, which is similarly obscured by cloud cover. And if you're interested, you can see the results in this paper. So for this analysis, we ran a hindcast simulation of CESM with CLOSP and analyzed years 2003 to 2016. We quantified satellite sampling bias by comparing the standard modeled chlorophyll to the modeled MODIS chlorophyll, and their percent difference provides an estimate of the sampling bias in the multi-year means. And because missing observations are not random, they introduce these systematic biases in certain regions. So there we go. The model allows us to quantify the contributions of various factors that cause the missing data. And so the overestimates in the high latitude regions arise due to the lack of sunlight and sea ice in the winter, which prevents detection of chlorophyll in the wintertime. So as a result, the annual mean is heavily biased towards the summer months when phytoplankton are very abundant. And then we also see strong underestimate of chlorophyll in the North Pacific, which can be attributed to the strong seasonal cycle of clouds and chlorophyll. So in this region, the peak chlorophyll values occur during a cloudy time of the year. And so then the satellite observations during that time of the year are limited. Okay, so next we highlight the importance of accounting for this sampling bias when comparing the model to real-world observations for model tuning and validation. And so these maps will show the difference between CESM chlorophyll and MODIS chlorophyll averaged over the same time period. Where the map is red, the model is overestimating chlorophyll, and where it's blue, the model is underestimating chlorophyll. And so overall, you can see that chlorophyll concentrations are too high throughout much of the ocean and too low throughout the coastal regions, which is a common feature of Earth system models. And so panel A is showing how model bias was traditionally calculated using the standard model output, where the model is being compared to observations that have sampling gaps. But here in panel B, both datasets have the same sampling characteristics because the model has been sampled using CLOSP. So this makes panel B a more direct comparison to the real world. And panel C shows how accounting for this sampling bias changes the apparent model bias. So it's the difference between panels A and B. In the green regions, the model is performing better than previously thought, whereas in the purple regions, the model is performing worse than we thought. And so a reduction in the apparent model bias suggests that some differences previously attributed to model error were actually caused by sampling bias in the observations, whereas an increase in model bias suggests that the observational sampling was masking the true model error. Okay, so far I've shown how CLOSP improves model evaluation, but once we have a realistic observing system embedded within CESM, we can also use it as a test bed to evaluate our observation systems. And so here we ask, how well do satellites detect daily, large-scale phytoplankton biomass extremes in the open ocean? So since phytoplankton are the base of the marine food web, their variability impacts ecosystem health. And just as marine heat waves can disrupt ecosystems, unusually high or low phytoplankton abundance can also have important ecological consequences. However, we don't know how often these extremes occur or their true ecological impacts because they're very difficult to observe. So because of the data limitations in the real world, we need a modeling testbed to answer the question, how well do satellites successfully detect phytoplankton biomass extremes? And these maps are showing examples of the daily model output that we use. So we have the masked surface chlorophyll or modeled satellite observations from CLOSP, which most closely represents what we would be able to see in the real world. And then we also have the full field standard modeled chlorophyll for comparison. And then we have the vertically integrated phytoplankton biomass, which is the variable that matters most for the ecosystem. And this is because zooplankton graze on phytoplankton throughout the water column, so concentrations below the surface also matter for the ecosystem. And here we're taking the integrated biomass over the top 100 meters, which is approximately the sunlit zone where phytoplankton and zooplankton live. So using these three outputs, we can assess how good of a proxy our observations of surface chlorophyll are for the total phytoplankton biomass in the context of extremes. So to find extremes, we first calculated the day of year climatology using an 11-day window for each variable at every point. So we're looking at local extremes. And here we are looking at the black point on the map just as an example. So the high and low extremes are defined as values above the 10th percentile or below above the 90th percentile or below the 10th percentile. And so the gray shading here represents the range between the high and low thresholds. So anything outside of this envelope is classified as extreme. And for the masked chlorophyll on the bottom from CLOSP, the thresholds are calculated using only the available observations, which changes the envelope due to selective sampling. So we found that satellites miss the vast majority of daily phytoplankton biomass extremes. Globally, only 19% of high and 10% of low phytoplankton biomass extremes are detected by the simulated satellite using surface chlorophyll as a proxy. And so a successful detection occurs when a phytoplankton biomass extreme is also identified as an extreme in the satellite observed chlorophyll. Because we have both the modeled satellite observations and the full field chlorophyll output, we can then separate the causes of these missed detections. And so the top row shows the total percentage of missed extremes, while the next two rows explain why they are missed. And so this middle row here shows missed extremes due to extreme misalignment. And extreme misalignment means that phytoplankton biomass and surface chlorophyll do not become extreme on the same day. So even with a perfect gap-free observing system, these events would still be missed, and they would be incorrectly identified as occurring on a different day. And so misalignment is especially common in strongly stratified regions, and in these areas, phytoplankton often grow deeper in the water column. So surface chlorophyll does not fully reflect the total biomass. In addition, photoacclimation can alter chlorophyll concentrations independently of biomass, so this causes the chlorophyll and phytoplankton extremes to become decoupled. And the bottom row shows the additional contribution of missing observations. So missing observations can only prevent detection when chlorophyll and phytoplankton extremes are already aligned in time. So this decomposition reveals that the dominant causes of missed extremes depends on the region. So in the stratified subtropics, misalignment between chlorophyll and biomass is the primary limitation, whereas at higher latitudes and in persistently cloudy regions, chlorophyll and biomass extremes are often aligned, but missing observations due to clouds prevent detection. So the key takeaway here is that caution should be taken when using satellite chlorophyll to study short-term ecological impacts. Okay, so to conclude, CLOSP allows us to sample CESM the way satellites would observe the real world for ocean chlorophyll, creating a more direct model observation comparison. And accounting for satellite sampling bias improves model evaluation by separating observational limitations from true model error. And using CESM with CLOSP as a testbed, we estimate that satellites detect fewer than 20% of daily phytoplankton biomass extremes. And so together, these results demonstrate that modeling observation systems are important not only for improving model evaluation, but also for understanding what our observations can and cannot tell us about the ocean. So with that, thank you so much. I'm happy to take any questions. Is there-
Thank you, really nice work.
Thank you.
Any questions for Genevieve?
Really nice work, Genevieve, and congratulations.
Thank you.
I was wondering if you could use this framework as a way to extend formal uncertainty quantification for these kind of like higher level satellite products for chlorophyll and other quantities.
Yeah, definitely. Yeah, so far we've just been focusing like on sampling bias and how that impacts like the mean over time. But I think another cool avenue is like looking at integrating like a full like radiative transfer model to see like how, the chlorophyll retrievals themselves are also impacted. Yeah, so I think the model is a really cool test bed for these kinds of things.
Awesome, thank you.
Thank you.
Great, thank you again.
Thank you.
Congratulations. Okay, we're going to move into break. We are a little bit behind schedule. Let's try to come back at 10:45 so we don't lose too much of our lunch. So a bit of a short break here, and I want to get photos with the award recipients, and yeah. Hey Duncan, if you can hear this, people are filtering back in.
Excellent, thank you.
Okay, everyone, can you please come in and take your seats? Okay, so we're going to have now this plenary session before lunch with three great speakers lined up to kind of cover different topics. One is sort of thinking about the future with our modeling and what we can do to make them more powerful, and then we'll get a talk about how we use CSM for impacts and real societal benefit, and then we're going to hear from Gretchen about how we can collaborate with the MPAS team. So Duncan is going to be our first speaker, Duncan Watson-Paris, and Really unfortunately, he was here last week, and he was intending to be here today. He was here at the meeting we had on the hybrid implementation workshop. We had a really good conversation about differentiable modeling, and then he had a family emergency and had to fly home last night. So it's unfortunate, but nonetheless, he's willing to give his talk here remotely. So for those you don't know, Duncan is an assistant professor at Scripps in UC San Diego, where he leads the climate analytics lab. His research focuses on aerosol cloud interactions and the representation of global climate models, combining satellite observations, machine learning, and differentiable modeling to reduce uncertainty in anthropogenic forcing. He's a lead developer of GEM, the first JCM, the first fully differentiable Earth system model, and leads the Gaia initiative at UCSD. So, Duncan, take it away. We're looking forward to your presentation.
Fantastic. Thank you very much, Dave, and thank you to the organizing committee for the invitation. Apologies, I can't be there in person, but I'm delighted to give the talk. I briefly just want to acknowledge the support of NSF for much of this work as well. So the uncertainty to which I allude in this title is the aerosol forcing uncertainty, and many of you in the room will be very familiar with this. But I just briefly want to reiterate its importance for producing accurate projections. So in this paper with Chris Smith a couple of years ago, we looked at the distribution in temperature projections for one particular scenario. So this is SSP 126, for those of you who keep track of these things. So it's a broadly Paris-compatible scenario with a distribution that represents the assessed uncertainty in all of the physical uncertainties in the climate system, including the aerosol forcing, but also cloud sensitivities and other feedback uncertainties. And this scenario is broadly designed to keep us it's a Paris-compatible scenario, so it hopes to get us to 1.5 at the end of the century. But you can see this 95% uncertainty range, and the shaded area represents a fairly large degree of uncertainty in that. And within this ensemble, the aerosol forcing is assessed to be minus 1.2 watts per meter squared, plus or minus about a third of a watt per meter squared, and that's one standard deviation. So what we did in this paper was actually to to ask the question, what improvement would we get in our ability to project future warming if we reduced that uncertainty? So I'm a new faculty and I'm writing a lot of proposals that are motivated by trying to reduce this uncertainty. And I realized there wasn't a great citation I could use to point to, the improvement we would get in our ability to project future warming if we were to reduce this. So we play this hypothetical game where we subsample the distribution in such a way that we reduce this uncertainty. And it turns out that when you do that, the ability to constrain future warming depends on the true value of the underlying forcing. So if we take this original distribution and we subsample it such that we reduce the uncertainty.
Hey, Duncan, I'm sorry. We lost your sound. Give us a minute and we'll get back to you soon.
Okay. Is it my end or yours?
Hey, Duncan, can you try saying something for me?
Testing, testing.
Okay, hold on 1 second. Sorry about that.
No worries.
Okay, Duncan, can you try talking one more time?
Okay, how's this sound?
Perfect. Okay, you're back. Great. So you probably need to go, well, if you can remember, I don't know, we're still on this slide.
Okay.
Yeah.
That's fine. I won't belabor the point. I think all I want to say here really is that, getting the present day aerosol forcing is crucial for attributing the warming we've seen to date, but also for producing accurate projections. Um, Now, of course, a lot of these uncertainties, and this will be familiar to many in the room, stem from the parameterizations that we use to represent aerosol and their interactions with clouds in particular in our models. And this isn't special to aerosol. There are many parameterizations with uncertainties, not least, some of the land processes we've heard about already this morning, but also the ice microphysics and submesoscale mixing in the ocean. But for me, the aerosol is obviously something that I think a lot about scientifically, but it's also a canonical example of the challenge of trying to optimally represent these complex processes. And so that's both coming up with the structural representation and then also calibrating those. And so, one way that the community has been increasingly trying to tackle this problem of calibrating, so making our models look as much like the observed world as possible, is using a perturbed parameter ensemble. And now there are different flavors of this approach, but the one that I have a lot of experience in myself are kind of emulator augmented PPEs. And I would argue are currently kind of probably the state of the art for calibration. And so more or less the idea is you generate a large ensemble of simulations, perhaps 1 or 200 model simulations that span the different parameters that you believe contribute to this uncertainty that you care about. And then you build an emulator over these points such that you can much more densely sample that space and perform inference, whether that's using Monte Carlo sampling or rejection sampling or something else. And there are, as I say, various flavors of this, but the thing they have in common is that they are all expensive. They all require generating this large initial ensemble, and they haven't yet been shown to scale to fully coupled models, which is often the crux of the problem. How do we make the coupled model look like the real world? And indeed, some early efforts to take calibrated atmospheres, some atmospheres that have been calibrated in this way, and couple them to the ocean, have not fared very well. And so maybe there's another way. And over the last 18 months or so, and in our lab, we've been developing the JAX GCM. So JCM for short is a fully differentiable physical atmospheric model written in Python and uses this JAX library, which is a Python library developed by Google for its machine learning work, which provides an auto-differentiable backbone that enables our model, which uses that, to have calibration and sensitivity analysis out of the box. We kind of get that for free, as it were. We've developed it in such a way that the parameterizations are plug and play, so we can experiment and explore not just the parametric uncertainty, but also the structural uncertainty. And because it's built for the machine learning pipelines, it's trivially compatible with both CPUs and GPUs, as well as TPUs, which are Google's proprietary hardware. And we get very, very straightforward scaling with very good throughput on this simple physics. So in this initial configuration, and I'll come on to this more on the second slide, we're using a fairly straightforward physics, but we nevertheless get very, very good throughput for that. And this is validated against the original Fortran baseline. So for 1.0, we targeted the speedy parameterization or set of physics with a spectral die core, which is a little bit clunky, right? It's not the best physics, but it produces a reasonable looking atmosphere and gives us a prototype. It gives us something where we can calculate gradients through something that looks like an atmospheric model and reason about how we might use those gradients for calibration and sensitivity analysis. And I see it as a stepping stone between, kind of Lorentz 96 and the full complexity models that we do with our science. And so this has been in development over the last 18 months or so. The original paper actually has just been accepted in GMD, But we've actually just this week released version 2. So this prototype version that I just described uses the speedy physics with a very simple gray radiation, diagnostic clouds, just 8 layers. But the version 2 I see as very much a kind of science capable version. We have the full ECM6 physics suite. We have a flexible die-core, which I'll talk more about in a minute. So we have the spectral model as well as a spectral element die-core, full RRTM GP radiation, Tiedemann convection, right? Something that actually looks like a climate model, or certainly an atmospheric model. And you can try this out today already. You can just pip install JCM on your laptop or on Casper or Derecho and start playing with that already. I briefly just want to shout out to some work that we've just been doing over the last few days, actually, coupling this latest version, which, as I say, has that flexibility to bring in different dynamical cores. And we've coupled it to this library called Pisces, which was developed by Owen Hughes, and you can find out more about it here. And that is designed to be identical to CAM-SE, so the spectral element discretization in there, and retains those nice conservation properties of that die core. It also has a non-hydrostatic dynamics and is still pure Python, so we can just use NumPy arrays. Actually, it also has support for PyTorch if you rather. And it's fast. So we were doing some quick smoke tests on Derecho the last weekend or so, and we get 3 simulated years per day on the full ECM6 physics at, that should be, 1 degree. That scales pretty nicely as we increase the number of GPUs that we're using. So using a single GPU on there, we can get 3 simulated years per day for this full complexity physics. So I think this is really exciting. It opens up a lot of interesting avenues for how we develop models, how we work with the models. But what about, I see this as a prototype. And so how does this actually help with calibration? There's been some unease or uncertainty in the community, I guess, about how useful gradients might be for calibrating given the chaotic nature of the atmosphere. And so I just want to tease some early results from one of the students I've worked with, Rebecca Genie at UCSD. And here I'm going to show a few plots of this loss function. So this is really just we can ignore this covariance term. This is the difference between some observations and our model predictions for a given set of parameters U and some initial state Z. We turn this into a loss so that we can minimize it, but this is essentially, you can think of this as the difference between the model and our obs. And so the way we're going to set this up is using that speedy physics because it's quick and we can iterate, not because it's necessarily the most realistic. But we have 15 parameters which represent things like stratiform cloud albedo, the maximum entrainment, and some convection thresholds. And we're going to, for the purposes of this demonstration, try and calibrate those against some observable properties of a held-out model simulation. So it's a perfect model test where we calibrate against a known configuration of the model with respect to things that in principle we can go measure. Radiation at the top of the atmosphere, convection, precipitation, and so on. And if we initially, for these purposes, we'll assume we know Z, so we'll ignore that for now. And we can plot that whole loss function. This is a very cheap set of simulations to run because we have, this GPU acceleration and speedy physics. And we can calculate the loss at a whole range of different parameter values. So 0.5 is the true value of cloud albedo. And we see that for a short 3-day simulation, we actually have a very smooth loss function, right? This is something that you would expect to very straightforwardly be able to optimize using any kind of gradient-based method. But as people perhaps anticipate, as we roll these simulations out over longer timescales where the atmospheric trajectories start to diverge, that loss becomes a bit noisier. But as we go to longer timescales and we then average out some of that chaos, we actually return to something that is very smooth. Now, this smoothness, roughness, what I think of as a kind of bias variance trade-off, actually is different for different parameters. So if you pick a parameter like entrainment, which actually feeds back more quickly onto the atmospheric state, then these intermediate times are actually much noisier still. But we retain this property where at short timescales and not long timescales, we get something useful. And actually, even over these short time scales, we can find that the model with the modern optimizers can find the right parameters very quickly and efficiently. So here, there's a lot of information on this slide, so I'll take a minute or two to walk you through it. We're looking at a number of different parameters in our parameterization as calibrated over a number of iterations or epochs. And we're comparing our gradient descent based optimization. So we use the gradients and just do stochastic gradient descent, which is the optimization that powers a lot of machine learning advances, as compared to ensemble Kalman inversion, which is the best kind of ensemble approach that we currently have and is used, for example, in calibrating the Klima model. And we see that the true parameter is in this dashed line because we're just calibrating against a known configuration. And for the parameters for which are informative or are informed by the observations, both approaches converge to the true parameter relatively quickly. There are some parameters which are not constrained by the observations, which is to be expected, and both methods actually broadly capture that spread of uncertainty. But we've shown, and this will be published hopefully over the summer, that this gradient-based approach is at least 4 times faster and more efficient than these EKI-based approaches in terms of the number of years of simulation that you have to do. And so we've started moving on towards using these gradients to calibrate against ERA 5 as a step again towards a kind of real configuration where we're using real observations. Obviously, ERA 5 isn't real observations, but it's a stepping stone in that direction. And we can see that, the model, this gradient-based approach is improving the model with respect to this data. There are some, interesting indications of structural errors. So this particular parameter just seems to want to go to 0. And this speaks to the fact that these gradients don't remove that, right? There will still be structural errors in these models, particularly the simple model that we're using here, but it much more quickly highlights and finds those structural issues. So we're really excited about the opportunities for these approaches for calibration, but actually also for science. So the way we calculate these gradients, we can calculate the gradients of the output of the model with respect to these parameters, which is what I've shown here, but also with respect to the boundary conditions. And much of what we're interested in atmospheric science is exactly that kind of sensitivity, the sensitivity of one of the outputs with respect to some sort of boundary condition. And so here again, I'm just showing some early results showing the sensitivity of, on the left-hand column, convective precipitation with respect to a change in SST around this blob here. This is the large-scale precipitation, and this is 2-meter temperature, just to kind of as a sanity check, if you like, that this is producing sensible sensitivities over different timescales. So each row now represents different timescales. So at half a day, 2 days, and more days. And what I find really exciting is the ability of these sensitivities to probe those transient responses in the atmosphere to, for example, a change in SST, but down the road, perhaps with response to changing, for example, aerosol emissions or other perturbations. And so I find this really exciting. And this, I won't go into the details of it now, but the Jacobian product that is involved in calculating these sensitivities is 1 or 2 lines of Python. It's very straightforward. So I briefly mentioned, the coupled problem, and so we've actually made progress in parallel in building a flexible JAX-based coupler, and so we can couple our atmospheric model here with, in the first instance, a slab ocean model with a start date, with a given time step and set of fluxes, but we also have work to couple to the Viros ocean model and differ land. So we are moving towards a suite of coupled, fully differentiable models, which open up some really exciting opportunities for coupled calibration. And I think this is starting now to kind of move towards this Tapio's vision from this original paper in 2017 of continuous learning of observations and data in high-resolution simulations, which, as originally formulated, I think relies on these ensemble-based approaches, but perhaps with these gradients now can more easily and directly and efficiently find those optima. Now, this raises some interesting questions, because if we can, reliably, quickly, and accurately calibrate our model to the observations, we have opportunities to really improve the model, but perhaps also overfit to them. And this also links to questions and recent developments in machine learning, atmosphere and ocean simulators or emulators, as to how do we know if a model that is built that looks just like the world today is useful as a climate model, or better than an existing climate model, right? What if Google say they've produced a fantastic machine learning climate model that's better than CSM? How do we test that? How do we say whether that might be true or not? And obviously we don't know the truth, but that doesn't mean we don't know anything. And there's a lot of information available in our observations that we can use to assess the likelihood of different outcomes. And so this is a separate project that I've been leading called Climate Bench 2, which tries to formulate this problem and the problem of climate model benchmarking. And in order to kind of make the scope somewhat manageable or reasonable, we define a specific task, which is not, the only task clearly that a climate model is used for, but it's a clear and distinct one, which is that, given a plausible future emissions pathway, what will regional temperature and precipitation changes in 2050 relative to the present day be? And so the way that we've tackled this, and this is a community effort that I've been leading to try and build a consensus around what this might look like. And our current proposal for this is a 3-tiered protocol. So again, thinking about the potential, it's not fully realized yet, but these models are very close. The potential for data-driven models and the potential for them to produce models that look very good in the present day, but are clearly not physical. And so Tier 1 involves a kind of physical entry ticket, a sanity check, if you like, that the models conserve energy, that close water budgets, do things like Arctic amplification, the things that we have a really strong physical basis for. Do they do those correctly? And if they do those, then they can move on to Tier 2, which are your more kind of traditional evaluation and benchmarking against observations. Crucially, we specify a period for holding out data for testing so that we avoid this problem of overfitting to some degree. But then, the elephant in the room is how these models produce or generalize to unseen data. And so Tier 3 involves a set of perfect model tests and paleo experiments to really prove their out of distribution skill. And so, as I say, I hope this starts to formulate a kind of community consensus around what a useful benchmark for climate modeling might look like. And I'm not quite sure where we are on time, but I'd briefly just take a couple of minutes, if I may, just to kind of provide a little bit of outlook on this, because over the course of building this JAX-based model, we've been using a lot of these AI-based models, Claude Code, and particularly for converting Fortran into Python. And we started off, actually, originally we were using ChatGPT, but we were taking, small chunks of code at a time. We were more or less converting specific routines or loops. And, we then hosted a hackathon and it started to grow. But over the last few months, these AI coding models in particular have got so good that actually we can provide pretty much whole parameterizations at a time with a template and just say, go convert this to JAX, make sure it has the gradients, make sure it does physical things. And it will do that pretty reliably with very little supervision. And I kind of did a little bit of an XKCD plot here of just lines that I feel were usefully generated, the number of usefully generated lines of code that I've been able to get out of these models for a single prompt, right? If I say, here's a parameterization that I want, or here's a chunk of Fortran, go make me the lines of code, or make this routine in JCM. And it's increased at a remarkable pace, and the rate of increase is increasing. So this is a logarithmic scale. And I think it's really interesting to think about what this means for model development in general. I think it unlocks a lot of possibilities for a center like NCAR, and maybe, forces us to rethink what it means to be a modeler, right? Maybe that involves a lot less coding and down in the Fortran, optimizing bits of Fortran that we wish we didn't have to. and more time building models that are just the right level of fidelity for the question that we have in mind. And so I kind of iterated with one of these AI tools to try and build a vision for what this might look like. But I think data is going to be an even more important source as these tools become useful and as we have these differentiable models. I haven't really talked about hybrid models, but these suddenly become much more appealing once we can just drop them in to our JAX-based model, and we can optimize those and train them online through the model. And there's a whole other talk on AI. As I say, I'm not quite sure how we're doing on time. I'll leave the summary up here. Again, apologies, I can't be there in person. If if this has sparked any interest, if you're interested in joining any of these collaborations or projects, please feel free to just drop me an email. I'd love to chat. Otherwise, I will leave a bit of time for questions. Thank you very much.
Thanks, Duncan, and thanks for coping with our technical difficulties. You did a great job. Any questions for Duncan on his vision? Jesse.
Hi, Duncan. Great talk. It was really interesting. I'm kind of curious if I'm a software engineer, so I'm kind of curious of your last point about using AI code generation, because it kind of impacted us. Because you talked about originally you were doing like small loops at a time or small chunks. And obviously it takes a while, but you can imagine the advantage is a human can look at that small chunk and look at the original chunk and go, that's the same. But if you do like a big parameterization, it becomes harder and harder for a human to be in the loop, basically, in terms of the code. So how has your team tackled that? I'm just curious what your thoughts are on that. And are you doing anything about it? Are you just kind of accepting it? Are you writing tests? Yeah, anything would be great.
Yeah, absolutely. No, great question. Thank you, Jesse. So I think it's definitely changed the way we work. So actually, to your point about tests, it's great for writing tests because it's so boring writing tests, and this gives us a framework we can be like, okay, test this, test that, all the edge cases, and documentation. But in terms of the core science code where the accuracy is so crucial, it's interesting. So the last generation of models, so like Opus, it makes human kind of mistakes. It makes the kind of mistakes I would make. Like occasionally it'll do an off by one, or it'll index in the wrong direction. Those are quite hard to catch. So I make a point of reading and reviewing every PR that these tools make. And that's a different mindset, right? You suddenly spend a lot more time reading code than writing code. And it's quite hard to pick those up. But I think that's also true of the existing development process. I had a brief go with Fable before it was swiftly removed, and that was pretty remarkable. Like that produced, as far as I could tell, pretty flawless code straight off the bat. So I'm wary to make predictions, but I think it really will be a shift in the way we develop and the way we move. And again, it's not perfect. This is an iterative process, but I think it just speeds up that iteration.
Thanks.
Yeah, we'll take one more. Judith?
Thank you very much. I might have misunderstood, but yeah, thanks for the talk. It was great. I have a question. Are you saying that your cost function is the same if you optimize for 3 days and 30 years? And I'm really getting to this question is, if we optimize a parameter for climate, it might be very different than if we optimize it for weather. And are you really getting the same optimal parameter? Thank you.
Great question. Thank you very much. Yeah, I glossed over a fair amount here in the interest of time. For some parameters, so for example, for the cloud albedo, the optima, if you like, over a short window is actually the same as over the climatology, if you like. But you're absolutely right. It's not necessarily the case that for a given parameter, the steady state climatological impact or true value will be as for the short term. And you can start to see this a little bit in the entrainment here. This is slightly actually off center. What we've been exploring is actually doing windows. So we do short windows. So the cost, again, I kind of glossed over this, but practically we can't calculate the gradients through this model for 30 years and then all the way back again. It's computationally too expensive. So what we've been doing is taking windows of a week at a time, or 1 or 2 weeks, over a 30-year period and doing batching very similar to the way that you would do batch gradient descent for a neural network. And we find that as I briefly showed on the other slide, converges to the true long-term optima for the experiments that we've tried. But I'd love to chat more offline if you have interest.
Great. Thank you very much, Duncan. Excellent talk. Very thought-provoking. Okay, so now we'd like to welcome James Dunn up to give the second plenary presentation. So James, come on up. Yeah, so James leads the Weather Extremes Across Scales research section within NSF NCAR's M3 Mesoscale Microscale Meteorology Laboratory. He does a lot of work partnering with risk managers to advance fundamental understanding of hazards in a changing climate while ensuring that new insights are usable in risk management decision-making. He currently serves on a National Academies Committee on attribution of extreme weather and climate events and their impacts, and we're looking forward to his presentation about how we can use our system models to help understand risk.
Great. Good morning, everyone. Yeah, happy to be here, and I'm excited to talk about how we can advance our science to support risk management, climate risk management. So before I start, I just want to go over a couple of definitions. So when I say hazard, I'm talking about the weather event, say the hurricane or the severe local storm. And when I say risk, I'm talking about the consequences. So of course, consequences are a combination of the hazard with what's in harm's way and how it responds to the hazard. And a lot of what I'm going to talk about today is from my own experience working with financial risk. Okay. So in financial risk management, one of the key tools of risk transfer is insurance. And currently the insurance industry is facing a crisis of affordability. So here's a map showing a recent increase in homeowners insurance premiums, and you can see it's going up everywhere. And I know this personally because my homeowners insurance in Longmont, just down the road, recently doubled, apparently due to hail risk. So I want to know what data they use for that. But of course, the prices are going up because of market forces and inflation, but also we have a climate change contribution. So hurricanes are now more intense than they once were. Recent years, we've seen record hail losses approaching, say, $100 billion a year. And mostly over in the western US, we've got burn areas that are expanding, and the rate of expansion is increasing. So we think of climate change as a compounding factor that's rising this, or contributing to this crisis of affordability. So when we think about homeowners, their climate risk is direct damage to their homes. So what's the climate risk to insurers? It's kind of indirect, and it's actually model risk. So it's the risk of using bad models to make decisions. So hopefully this sounds familiar, because you know, as climate scientists, we are also exposed to model risk, making scientific discoveries based on perhaps questionable models. So there's a key point of collaboration to reduce our model risk. So let's just review where we're at in terms of how close we are in terms of talking to each other. So here I'm going to outline what most of you will be familiar with, the scientist paradigm for how we tell stories about weather in a changing climate. So here's a figure from the Banner Mesoclip paper by Chang et al. This figure here shows the future increase in annual maximum rain rate. So green everywhere, no surprise, annual maximum rain rates are increasing almost everywhere. Now let's just analyze this figure. A number of choices were made in terms of how that figure was produced. It was built around a specific climate forcing scenario, one of many choices. This is the future change to the end of the century. The time horizon is also rather arbitrary. There was a choice made to analyze annual maximum precipitation, and then there's a choice about the significance. So here stippling is where the majority of the ensemble members agree on the sign of the change. So why were these choices made? We can discuss that at the break, but it turns out many of these choices make or break whether this information is usable for risk management. So now let's look on the other side. Here's the climate risk manager paradigm of how they tell stories about objectives in a changing climate. So I'm talking about, say, for an insurance company, it could be profitability. For an emergency manager, it could be reduction in fatalities or improved livelihoods. So they identify undesirable outcomes, and often they set an impact threshold and track the probability of exceeding that threshold through time. So that's depicted on the figure here. So we've got time going forwards from today, and on the y-axis is likelihood of a bad outcome. And risk managers often have some kind of risk tolerance, and they can track it every year. And when they see the risk level exceeding or poking up into the unacceptable risk, they can take an adaptation decision earlier in time to prevent their exposure. So clearly our climate science can inform this kind of risk manager paradigm, but when we were just talking about the scientist paradigm, it said nothing about bad outcomes. So if we want to deliver usable information, then we need to blend these two modes of storytelling. Okay, so Abby J and I in M-Cubed, we conducted a listening exercise where we interviewed 10 experts in the insurance, reinsurance, regulatory industry to understand what climate information they're using, why they don't use certain data sets, and generally what their frustrations are with the current state of a system science. And I need to preface all this by, we all need to understand that catastrophe models are the language of financial risk management. And more, these catastrophe models are using across many different sectors. So some of you will be familiar. I'll give a 30-second overview. So they start with a weather event set. Could be a collection of US hurricanes. Then they have exposure. This could be the map of insured properties. And then they have an impact function or a vulnerability function that says how the exposure responds to the collection of hurricanes in this case. Whoops. And then there's various financial modules, and it spits out a loss curve. So a loss exceedance curve that tells them the likelihood of a loss within, say, a 12-month period. So much like our GCMs, these models are decades in the making. They're highly decision relevant. They talk in terms of loss. So unlike CESM, which talks in terms of weather and climate, which I would argue is more indirectly relevant, and they're rapidly evolving now to account for climate change. So historically, they weren't built to include climate change, but now versions are coming out. Companies are putting out model versions that include climate change. And I've highlighted this word recent because these models are not forwards-looking. In a way, you could call them backwards-looking. They want to account for the climate change that's already happened and get the best estimate of current climate risk. Okay, so if we want to be relevant, we have to speak in terms of the language of these catastrophe models. So here's some other findings from our interview study. So we're off to a good start. Public research is universally trusted source of information. So we're on a bedrock of trust. As I say, the key time horizon is next year. It's not the end of the century. Financial risk managers are interested in the end of the century, but more for regulatory compliance. For pricing, it's all about this year and next year. So the key information need is the frequency and intensity of events. So it's not maps of 99th percentile exceedance of wind or precipitation, for example. And it's tail events, the events that cause losses. And they want to understand trends in these events. They don't want surprises, so they want to understand the full distribution of anything the current climate can throw at them. We also learned that passing peer review is far from being usable. So peer review may be one criteria, but being usable, the information has to be understood, it has to be rigorously transparent with full uncertainty quantification, and it needs to be unbiased. That's a whole other talk I could go into. And then time for some humility. They thought there was a lack of reciprocity from climate scientists or lack of interest in how science is applied for risk management. They felt they're very interested in climate science. They didn't see much interest from the scientists of how the science is applied. So, okay, well, sorry for the cross out, but let's consider these dimensions of the climate drivers of climate risk. So we'll start with spatial scale. So we know CESM is most confident on global and now down to some regional scales. It's less confident on local scales, whereas that's what drives a lot of climate risk, particularly if they want to interact the climate data with local exposure. And apologies for the formatting here, but let's think about intensity. So of course, CESM is most confident in terms of the mean intensities, less confident in the extremes, which is what's driving most of the climate risk. And then finally, time horizon. So again, we have most of our experience has been at understanding past climates and future climates, say end of century. There's been less emphasis on present climate. However, I do want to give a shout out to Andrew Gettelman's paper recently with Claudia Tibaldi and Ruby Long on climate nowcasting, which is directly tackling this current climate capacity gap. So a lot of my work then has been extrapolating from where those green regions were, where we're most confident, into the red regions, which is our science gaps. And I just wanted to present 3 slides of current work I'm doing with various reinsurance companies, just to give you a sense of how I'm connecting CESM with insurance needs. Before I jump into that, just a quick overview of how I interact and maybe why I partner with insurance companies. So here's the 4 main companies I've been working with. These are global insurance and reinsurance and financial advisory firms, and you can see they've been long-term partnerships. So clearly they get value from partnering long-term with public science. I like to partner with them because they make me think of fundamental science differently. I come up with new science questions that I wouldn't have come up with alone. So we co-develop the science questions from the outset. I get my science in the peer-reviewed literature. I publish data sets, public data sets that they download and use for internal modeling. I think this is the most important outcome of the partnership is understanding of each other. So, I mean, it's not just me. Many of us work with risk managers, and this deep understanding of the application, I think, is rather untapped and could go a long way to informing CESM model development. However, it's not all a bed of roses. There's some limitations here. The projects are rather ad hoc, and you could call them fleeting, and they're exposed to market forces. And they're also short-term units. So companies require a deliverable, say, on a 12-month cadence. So they wouldn't fund, say, core CESM development, which operates on a much longer timescale. So I think there's an opportunity here for a much greater coordination across timescales of the application and the model development. Okay, so I promised 3 quick slides showcasing some of my projects with these companies. The first one is with WTW, the large financial risk advisory. So they conducted an internal study using one of their catastrophe models where they found that changes in the variability of North Atlantic hurricane numbers really drives up their tail risk, a lot more than changes in the mean. So they conducted 2 experiments. They added 20% more Category 5 hurricane model, and they did it in 2 ways. One, they just added it randomly to every year, and another, they only added the extra storms to already active years. So in purple, they increased the variability. So here you're looking at percent change in loss versus rarity of the event. So the gray is just an increase in the mean numbers of Cat 5s, whereas the purple is increasing the variability of Cat 5s. And it's the variability that's really driving up their tail risk. So we just started a project looking at the historical record of North Atlantic tropical cyclones, and here's a time series of annual counts in the observations over the past 50 years or so, and the annual numbers have indeed become more volatile. And then if we look at an equivalent figure in mesoclip, and thanks to Dan Fu for the TC tracks, we're looking at a longer time series here, but the shaded region is the period of overlap between the two figures. We see rather different behavior. But it's still useful information. It's two lines of evidence, and we're merging these two lines of evidence to get to better interpret historical loss experience. And that's an ongoing project. A second highlight is with Insurance Australia Group, the largest insurance company in Australia. We're also using mesoclip, and thanks again to Dan Fu for the TC tracks, where we're trying to better understand climate risk over New Zealand. There's been some very intense events over the North Island, flash flood events, Cyclone Gabrielle. They really want to pin the tail on those events. How much worse could those events have been? And so we're using mesoclip to expand our sample size beyond the observations. You know, there's not many cyclones of tropical origin that impact New Zealand, but there are in mesoclip. So we're looking at changes in the intensity and frequency of these events. And the nice thing about mesoclip, we're at TC resolving resolution now, so we can look at structural changes and how that impacts losses. And final slide, final example is with QBE, a global insurer who has commercial exposure to large hail across the US. They wanted to understand basically a spatial map of current climate, today's climatology of large hail. So we developed a machine learning model based on observations of large hail and applied it to Lens 2 and now also mesoclip. And of course we get the hail alley. And mesoclip is nice because we can understand variability within the year and also spatial hail footprints. So we're looking at spatial dependencies within current climate. Okay, well, you might notice that those projects, I'm really using existing data sets, and you might argue it's kind of a passive use of CESM. So I just wanted to finish with some thoughts about how we can scale our impact and scale the integration of the application into CESM development. Now, I thought quite a bit about this, because how do you scale science that is usable? There's a really nice handbook here by Ned Horton from the Australian government agency. He put out this last month, this handbook on climate risk assessment, a handbook for climate scientists. So if you're interested in this topic, I highly recommend you take a look at this. A key point that they made was you can't know in advance what hazard thresholds are going to be important for loss. So there's no one-to-one mapping between, say, precipitation or wind speed and losses, because it depends on the exposure and the vulnerability and the policy and the market, the state of the market. And one solution, obviously, is to work together and figure out what hazard information is useful for their decision, but it's not a scalable solution. So I'm going to take us back to these dimensions and got messed up again, but in terms of public science in places like NCAR, I think we can really coordinate around these scales that matter for impact and losses. So this means understanding tail events within your city, your location in the current climate. And I like to ask this question. I think this is a key question, a key societal question we can rally around that speaks to these scale gaps. How bad can the weather get this year? It's not a question we often ask ourselves in climate science, and I'm not sure we have the data sets to answer it yet. So just to illustrate the point, here's last Thursday's severe weather reports in the greater Chicago area. Was this as bad as it could have got on that day? Or could the tornadoes have gone through downtown Chicago? And is there another event coming up next month that could be worse than this? So what sets the ceiling on these kinds of events? You know, what Earth system processes set the ceiling, and how much worse could it have gotten? So this is a key question that is tackling extreme weather at local scales in the current climate. And I think there's novel ways we can be more creative with the way we design our ensembles and modeling systems to really target these kind of questions. And there's some cool science we can do along the way. Okay, well, before I summarize on the next slide, I wanted to give a quick shout out to a session I'm co-leading here tomorrow afternoon. It's the cross-working group session on storytelling. So at the beginning of my remarks, I mentioned about these two paradigms between the climate science and the risk managers telling stories about climate change. So this session, we're going to challenge ourselves to create narratives of our science that open up conduits for collaboration across disciplines and collaboration with societal communities. So we've got a great set of talks and a breakout session as well tomorrow afternoon. Okay, well, let me wrap up then. So I think it's our shared exposure to model risk that brings us together and necessitates partnerships. Model risk for the scientists, the risk of science being based on poor models, and decisions being based on poor modeling. And partnering forces scientific creativity. So I was pleased to see Dave's vision for a more agile CESM developmental system, and that's what I'm talking about here. So being more agile, being more creative in how CESM looks, maintaining rigor, but also being rather pragmatic. So pragmatism is not something as scientists talk much about, but I think we can be rigorous and pragmatic in order to deliver usable information in this urgent time for climate adaptation. And then to be usable, many of us are already working at these scales, but I'd like to see a renewed emphasis and coordination of our science at the scales that drive climate risk. And if you're interested in learning more, we just had a special issue on understanding catastrophic risk in a changing climate that integrates GCMs and CAT models in environmental research climate. And I'll leave it there. Yeah, thank you very much.
Questions for James?
Hi, thanks, James. What are the steps involved in going from physical model information to these insurance company estimates of loss? Are their models open source? I mean, are they proprietary?
Yes. So these catastrophe models, yes, they're proprietary. These catastrophe modeling companies have built these models over decades. They have teams of PhD climate scientists developing them. You can have an idea what's inside them, but you can't look inside them. It's proprietary information, but there's been a big push recently at the federal level for a public option that basically produces a public equivalent of what comes out of a catastrophe model. Yeah, and the reason they're interested in NCAR is providing an alternative view of hazards in a changing climate that then they can go back to their workhorse catastrophe models and ask questions. Do you contain this information that NCAR is seeing? And yeah.
Thanks.
Really great. Can you tell us anything about like interactions or responsiveness for city planners, people who get the money from the insurance companies and then have to decide, do we need to press ceilings on how regulations or how strong we make the next piece of wall?
That was it. Okay. Time's up.
So, yeah, what about people who are rebuilding after this?
Yeah, I haven't worked directly with city planners, and often they have to use public information, which is less about the catastrophe models, and which is why there's another need for a public option that would help people who can't afford to pay for these catastrophe models. Yeah, and a lot of what I said today about needing to understand current risk, of course, for city planners, they are forward-looking and need to build infrastructure for the future climate, not today's climate. So it's a rather different question, and I guess speaks to the utility of CESM more broadly. Mm-hmm.
Just quickly, the question I have is, you're only looking 1 year out when you do these kind of insurance policy types of things, and it may be that when you're only looking 1 year out, the climate model information is not that helpful relative to the historical record. And I'm wondering, has anyone done a study that demonstrates the value of using an ensemble of model simulations kind of as a way of getting around, non-stationarity? Because I think it would be very helpful to demonstrate the value of the modeling approach.
Yeah, exactly. Yeah. Yeah, there is a US Clever working group that I'm a member of who's asking these kind of questions and trying to formulate experiments to demonstrate the value of this kind of information for current climate. So, yeah, exactly. Nothing yet. And I think, there's a workshop next week asking these kind of questions.
Thank you, James. Okay, so our last speaker before lunch is Gretchen Mullendor, who's the director of the M-Cube laboratory here at NCAR, and invited her today to talk to us about MPAS. And so sort of the rationale here, one of my rationales at least, is that we are in at least an uncertain funding environment, potentially constrained in the future. And one of the things we need to do is continue to find ways to become more efficient. And the second motivation is that we've seen just here the talk from James about the important intersections between weather and climate and how it impacts society. And so, since Gretchen is leading the weather lab and we're the climate-oriented lab, I figure one of our pathways towards increasing efficiency, increasing this weather-climate interface kind of research is to at the very least understand what each other are doing. And so Gretchen is speaking here to tell us about MPAS activities. I'm going to go down to the MPAS workshop next week and talk to them about CSM activities. So I'm looking forward to that. So Gretchen.
Yeah, thanks very much, Dave. And I have more material already than I'm going to have time to present because I'm not going to hold us up from lunch. I understand my role is to get us out of here so we can all have lunch. So I'll say up front what I think is the most important thing, and I hope everybody hears this, which is we don't have a weather-climate interface. We have a weather-climate continuum, and we all sit at different times at different spots along that as we do our research. And there is no innovation on the weather timescales without innovation at the climate timescales and vice versa. So we are all one team, right? And let's make that clear to anyone that asks. Okay. All right, so I'm going to be talking today about MPAS, which, if you haven't heard about it, is the model for prediction across scales. It's the next generation community model system really built for the weather scales. It can operate standalone, both global or regionally, and it's also integrated within the CSM already as part of a connection to CAM, but I also have some new connections, which I'll do a teaser for later in this talk about actually being another DICOR that will be accessible in the CSM framework, which is also exciting. It's applicable from regional cloud scale to global climate applications, but we're just testing that space out. And we also have the exciting news as of January that NOAA is adopting MPAS for the next decade of research and operations for their modeling moonshot, which means by 2030, global runs at convective scale for forecasting. I see some representatives from NOAA in the audience that we're not sure how we're going to get there, but it's a good moonshot to have. It's a moonshot. So, but we're excited to be part of that team. So what's been going on with MPAS? MPAS actually was begun development over a decade ago, but it's only more recently that it's really become seen this increase in capabilities and features, and it's a really important partnership with the academic community as well as many other partners. So our operational entity testing and adoption includes Weather Company, NOAA, the U.S. Air Force, some international partners that are all operational. So we are just like CGD, we are not operational because we are at NCAR. NCAR is about the innovation that happens upstream from operations, but it's very useful to partner with operational entities, the same as partnering with application entities, as James was just talking about in the last talk. It really helps inform where our priorities are. And we've seen a real big uptick recently in community use and support requests And so we're excited to see all that happening. So I'm going to just give a brief potpourri of some work going on with MPAS, and I picked out some projects that I thought might be of interest to this community. One of them is SPAT work that's happening. So SPAT, if you haven't heard about it, is the NCAR Earth system for predictability across timescales. And so we have finished some uniform mesh runs at 60 kilometer and 100 kilometer. These are atmosphere only with a prescribed SST. And then we are currently working on some regional refinement. So you can see the pictures in the lower right-hand corner that these are how we can do global runs, but with regional refinement. That's sort of one of the next-gen aspects of MPAS is these really flexible regional refinement meshes due to its architecture. So we have the group here. So these slides were provided by AMWG, which is collaboration with a bigger team. There was an anomaly correlation coefficient completed. So what you see on the left is for weeks 1 and 2 in the first column, then weeks 3, 4, weeks 5, 6 in the next 2 columns. And the models listed are going by row, CSM2, CAM6, MPAS at 60 kilometers, and MPAS at 120 kilometers. And again, there was prescribed SSTs for MPAS and CAM6, where CSM2 had a fully coupled ocean model. So these are not apples-to-apples comparisons by any degree. The MPAS runs were 60 and 120 and 1 degree for CSM2 and CAM6. And in the lower right-hand corner, you see the results. And yeah, we, of course, folks from the MPAS team are very excited to see MPAS at 60 kilometers leading with scores. Those are red. But really, the scores are not that different. I think the big takeaway here is an ACC over 0.6, which is what we see in weeks 1 and 2 for sort of, this is the subseasonal prediction space. It's really short-term prediction in that space. And we're seeing skill there, but really still struggling to get skills out into the subseasonal space, which is weeks 3 through 6. And it's more just what can we learn from each other. That's the takeaway I see here, right? We're bringing more perspectives into the space, and we want to see what can be learned from these different approaches. There's also other work going on, additional S2S work going on, and this one more focused on the land modeling system, NOAA-MP. And thanks to Jay Zhang for providing this slide. But this is where another approach to looking at S2S skill or the subseasonal to seasonal skill is to look at specific extreme events, right? So if we have the capability to have a more resolution of specific events we can run regionally, and we see that just don't need to read everything here, but these 3 plots on the left are the 2021 cold air outbreak, which really affected the central U.S., in the south in particular, the 2021 Pacific Northwest heat wave, and the 2015 extreme rainfall. So it's an older Texas extreme rainfall. And the results are variable, but there is some skill that we're seeing that we're excited about. And for instance, the Pacific Northwest heat wave, there was actually good days 11 through 17. There was increased fidelity, and again, some skill across all of these, which was great to see. So this is another thing that we want to do in this subseasonal workspace, is to look at specific extremes and how well we're able to capture those cases and look to see what we can learn looking across different modeling systems. Also, I wanted to highlight some work that we've done here at NCAR with actually doing some forecasts runs globally at convective resolving. So this particular case that you're seeing was a 3-kilometer MPAS forecast. The forecast was a 2.5 day, just 60-hour forecast, but initialized from GFS initial conditions. So that's the NOAA GFS. It's their global model that has data assimilation going on. So we just initialized off of that a deterministic, a single run, just to sort of proof of concept run, and this was done for the month of May. It was included in the NOAA hazardous weather test bed and did decently, but we're really more interested about And again, thanks to Craig for this plot. But we're really interested to see how performance is going on across the globe. This is an interesting thing on the weather climate continuum, that the weather side, it used to more traditionally be that everybody's running their own models, but now they're getting more and more expensive as weather scale forecasting is going to global and high resolution, and so we're looking to have community test beds for that. There was another run that was done similar to this one, September of last year, to look at hurricane season. Both of these runs are available to share with the community. If anybody's interested in looking at them, we can get you hooked up with that. But we'd actually like to run a whole year of these to have a research test bed for global convective resolving with an ensemble, like a 5-member ensemble, but it's computationally expensive. So that would be about 25 million core hours per month to get those forecasts done. A small ensemble daily, I do think it would be really valuable, but also if anyone has any ideas on that front, we're ready to go and just looking for the space to run that and some partners to run that with to make sure we have the right scientific hypotheses and we really are working. So John Petch and I have talked a lot with the teams working on global kilometer scale. We want to have this test bed have hypotheses that range across the weather and climate continuum. I think we can be testing both in this test bed, and that's very exciting. All right, so this is a teaser for a talk that Dan Amrine will be giving tomorrow afternoon. If Dan's out there, thank you for the slide, and thanks to this whole team, and congratulations to his team for this really exciting work. This is actually running MPAS in the CESM framework, so it's coupled to MOM6. It's right now really lightly coupled, but we have a new OPSICAP for MPAS-A. We're doing this Caribbean Hurricane Michael test, and you can, again, congrats this whole team. This is really exciting to see, and let's see if this next one runs. So this is even a better plot of it, and so on the left you see the wind speed and sea level pressure in the middle of the winds, and on the right the SST, and you can see that wake of the SST as this hurricane goes over. So this is really exciting. This really is MPAS in CSM, and we're excited to move this work forward. Again, see Dan and Ben and others and their talk tomorrow for more information. All right, I'm going to wrap up here. We'll just talk a couple slides about the MPAS program here at NCAR, which is across the institution. It's not just MQ. This is lots of folks. Really, what I want to just show you here is that we do have a whole catalog that lists to our best ability all the projects going on at NCAR, which are lots of stuff. You can see in these like sort of teal, green. We have ChemPass, the DICOR itself. We're bringing in NOAA physics, the ocean coupling, MPAS hydro, lots of exciting work going on. How that works is we have a developer committee with key developer partners on there to make sure there's good communication going on, because really MPAS is a distributed model, which is something else I want to just mention briefly. So I'm not going to read this whole slide because I'm running out of time. But it's very different than WRF. If you ever heard of WRF, it was also very distributed, but it meant all the updates still came in through NCAR, like we were the gatekeeper. Now we're really going distributed with repositories sitting at other institutions and bringing in those capabilities. So that's truly distributed. That really is more efficient in how fast we can get the capabilities in. But it does mean that we have to have a new paradigm set up where we're very clear about developer guidelines, and so that's something we're working on. And it's something that we're talking to CSM about and how we want to do that and be distributed. So as CSM and MPAS are using capabilities from each other, how do we make that happen without having two separate repositories? I just mentioned the catalog because I'm going to mention it in my conclusions, but it's really currently not available to the public. It's available to everybody internally. We're looking to make it more public, so for now, I'm just giving you a heads up. There's a full catalog of all our projects and points of contact, and it is something we're willing to share with developer partners, so just let me know if you're interested in learning more, and we are working to make that publicly available on our website. And then I'll just say, I'm excited to have you all involved. So if you, as I said already, if you would like access to our development catalog, please just let me know. And also, if you have any ideas or questions on improving and growing the NCAR MPAS program and alongside the CSM program, that's very exciting for me to hear about. Some upcoming events, I'm just going to leave here, and thank you very much for your time. Everybody's ready for lunch?
Yeah, ready for lunch.
Oh.
Yep. No, because people online. Can you come up? Because people online. Yep.
One of the original concepts of MPAS was to have higher order numerics, extra velocity vectors, with the idea that the effective resolution would go higher and basically compensate or even be beneficial relative to the costs. That was not originally, say, 10 years ago, realized. Has that been realized now?
So
does it get full to the Nyquist? Very good. That's my question. Does it really handle that?
We are seeing better effective resolution because of the way the numerics work than, say, if you have WRF running at 3 kilometers and you have MPAS running at 3 kilometers. We're getting better effective resolution with MPAS. But that's been shown more through operational testing. So NOAA's been looking at that for efficiencies.
Great. Thank you, Gretchen, and thanks to all of our plenary speakers and the award winners earlier this morning. So that ends our session. So we're going to have lunch now, but before lunch, well, two things. One, we're going to try to take a photo. So I want everyone to file out and just look up that way. We don't want to make a big deal of it, but let's get a photo. And then after lunch, be back for the sessions need to start kind of on time because we've got a lot of online, offline speakers or online and in-person speakers going. So we need to try to start on time at 1 o'clock. So it should be a grab and go lunch, fairly straightforward, and you can go eat outside or there's a cafeteria upstairs. So let's go get a photo, and thanks a lot.
Hello, 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 hello. Let's get going here. My name is Peter Lauritsen. I'm currently serving as the internal AMWG co-chair at NCAR. And on behalf of my other co-chairs, so Kevin Reed and Hu Ivan, and our liaison, Cecile Henne, we would like to welcome you to this year's edition of the MWG. You probably already spotted my English mistake here. That's because I didn't know if I should say term ending in 2026 or saying term ending with CAM 7. Hopefully they'll both be true. So I ended up with this incomprehensible sentence here. In case you're not involved or keeping track of what's going on, we are hopefully ready with version 7 of CAM, and here's just a very brief overview of what's new in the model. We have a new vertical grid, both in terms of increasing the boundary layer resolution, but also moving the top up and having a well-resolved stratosphere. So the top is now at 80 kilometers instead of 40-ish kilometers. After a long time, we've changed the workhorse dynamical core to the spectral element C-SLAM dynamical core. It's defined on a cube sphere grid, as you see here. And then we've also made the argument that with this higher order Galerkin method that we should run physics in a different grid than the dynamics. The dynamics runs on this quadrature type grid, and we made arguments we should run it on this grid here. That was work done a long time ago with DOE funding and NSF base, and DOE has since adopted that in their modeling systems as well. So we have a lot of different grids floating around here that may confuse some people, but what actually matters when you're looking at output is this finite volume type grid where all the variables live on in terms of what the user sees. We've had important updates to microphysics that have had impact on our climate sensitivity. The boundary layer and shallow convection scheme has been updated. That's the club scheme. We have a new radiation code base, the RGMG P code base. We also had to do some changes near the top of the model because our GMGP is not valid above 70-ish kilometers, so we're blending in non-LTE radiation as well. We have new sources of gravity waves that we call moving mountains. There's a new gustiness parameterization, and then we've been fixing many bugs along the way. So here's a schematic I also shown last year, just showing in each column here what the different or the major schemes in the model have been since CAM 4, 5, and 6, and now CAM 7. I won't go through the details here. But I do want to highlight here, there's been a lot of stuff happening in the dynamical core world. So as I mentioned, we switched the workhorse to SEC-SLAM. We're importing the MPAS dynamical core as an external, so it's always in sync with the MPAS A group's version of the dynamical core, and we are both looking at it at 1 degree, but also at, what should I call it, weather resolution. So we're doing diamond simulations at the kilometer scale. So Adam Harrington is going to give a presentation on that. One thing I do want to highlight is that it was very important to use the CLOP MF scheme, which loosely speaking is unifying deep and shallow convection, and that really improved our simulations at that scale. We also turned gravity waves off at that resolution and did some parameter changes in PUMAs. Speaking of kilometer scale, we also have a project called Storm Speed that Cristiano Diablonowski will talk about during this meeting. We're basically bringing in the non-isostatic dynamical core that DOE is using. So we're also getting the capabilities of running both on CPUs and GPUs, and in this case here, it's using the C++ Cocos approach to GPUs. So what have been going on this past year here, it's basically tuning. Most of our tuning has been done in couple simulations because we have frequently found that certain tunings in AMIB do not carry over to the couple simulations, so predominantly we've been tuning in that setup. Business as usual is hand tuning, so basically experts knowing what parameters to tweak to get a change the simulation in a certain way, but we've also been exploring automated tuning approaches. There's the perturb parameter ensemble that Dave talked about this morning. We've mostly been deploying that in AMIB mode with the LEAP project. And then we've also been exploring Vince Larson's quad tune approach. And the new thing here that was actually also deployed in coupled model setup and actually helped us get to the parameter tunings that we are using right now for CESM3. So during this summer meeting, I tried to keep my talking and the NCARS group model developer talking to a minimum and let the community speak. Usually at the winter working groups, if you want to attend those, that's where all the modelers give extensive overviews of all the model developments that's going on. So with that, I can take a quick question, but with that, I'll go on to letting the community speak. So are there any quick questions before we move on? Good. But let's move on. And if my memory is correct, it's Thomas Toniazzo who is up next, who is speaking remotely from Norway.
Yeah, hello. That's me.
Is it Timothy? Oh, apologies.
Yeah, I thought so.
Yes, I'll give the mic over to Timothy. How do I change the... So you push here to point, and then forward with this one.
Not very well, I don't think, sorry. Do you want me just to go off this? Or? Yeah, that should do the job. Cool. All right. Yeah, my name's Tim Andrews. I'm currently at the University of Michigan, and this is work done with Christiana Jablanowski, Owen Hughes, a PhD student in our group, and Thomas Bendel from the UK Met Office. So I'm going to be describing a new test case from DCMIP 2025. So what is DCMIP? So this stands for Dynamical Core Model Intercomparison Project, and this is something that's been held 4 times where we gather students, and there's a bunch of lectures for these students about dynamical cores and atmospheric modeling. And at the same time, we take a bunch of dynamical cores and test them using new test cases. And so I'll be describing a new test case I helped make for the DCMIP we had last year, which was in fact the week before CESM 2025. So this new test case is a simple initial condition, which is used to look at mesoscale dynamics. And so the idea is we can use different orographies to look at different flows. And I'll be showing 2 variants. So we have a gap flow and a vortex shedding variant. We'll be looking at cases with and without the Earth's rotation and comparing 4 dynamical cores, which I'll explain a bit later. So the initial condition is quite simple. So we have an isothermal atmosphere. We have a solid body rotation, which means that the flow is maximum at the equator and decays towards the poles. And then we have an orography profile, ZS, and a pressure field, which is balanced to this. A couple of other modeling features we had is we have quite a thick Rayleigh damping layer, and this is because we have quite steep orography and gravity waves can impact if we don't have enough damping at the model top. We also have a small Earth factor, so this is where we shrink the radius of the Earth, and we do this to make more realistic length scales of the orography. And 2 consequences of this are that we need smaller time steps, and that it also increases the rotation rate in the cases with rotation. So version A is gap flow. So this is motivated by when you have, say, a mountain chain here, and you have a region of reduced altitude or a gap, and the flow going through that will accelerate, and we wanted to look at this. So on the left-hand side, we have a picture of the velocity perturbations, and on the right, the temperature perturbation. So on the top row, we have the without rotation case, and on the bottom, the with rotation. And in the velocity fields, in both cases, we have these red regions through the gap. So the orography is shown here in gray. This is a cross-section at 300 meters altitude. And the red shows we have gap acceleration. When we have without rotation, we have a detached leading region of flow, whereas in the case with rotation, this accelerated stream kind of stays together. And in the temperature field, we see that the case without rotation, we have these vortices which form around the outside of the orography and propagate along. And in the case with rotation, these form actually from within the gap and propagate polewards. So the second case is vortex shedding. So this is motivated by, in the Earth, you can see that where we have isolated islands, often in the atmosphere you get these really cool vortex streets forming behind them. We're very similar to a von Karman vortex street, slightly different dynamics of how that's initialized. And a key feature of these is that you need some asymmetry in the flow to instigate it. So we put the mountain at 20 degrees north, and this means that the flow is slightly slower over the northern slope compared to the southern slope, and this instigates vortex shedding. So here I've got pictures of the relative vorticity. So on the top row is the case without rotation, and the bottom row is the case with rotation. Without rotation, we have the kind of more classical vortex street forming, where we have alternating vortices of different signs shown by the different colors. And in the case with rotation, we have more dominant cyclonic vortices forming. Okay, so the 4 dynamical cores we looked at during DCMIP, we had 3 from CAM, the community atmosphere model. So we have CAM-SE, the spectral element model. We have FV3, the finite volume model on the cube sphere. And we also have MPAS, which is finite volume and on a Voronoi mesh. The 4th model we looked at was Gung Ho. So this was run by Thomas Bendel, and it's a compatible finite element method on the cube sphere. And this is from the UK Met Office and will be part of the next atmospheric model. I won't go into the details, but just to highlight that there are a number of different modeling decisions between these dynamical cores, and this is reflected in the simulations we see. Okay, so just comparing the gap flow simulations. So here I'm just showing the temperature perturbation fields. On the left is the case without rotation, and we have SE, FE3, MPAS, and Gung Ho. So we see that SEs are probably a bit smoother than the others, and this is from quite a strong hyperdiffusion I found in CAM. FE3 and Gung Ho have a bit more smaller scale features. One thing to note is Gung Ho doesn't actually have explicit diffusion. And MPAS, we can see some asymmetries, and that's due to the asymmetrical mesh compared to the other 3 being cube sphere. And on the right-hand side, we have the case with rotation. We see all of them form these detached vortices as expected. But in the case of FE3 and Gung Ho, these are actually more stretched longitudinally. So if I go to the case of vortex shedding, so here I'm plotting the relative vorticity fields. In the case without rotation, we see all of them forming these vortex streets. Some are noisier than others, and this is probably due to model-specific diffusion, which I'll go into in a second. And in the case with rotation, we see that all of them form these dominant cyclonic vortices, but different numbers and locations of these. So just to briefly summarize some diffusion aspects of each dynamical core, this is quite a key difference between them. So starting with the SE model, I first looked at reducing the strength of the hyperdiffusion, and we can see in the case without rotation, we get some more of these smaller scale features, which is similar to what FE3 and Gung Ho were showing us. And on the right, we have the case with rotation, and interestingly, reducing the hyperdiffusion actually led to a lower temperature perturbation when I might have expected the opposite. With FE3, a key feature of the diffusion in this model is the choice of horizontal transport scheme. So the default transport scheme in CAM is relatively diffusive, and as shown on the left, this is a pretty good gravity wave, and it's damped reasonably well by our sponge layer. And when I played around with going to a very inviscid transport scheme, I found that actually the damping of a sponge layer didn't work nearly as well. And so this is just a word of caution that often changing one diffusion mechanism might mean you need to tune other ones as well. And the last diffusion thing I'll look at is an MPAS, again, reducing the hyperdiffusion. This was on the divergent component of the flow. And interestingly, this also feeds back on amplifying the rotation, because it's the relative vorticity field. And so the comment here is that damping just the divergence or the rotation still will impact the other, because these are complex flows, and yeah, due to interactions, etc. Okay, so just to quickly summarize, so I introduced a new test case we had in DCMIP 2025 for comparing dynamical cores. We had gap flow and vortex shedding variants, although you could basically put any orography you wanted in there and have a look at what happens. We saw some differences depending on the choices of the model, such as the grid, spatial discretization, and specifically diffusion is a big factor. And also we have submitted to GMD, and hopefully we'll have a preprint out soon if you're interested in looking. Thank you.
Much for presentation. Have you tried to compare it with DNS models, like very high resolution models?
No, we haven't actually, but definitely for the vortex shedding case, that would be interesting to see what that was getting us.
Ground truth in your simulation? Do you know which one is better, which one is not?
No, and I suppose that's, a downside of what we have currently. But yeah, we don't have a expected or true solution yet, no.
Mhm. Hi, can you hear me? Can you hear me? Yes. Okay, can you hear me? I can't hear you. Ah, right. Yes, that's what I thought. So that's a bit. Is your mic on? Check the mic. Yeah, my audio is working. I've just tasted it. Can you hear me now?
Just one moment, please. We can't hear you in the center grid.
Yeah, right. How about now?
Thomas, can you say something, please?
Yeah, I'm here. Can you hear me? Hello?
Yes, we're not getting audio in the room. Hold on one second.
Okay. So, but you can hear me. That's positive.
Yes, yes. Here's some good.
You want to swap? We can wait for the next talk if you like, if that helps.
Hey, Thomas, give me a second.
No worries.
Hey, Thomas, we're going to go to the next talk and we'll come back to you, okay?
Okay, fine.
All right, thank you. Sorry about that.
Sure.
Alrighty, apologies for that. We're going to jump ahead to the next talk, which is by Hadi Kia from the University of Houston. I hope it's okay with you to speak 12 minutes earlier. So, next slide with this, and you point with this. Okay.
Hello, everyone. My name is Hadi Zanganekia. I'm from University of Houston, working with Dr. Zhang. Today, I'm going to talk about moisture source attribution and precipitation recycling in, okay, it's fine. Okay, like here. Good. Right. Okay. So I'm going to talk about moisture source attribution and precipitation recycling in Southwest North America. And then, so a little bit of background in Southwest North America. As you know, we have a drought problem. And then understanding of source attribution help us assess how precipitation may respond to changes in remote moisture transport versus local land. And recently, Joe et al., like in my previous colleague, used one layered dynamic recycling model, which is very simple model to study a moisture budget and moisture variability. And because this is a very simple model, considering the whole atmosphere in one layer, there are some limitations. So we try to expand it to two-layer model, which treats the atmosphere in upper layer and lower level. And then actually Jesse is here, news bomber. So in 2018, he used 21 geographical water tags using ICAM. I tried my best to make it work with ICAM 5, but ICAM 6 was a little bit better. As he helped me, but I'm using ICAM 6. And then there is another model we are interested to look at, which is WRF WVT. It was developed in 2018, but unfortunately not very well updated. So it only can tag one specific area in contrast to other models that they can tag multiple source area. And then the research question we are trying to answer is what fraction of Southwest North America precipitation originates from local versus remote area? And how do they vary seasonally? And also, how sensitive are the results to the choice of models? Because we don't have any observation for it. We can't really use a station to say this amount of precipitation came from, for example, the Gulf of America or somewhere. And then, as I said, I'm using two-layer dynamic recycling model, which is actually my moisture budget framework. And we are using WRF WVT, which is online Eulerian, and also ICAM 6. It has, we are using the isotope-enabled one for further research in future. And they are a little bit different. The two-layer model we have, they trace back from target area. For example, you want to see the origin of precipitation in Boulder, so we trace back in time and find those sources. But in WRF and ICAM 6, it's different. They track the moisture from the source area. As I said, WRF can only, for now, can only tag one area, but ICAM 6 can tag multiple sources. Yeah. Okay. And then, as I said, the Southwest US is our target area for now. We divided the area into western area and eastern area. The western area has Mediterranean climate, which means they have more precipitation in winter. And region 2 or Reg 2 is more summer monsoonal climate, which has a more summer precipitation. And as you can see on the middle plot and the right one, I'm showing the precipitation from observation data. And the green area on the first plot is reg 1, and the red one is reg 2. So about our two-layer dynamic recycling model, we divided atmosphere to two-layer, upper level and lower level, and we use the 700 hectopascal interface. And actually, each layer we are using, they have their own back trajectory. We march back in time until 90 days, and then we find the first grid point on the 90 days or the day which the trajectory leaves the domain. And we are using the near global domain, and resolution is the Era 5 resolution, same Era 5. And then there are two equations which are actually from moisture budget that we are solving for both lower and upper level, and then we find the contribution for each cell, and then we do the weighted average to find the contribution of each cell to the target area. So the same setup, the same grid resolution we are using with WRF WVT, and the same time period from 1979 to 2014, and we are using Era 5 SSD for variable sea level temperature, and also we are tagging 3 areas separately. This is very computationally expensive model, so we had to rerun each case 3 times to get like three region tagging area. So the blue area is North Pacific, the orange one is Gulf area, I can say, and then the green area is the local land. So we are actually tagging 3 separate. And then for ICAM 6, we are challenging the model with lower resolution actually. And with ICAM 6, we are using 2 degree instead of a quarter degree. And then we are nudging U and V 3 hourly. So ICAM 6 is global, but WRF WVT is near global model. And here are the results. As you can see, for the top one is for region 1 on the western side, and the bottom one is for the eastern side. The results are very similar with WRF WVT and ICAM 6. Actually, the local land is the main summer moisture contributor, especially in July and August, and they are increasing in June, July, August. And DRM model, like the very small, the cheap model is really doing good in region 2. And region 1, actually, the train is captured, but the amount of local recycling ratio is lower compared to WRF WVT and ICAM 6. So looking at the spatial pattern, comparing WRF with ICAM 6, the spatial pattern is almost the same with correlation more than 0.97. This is the average of all MJJA, May, June, July, August, during all 36 years. And there is only a little bit of difference, I can say, in local land area that ICAM 6 predict more precipitation from local area compared to WRF. And also showing a 2-layer dynamic recycling model. The Reg 1 actually gets the most early summer moisture from the west side and Pacific side. And by July, August, Reg 1 sources shift slightly to the eastward, and Reg 2 has broader continental sources compared to Reg 1. Actually, these plots are showing the contribution of all sources to the target area, not everywhere. The places that we track the moisture from. So this is a little bit different from the other plots because the 2 models are working differently. And then we were interested to see if this spatial plot is actually makes sense, like visually makes sense, because the reg area is getting more, reg 1 is getting more from west and reg 2 getting more from east by August. And then we tried to make a fully tagged ICAM 6, which is very expensive one, I just finished running this actually like last week. So we tried to tag 64 area, like very same as Jesse did with 21 tag area. But we are actually refining the grids near the CONUS. And we are interested to see if really it matches the two-layer dynamic model we have. And then looking at the result, this is showing the actually precipitation fraction per source area in million kilometer. So because we have different area of grids, so we normalize them with source area. And then the left plot, the left plot shows the contribution to Reg 1, but the right one shows the contribution to Reg 2. So visually they make sense, like they get more moisture from west, and they get, for Reg 2, they get more moisture from local land and eastward. So my next step is to validate it with a two-layer dynamic recycling model. But actually comparing WRF with ICAM6, I can say having WRF having 8 times finer grids, it's giving very similar result to ICAM6 model. So yes, so I'm gonna just wrap it up now. So at a fraction of the cost, like 200 cheaper than WRF WVT and three times cheaper than ICAM6, the two-layer dynamic recycling model offers a scalable, low-cost alternative for moisture source attribution. Thank you so much. I guess there is a question.
Sorry. Yeah, great talk, Hadi. I'm just curious because, I mean, the fact that you show that the resolution, between WRF and CAM didn't really matter that much. I mean, is that kind of an implication that it's the large-scale kind of dynamics that are controlling the moisture transport? And then does that also imply that that's one of the reasons why the two-layer model is doing so well? So does it matter in regions where mesoscale circulation and things might matter? Would these relationships hold? I guess, sorry. So my question is basically, what are your takeaways from the fact that the spatial resolution didn't seem to impact the results?
Actually, we didn't. So to me, we should challenge the ICAM6 with the farther remote precipitation, so remote area other than like the local one. So maybe we are tagging very local one and very remote one. We can't really see visually the differences. But if we only like tag a little bit farther, maybe the WRF gonna do better because the resolution is better. But for Southwest US, I guess, I mean, we are interested in local, like what's happening around it. Yeah, but that's interesting that we can just challenge the ICAM6 like this. So I was surprised with the performance. Yeah, thank you.
Thanks, Hadi. I think we'll move on here. I think we're going to get the long-awaited Thomas Toniazzo talk now that I'm announcing now for the third time.
So can you hear me now? Oh, that's good. Right, so I'll share my screen then and get going. Sorry for seeing so much of my face. It's slightly unnecessary. Right, can you see my screen? Right, I can't hear you because it's only, so speak up if you need to tell me something, please, because I can hear you only very weakly. Okay, cool. Right, so I'm going, this is an update from a talk I gave in February, actually, and it's about enforcing local energy conservation in CAM physics, which is the main source of energy non-conservation in CESM, in fact. It is a very boring talk because it's only a matter of doing things right, as in the example of the cookies. In the right order and following the correct recipe. So the problem consists in the fact that CAM is not conserving energy locally, and this conservation is locally large. It's of the order locally of hundreds of watts per square meter and integrates globally to about 1 watt per square meter, which is a signal that is comparable to climate change. So it is a large error in the model simulations, in the numerical simulations of the climate. This has been a long-standing error, and it's been traditionally repaired by using a fixer that actually computes the energy missing or in excess at the end of the time step and applies a uniform heating, well, a uniform temperature tendency really over the entire atmosphere. So this unfortunately breaks the relationship between, for instance, radiative force and local temperature tendency. So it is something that arguably breaks a little bit the what really CAM should do when we are talking about climate or long-term weather prediction. How does this come about? The main culprit is the mass adjustment at the end of the physics cycle, which is explicitly allowed to break energy conservation. And this is due to historic approximations that have been made that have actually become unnecessary. There are two ways to cure this problem. One is to go back to the old good 90s when water was massless and therefore also enthalpyless, and that is a consistent formulation, or else we actually attach the necessary material heat or the material enthalpy to the water mass that is being exchanged between the atmosphere and the surface, and also within the atmosphere. So in order to do this, the very first step, which is the breakthrough really that was needed in order to manage to fix this problem, is that we need the correct thermodynamic functions. We need to have the correct enthalpy function for the water species in the atmosphere. This hasn't been the case for a long time and is still not the case now in standard CAM. In order to define that enthalpy function, we need to define reference phase. This is known. We also, however, need to define a reference temperature that matches the latent heats that are used in the model, and that 0 point enthalpy. That is both T0 and H0 being arbitrary constants which we can choose, but they need to be used consistently throughout the model. Once this is done, then we can go to the business of actually adjusting both the mass conservation and the energy conservation at the same time consistently. And the way to do this is actually to take account of all terms that are involved, namely the change in enthalpy due to mass adjustment, the pressure work, the material enthalpy of water, the internal energy, if you like, of water, and match that to the implicit heat that is due to the update of the heat capacity of the mixture of moist air. All these terms are necessary in order to satisfy the equations that we need to satisfy that are documented in Lauritz et al. 2022. And once we do this, we find that we have a material enthalpy flux at the boundary, at the surface, that has the boundary temperature, and between the point of water loss in the atmosphere and the surface, there is an exchange of heat that occurs in reality between water and air as water travels through the atmospheric column. So this is what they've done, and the steps that are necessary, they are all of them necessary in order to achieve this, is to correct the thermodynamic functions. Have a look at physics update, because in the case of NPAS, there is an error there that also implies non-conservation, and therefore there is an additional non-conservation error for the non-hydrostatic dynamical cores. Generated necessary rain and snow production diagnostics that is passed to the enthalpy adjustment routine. Do the adjustment, do the exchange of heat between air and atmosphere water, add the material enthalpy flux to the surface fluxes to close the budget, and check, importantly, that all the states update are independent of your arbitrary constant, so your reference phase, your reference temperature, and your reference enthalpy. Once you achieve this, then everyone's happy, and you can choose or not to turn off the fixer for the physics part. It doesn't matter, as I'm going to show, because the residuals are very small. This is shown in this figure, where there is a host of simulations. These are aquaplanet and slab aquaplanet cases, and I'm using a mix. I'm using the FV dynamical core, the SE dynamical core, MPAS, and I'm using CAM5 physics, CAM6 physics, CAM7 physics. For all of these cases, I can conserve the physics energy exactly or nearly exactly to better than 10 to the minus 10 watts per square meter. And the fixer at that point is only fixing the dynamics part. So it's only repairing the energy non-conservation that occurs in the dynamic time substep. And when this is done, in fact, you can see that the simulations collapse onto their dynamical cores. So this dA, dt, infix dynamics is only dichord dependent, it is not concept dependent, is not physics dependent. So this is another proof that the method works. They are also smaller generally than the fixer tendencies that needed to be applied before. Particularly in MPAS, correcting also the physics update cycle avoids a lot of noise. The fixer is really working extremely hard in MPAS in the default CAM code. And finally, E flux is representing the material enthalpy flux. At the surface, they are 0 for the default CAM, while they are taken account for in this work. So another comment, I've implemented these corrections also for the simple physics package. That is a particular case because the simple physics package doesn't even attempt to conserve energy. It doesn't really run check energy. So that has to be inserted. And when doing this, I came across several errors. In fact, in the physics suite, for instance, in Thatcher-Jablonowski 2016, which were explicit violation of energy conservations, and frankly, some of them just simply errors in the code because an implicit tendency is then matched to an explicit flux, and obviously they don't. And also there is a diffusion of potential temperature that is automatically not energy conserving because there should be a conversion into kinetic energy that isn't happening. So you cannot do that. So you need to diffuse either internal enthalpy or total energy. So once this is done, you find also that in these idealized nice paraclinic wave tests, conserving energy matters. There is a noticeable residual of non-conservation from the dicore, and that is attributable to using temperature tendencies to couple the physics part and the dynamics part of the time step, because those temperature tendencies will not act on the same heat capacity locally, and therefore the energy that should be added during the dynamics time step that is coming from the physics isn't actually respected, and it has a different value, and that is a remaining source of non-conservation. However, it is much, much smaller. It is never bigger than a few watts per square meter compared to much larger values when this is not done. Right, so the results is that finally the code I've implemented for a fairly recent tag of CAM supports CAM5, CAM6, and CAM7 and simple physics packages. It supports MPAS, SE, FE3, and FE dicores. I've tested this on all of them. Multi-annual integrations in QS, in aquaplanet and slab aquaplanet configurations. The residual energy conservations are better than 10 to the minus 10 watts per square meter, so that's okay. The implementation calls a single routine at the end of tphys-acc that replaces the whole explicit adjustment section that is there. It is namely driven. There are 4 entries. One of them is energy back compatible. So if you like to have not conservation, you can still use my code with energy back compatible equal to true, and then you'll get your wrong results that you like, historically speaking. Right, there is some issue because calling it at the end of the physics cycle means that some of the water history is lost. This does not imply any error due to multiple local phase changes, so that is still an exact calculation. But in order to reduce the remaining error, there could be an implementation that is calling a just entropy after each parameterization. And that should be straightforward. I'm saying easier, but I haven't actually tried it yet. It is obviously more invasive from a code-based point of view. Finally, it's worth noting that the dicers themselves have avoidable energy non-conservation, partly due to the coupling, partly due also to the choice of time stepping. These are smaller for SE and MPAS. They are obviously larger in FV because of the internal assumptions of FV in not regarding condensates. Right, this concludes more or less. We probably should be more careful in energy conservation because it is an important characteristic of the climate system that heat is transported around and is causing temperature and humidity changes. This shows actually systematic impacts on the moist paraclinic wave case. So the results of those tests change when you conserve energy. And using fixers is bad because not only is it not physical, but actually it hides other model formulation errors that you might have. So you're not really checking your code as well as you could when you're using a fixer because it's just papers over stuff. And the way to cure things is simply to respect the physical equations you're supposed to solve. So that's what I've tried to do. Very happy to share my code with anyone who wants to use it for any purpose, and I can help you obviously porting it to your particular version, flavor, repository of CAM, and please get in touch with me to do that. That's my email address. So that concludes my talk.
Thank you, Thomas. We're really behind schedule here, so people can email Thomas on the email address that you just saw on the last slide, and then we need to move on to the next talk. So, Justin, if you're there, good. So next up is Justin Richling. He's going to talk about the ADF.
Is there a laser pointer? So you point at this. Oh, gotcha. And then next slide with this. Okay, I guess we're good to go. All right, thanks for joining my talk. I know there's been some great discussion about model development, so it kind of wraps in nice to what I'd like to discuss today and what we're building in NCAR. And my name's Justin Richling, and I'm a scientist at CGD in the atmospheric and modeling predictability section. So we have a diagnostics package that's already out, so if you're not familiar with it, this is going to kind of assume that, but we have documentation to look at all of that beforehand. So really quick summary of what it is. It's here to replace the old NCL AMWG diagnostics and to build upon that. So we've hit a lot of those benchmarks. We're really looking to advance some of the features and some of the diagnostics, and you'll see kind of what's going on here. So here's our GitHub, and we have tutorials as well, so we can show you guided examples of how to run this in the various capacities that it has. So please check those out if you're interested in this package. Just as a continuation, it really just takes history files from CAM, SEMA, similar models, makes climatology files from those, then regrids those if they're on different horizontal grids, and then it'll do vertical interpolation to your flavored set of vertical levels for any 3D variables. It runs analysis scripts, so basically statistical tables, and then sort of a standard set of plots, and you can see on the website in the tutorial examples of these ones that are kind of just in there. And then it'll generate a nice website so you can view all your images. So what I want to talk about today is sort of some of the more recent ones, if you have been following, and the ones that we're actually testing. Hopefully fairly soon we're getting a lot of good examples of this. So chemistry and aerosols have been kind of a nice lead for us to get out of our own just general atmosphere, and we're looking into developing more of the whole atmosphere Wacom and ACOM have been great to help get some of these plots up. And I have sort of examples of all these plots as we follow. So it'll be kind of a show and tell kind of thing. But on the right are sort of the all the TEM plots, the transformed Eulerian means. And I will want to say that the land diagnostics have sort of piggybacked on us. So if you're doing any kind of land atmosphere where you would like some land diagnostics, they have a branch off of our repo, and you can chat with Will Weeder, who was just next door, if you're interested in what he's doing over there. On top of the plots, there's two kind of big infrastructure changes we really wanted to get pushed through with CSM coming up again. Native grid is kind of the output that we're looking to get. So a feature that is currently under test is to have an option, if your output is on the native grid, we can grid it to lat/lon via XESMF, excuse me, or we can plot it unstructured with UX-Ray, which is a great mesh plotting if you haven't heard of that. We do have testing going for the multi-cases, so if you have multiple cases you want to run against one baseline, we can do all those diagnostics a little bit quicker than having to do this multiple times over and over. And then we have sort of some updated plotting details that just help with the plots later on, and I have examples of those. So for the chemistry and aerosols, we've had great work to get some of this stuff in, so I'm just going to kind of rapid fire through some of these images, but this is a total column Moppet diags, and we also have a whole slew of ozone column diagnostics that are sort of regionally based. So we have a whole database of where you can pop some of these ozone columns. This is just a boulder as an example. Likewise, we have Taylor diagrams for all those. I hope that's not too hard to see. And then, so those are actually in the ADF, so you can plot those out right now if you run the ADF in its main branch. But some of the development branches we're working on, this one is the Wacom and CESM cycle plots that I mentioned earlier. This is on a dev branch, so you can find it there on our GitHub. And so the TEM plots, I'm just going to kind of discuss sort of the major ones. So we got the EP fluxes, and you will need to output the correct variables to CAM, and we can discuss that if you need. We have V bar star, W bar star as well, and these are two cases and then the difference obviously on the bottom. We have the mass stream function, and finally just the EP flux divergence as well. So those are the ones that we're currently testing. We're always open to try more if they're interesting to you. And we have updated QBO plots with MERA 2 as well. And then for the seasonal cycle, these ones, we're looking at the zonal mean, zonal winds, and the zonal mean temperatures. The winds are compared against MERA on the bottom, and the contour lines are interpreted to MERA, or from MERA, I should say. Now on the right, it's a little hard to see, but this is the temperatures. So you have the top is the models, middle is with MERA, and the bottom is against observations of SABRE data as well. And then we have northern and southern polar cap temperatures, and you can see this is zonally averaged and then meridionally between the Arctic and the Antarctic. We have cold point tropopause. So again, this is a zonally averaged quantity, and then we're pulling it at 90 hectopascals, just to kind of get you an idea of the temperatures up high. And this is a repeated monthly, so you can see it goes January to December, sort of repeated for ease. Along the same lines of that plot, we have the H2O mixing ratio, both at 90 and 100 hectopascals. And these are all optional. You can throw in multiple levels if you wanted to look at something else of interest. And then for the infrastructure, we do have, again, another dev branch called Native Grid, so you can check this out. It will take a little bit of advancing in the configuration file, but this is kind of, it got a little off. So remapped versus unstructured, tried to color code it so I don't have to keep talking about it. But these are just kind of the options that you need to go from either having it remapped to lat/lon or to do unstructured through X-Array. So just a couple simple command line, or not command line, but config options. Again, here's kind of a comparison of the exact two same cases doing remapped and via X-array. Notice the bug is in the text, not the actual plots. Plenty of bugs, always looking for bugs. But spatially average-wise, it looks pretty good. Min and max are pretty close. And just to highlight that it was maybe just a text bug and not data bug, these are the two statistic tables. You can see most quantities are fairly close. So I think you're good to go with either one of those as an option for the native grid. And finally, sort of the enhanced plotting features I was talking about. So when we run the ADF, we're kind of constricted to setting contour levels and color maps, but this can be not highly informative because you have different vertical levels, different regions. So this contour level is not really great because it kind of gives you this. So this is the same contour region over all of these, so you can see some of these values get washed out. It's not a helpful plot. So that has been a pain, and I apologize for anyone who deals with this. So the fix is to make this incredibly robust. And by that I mean obnoxiously. So you can change your contour levels, color bars, things like that based on both the plot type, vertical level, stuff like that. And just to throw stupid color bars at you, here's none of this should be taken as a good color bar for wind. But just to show that, you know, before you were stuck with one contour range, one color bar. So that's hopefully pretty helpful. And obviously we're always looking for guinea pigs, test our stuff out. If there's a set of diagnostics that you run often that you think the community would be useful for, please reach out. Again, the best way is through GitHub issues or discussions, or email me personally. Thanks.
Thanks for getting us back towards being on time.
Yeah, sweet.
A quick question for Justin while Vince sets up.
Take that as a no. Thank you.
I have a quick question.
Sorry, yes.
Yeah, how does the ADF, this looks pretty good, how does the ADF choose the vertical range? Is that just from the data?
We have a default set, but you can also override that by whatever number of levels you want.
Okay, because like Whack-A-Mex goes really high. So.
Yeah. So it'll obviously stay within the bounds of that, but if you supply it a certain amount, it'll interpolate to those levels exactly.
Right.
Yep. Thanks.
Okay, next up is Vince Larson, who is going to talk about tuning.
All right. Well, thanks for giving me the opportunity to talk. I'm going to talk about some tuning analysis that was done by Ben Stevens, Adam Harrington, Cecile Hane, and Julio Bachmeister. Oops, how do I do this? There we go. Yeah, so we can't release a new version of CESM unless our version is in global radiative balance. And that poses a challenge for the final stages of tuning. And so the problem is we like to tune on nice, simple, fast configurations. So for instance, a configuration that has prescribed sea surface temperatures. But if we do that and spend a lot of time tuning, and then we put those parameters into a coupled ocean atmosphere run, and it's imbalanced, then we can't use those parameter values. So we want to avoid that sort of problem, that sort of waste of time. So in CSM, the global mean radiative balance is measured by the model variable RESTOM. So it's the net global mean warming. It's just a scalar of the whole Earth system, including ocean and atmosphere. So if RESTOM is positive, that means the whole system's warming. What we want is a value that's close to 0 in the pre-industrial climate. So if we're doing late stage tuning, then we need that tuning to take RESTOM into account. That means we need to do runs with long duration, which is expensive, unfortunately. So how expensive? Well, so one problem is that RESTOM has strong interannual fluctuations. And so if you want to estimate the value of RESTOM, you need to do runs which are fairly long, at least 10 years in duration. So this is a slide that was put together by Cecile, and basically it shows 100 years of a CESM simulation, and the rest varies by quite a bit. So it goes up to values greater than 1 watt per meter squared, which is quite large, and then down almost to minus 1 watt per meter squared. And if you take the 100-year average, well, then you get a value of 0.34 watts per meter squared, and that's the true model rest but you could imagine that you're tuning over here somewhere, and you think that your rest is 0, and you think it's going to be wonderful, and then you start running the model, and just a few years later, the rest all the way up to 1 watt per meter squared, which is quite large, and you really don't know what the true rest is. And so what do? Well, you could take a 10-year snippet of this and average over it, and then that would give you a better estimate of the true model rest but of course, the more years, the better. Oops. Now what did I do? Okay. So then if we care about rest then the tuning becomes very expensive. So to smooth out the rest fluctuations, we ran our CSM3 tuning runs with a duration of 12 years. And then we wanted to tune 10 model parameters. And then, of course, the problem is this was all during the course of model development. So every month or every other month, we'd get a new model version which would change answers. And so when we were doing our tuning, we wanted to finish it before the end of the month, before the model would change. So we wanted a fast tuning method. And the other problem is just the computational budget. So basically, Ben Stevens would sort of put these runs in sort of under the radar, not bothering anybody too much. But if we wanted to run a standard Latin hypercube perturbed parameter ensemble with 100 ensemble members, then we'd probably have to ask for an allocation. And then inevitably, we'd mess it up and say, oh, sorry, we need to do it all over again because we misconfigured something, and we weren't confident we could get that extra allocation. So what we did was we used a poor man's tuner, quad tune, and we tuned to match 5 fields. So rest itself, shortwave cloud forcing, longwave cloud forcing, liquid water path, and ice water path. And a special goal was to reduce the liquid water path in the storm tracks. So we penalized large magnitudes of global mean rest and so the goal here was that whatever tuning we got, we'd end up with something that has a decent, reasonable rest that we could actually use in the coupled model. The 10 tuning parameters were mostly related to microphysics, aerosols, and deep convection. So in order to reduce the number of tuning runs, we basically neglect the parameter interactions. So we just do simple one-at-a-time sampling of the parameters. And then the problem with that is we neglect the parameter interactions, and so QuadTune's parameter recommendations aren't perfectly accurate. So QuadTune, its usual symptom is it tends to be too optimistic. But typically, qualitatively, it will push the model in the right direction. So it's still helpful. But the beauty of neglecting the interactions is instead of having to do p-squared model runs, where p is the number of parameters, we can do 2p plus 1. So it's 21 tuning runs instead of the typical 100 tuning runs. So it saves some time. Okay, so we did our tuning exercise, and it yielded a simulation with reduced or improved liquid water path in the Southern Hemisphere storm track. 7 of the 10 tuning parameters recommended by QuadTune will be used, hopefully, in the release of CSM3. The remaining 3 parameter values were hand-modified after the fact. And why was that? To account for information that wasn't in the tuning data. So this tuning business is very risky. We only tune to these 5 fields, so QuadTune is perfectly free to make the dust burden much too large, or make the QBO have the wrong period, or whatever. So there's always a risk that something bad will happen. And so these 3 parameters are modified. And this is the result that we got. So this is what we started with, is this run 308, and compared to OBS, the liquid water path in the storm track is too much. So it's just too large a value. This is another configuration which varied the model structure a bit, didn't seem to help. This is the version where we change, we introduce QuadTune's recommended parameter values. So it's a difference plot, and where it was too blue before, now it's redder. So in other words, it's reducing the liquid water path. And now, if you have a model that's already pretty close to in tune and you start tuning it more, there's always trade-offs. So the trade-off here was the shortwave cloud forcing, which was already somewhat too bright in the tropics, gets even brighter. But nonetheless, it was felt that this was a good compromise. But much of the benefit of tuning comes from improved understanding of the model sensitivities. Like, I think the real wins come if you can change the model structure and not just the parameter values. So, you know, these tuning methods, they can give you some information. So you might ask, okay, what is it that actually reduced the liquid water path in the storm track? And you can go back and look at the tuning diagnostics, and you can see that it's autoconversion and accretion. So it's both warm phase microphysical parameters. The autoconversion basically was tuned such that it's drizzling more, and that happened both at 45 degrees south and at 60 degrees south. And the accretion was counterbalancing that at 45 degrees south, but not at 60 south. And then that yielded the result we wanted at 60 south. So a model developer can take this and say, okay, there's important physics going on with autoconversion and accretion. The model developer can look and see that it has important impacts in the storm track, and then start to look for model structural errors. It just points you to where the model problems are. Likewise, long-wave cloud forcing also improved a little bit in some areas. So basically, CSM3, it has sort of a dearth of deep convection in the eastern Indian Ocean right here. But with the new parameters, that's mitigated to some extent. So we still have an under-prediction of the deep convection, but it's not too bad. And why was that? Well, again, looking at the tuning diagnostics, you can see it was due to two parameters. One of them was this W sub I, which controls the activation. If you increase W sub I, then you increase the number of cloud ice that are nucleated. And that boosted deep convection over a wide swath of the ITCZ here. There's another parameter which was important, which was this VTRMI. If you boost that, then you boost the sedimentation or the fall speed, and that tended to diminish the deep convection in this eastern part. And again, combining these two, we got the increase over the eastern Indian Ocean that we wanted. But, you know, basically one is acting like a source of cloud ice, one's acting like a sink. The balance overall is really not that much different globally. It's about the same, but it does shift the spatial pattern in a way that was beneficial. So again, you can learn a little bit about the model physics. These two parameters are important for convection in the Indian Ocean, which may not have been obvious ahead of time. So conclusions, one is it's difficult to tune a coupled model quickly enough to contribute to model development. But you can reduce the number of tuning runs if you're willing to compromise on your emulator, just do one at a time sampling. And the tuning process can give you some insights into where the model sensitivities are, autoconversion accretion for the storm track, or the cloud ice for the deep convection in the eastern Indian Ocean. So thanks.
Okay, so while Hing gets set up, we'll take questions for Vince.
I'm wondering, with what you did for the Southern Ocean, have you seen any detrimental effects on the precipitation distribution if it's drizzling more?
We haven't looked at that, but yeah, that's a great question. Yeah, you would expect that it would be. I mean, basically, we tried a lot of turbulence parameterizations to try and dry it out. That didn't work without damaging other aspects. So now we're trying to rain out the clouds, so that's going to lead to more drizzle. So is it too much? Yeah, I don't know. There's always a risk of tuning in compensating errors. So.
Okay, next up is Hing Ong. He's going to talk about a version of MPAS with a deep atmosphere approximation, so you have full 3D Coriolis forces that's been implemented into CSM3. So take it away.
Yeah, thank you. Well, first of all, I want to thank NCAR CGD for the travel support last year and this year. And this big collaboration actually started at this meeting last year. So really thank. So I'm going to talk about precipitation improvement by introducing deep atmosphere configuration in MPAS and spectral element dicore, two dynamical cores. And deep atmosphere, I'll talk about that later. The main target here is the double ITCZ bias, which has been a persistent problem since the earliest generation of our system models. Look at this figure, for example. These are 3 generations of ensemble means of many models of that generations. And you see that that there's a precipitation rate overestimation in the off-equatorial tropics, and that's why they are called, it seems like a double ITCZ, so that's why it's called double ITCZ bias. And we want to improve the model by introducing the non-traditional Coriolis terms into the dynamical core. What are the non-traditional Coriolis terms? Well, traditional Coriolis terms refers to this. If you consider the complete Coriolis, that is the planetary vorticity, and the traditional Coriolis is the vertical projection of that, while the meridional projection of the planetary vorticity is associated with this non-traditional Coriolis term. It is proportional to the cosine of latitude. It turns eastward motion upward, upward motion westward. It is maximized at the equator, and it is symmetric to the equator. They are omitted in most of the global atmospheric models. And they are recently introduced into 2 atmospheric dynamical cores. One is MPAS, one is SENH. I'm going to talk about MPAS most of this talk, but I'll give a brief touch on SENH. So we first want to see whether we still have the double ITCZ bias with the default MPAS model. So I use MPAS. No, actually, this is a run by CESL. You use MPAS without the non-traditional Coriolis term to drive the CESM3 model. 50-year time integration, and I'm showing climatology from year 11 to 50, and 120 kilometer grid spacing. And we see that, so this plot is showing the difference between our simulation and the observation. And we see that there is an overestimation of precipitation in the off-equatorial tropics and underestimation of precipitation near the equator. So yeah, we see that double ITCZ bias appears. And then we switch on the non-traditional Coriolis term in the MPAS dicore. Well, first of all, the computation increase is less than 1%. And importantly, that for dynamical consistency and angular momentum conservation, whenever I say with the non-traditional Coriolis term, I actually mean deep atmosphere simulation. And without the non-traditional Coriolis term would mean shallow atmospheric simulation. The change to deep atmosphere equations is a change more than just non-traditional Coriolis term. But if you do a scale analysis, you will see that the non-traditional Coriolis term is the biggest change when implementing the deep atmosphere equations. Okay, so what is the difference by omitting the non-traditional Coriolis term? We see that the precipitation rate, there is an increase in precipitation in the off-equatorial tropics by omitting the non-traditional Coriolis term. And the non-traditional Coriolis term kind of concentrate the precipitation toward the equator. And so that kind of partially explain why we see a double ITCZ bias. And the first thing that non-traditional Coriolis terms affect should be the zonal wind. So whenever there is upward motion in the ITCZ, the upward motion is kind of forced to the west by the non-traditional Coriolis term. So omitting the non-traditional Coriolis term, first introduced this westerly wind bias. This is a meridional vertical meridional vertical distribution of the zonal mean zonal wind. You see that there's a westerly wind bias in the tropical regions. And the next thing is that omitting the non-traditional Coriolis term weakens the Halley circulation. So the color shadings denotes the difference between with and without the non-traditional Coriolis term, and the contours are the simulation with the non-traditional Coriolis term. So you see solid contours with the blue shading. That means the Halley circulation becomes weakened by omitting the non-traditional Coriolis terms. And why is this happening? We built a model hierarchy to explain why is this happening. And also, using this model hierarchy, we want to show that this is a robust change. So starting from a very simple linear model, Owen and Roundy, that model shows that omitting the non-traditional Coriolis term, actually including the non-traditional Coriolis term, will induce easterly winds with heating. And then next we run aquaplanet simulations with fixed SST, fixed sea surface temperature, and we start to see that the non-traditional Coriolis terms strengthen the Hadley circulation and concentrate the precipitation toward the equator. And then we include realistic land-sea contrast to the model that gives us the AMIB type simulation. We start to see mitigation of double ITCZ bias when the non-traditional Coriolis terms are included. And last, when we couple the model with the ocean, we see the change due to including the non-traditional Coriolis terms becomes amplified. And to further show this is a robust change, we run aquaplanet simulations with two different dynamical cores. One is MPAS, as I showed before, and the other is the spectral element non-hydrostatic core. And here I'm showing two different pairs of simulations. The left-hand side is for MPAS, right-hand side SC, and the blue curve is the run with the non-traditional Coriolis term, and the red is without. And these are zonal mean precipitation rate. So you see again, in these two dynamical cores, the non-traditional Coriolis terms tends to concentrate the precipitation toward the equator. So omitting this non-traditional Coriolis term will contribute to the double ITCZ bias. Here are two caveats. We show results with the non-traditional Coriolis term only in the dynamical cores. The non-traditional Coriolis term in the turbulence and shallow convection parameterizations are not implemented yet. And the couple simulations here has not reached the equilibrium. So these are just 40-year transient results. So to conclude, the non-traditional Coriolis terms are relevant to ITCZ dynamics, and they are interpretable with this model hierarchy, and they are economical because they cost just a little. So we should include them into the model. Yeah, that's all. Thanks.
Quick question for Heng.
Very nice talk. Thanks so much. Do you happen to know, do the NICAM models or the UK Met Office models, do they have a double ITCZ? Or
it depends on which version they use, and but I recall that the UK Met Office model is kind of has a less double ITCD, but
Okay.
I'm not 100% sure about, because there's lack of a sensitivity test. They haven't done a sensitivity test of turning on and off the non-traditional Coriolis term, so it's hard to tell.
Right, right.
Okay, thank you. So standing in between you and the break will be will be Julio Backmeister, who's going to talk about gravity waves. Does this work? Whoops. You can point here. You can point there.
Oh, how? Oh, I see. Okay. Got it. Okay, thank you very much. I'm going to be talking about gravity waves, really, in CSM. I should have put ML in the title because that will be a big part of this analysis. That wasn't in the apps in the program. But anyway, before I go on, I just want to acknowledge all collaborators that have been involved at various stages of this project. In particular, Will Chapman and Aman Gupta have helped me a lot with ML models in the last few weeks. Quickly, I'll just talk about why I'm doing this. I'll describe the 3-kilometer simulations I'm using as sort of ground truth here for gravity wave generation. I'll talk about the analysis techniques, how I separate large scale and small scales in the simulations, and then I'll show some event-based machine learning. And I'll show some results and then summarize. So the motivation for this work is shown here. Over here you see the current version of CAM7, or a recent version of CAM7. It includes a new scheme for gravity wave sources we call the moving mountain, which has led to some pretty significant improvements in the simulation of the southern hemisphere polar vortex. Other earlier versions of the model are shown here, and they both show a strong vortex, and the white lines show the variation in the jet axis in these models, and there is none. So basically, before the moving mountain source, these models had a pretty much straight up and down polar vortex every year that was too strong. The moving mountain source has alleviated those problems to a large degree. This is from a paper by Martina and I, which appeared recently. We feel that our moving mountain source is a little ad hoc. There's a lot of overlap with the frontal source, physically probably. So we think we need better understanding, and the approach here is to use 3-kilometer MPass diamond simulations to see if we can clarify something about the sources of gravity waves. The model configuration is described here. I'm actually only going to talk about the no deep run, which has no parameterized deep convection. I encourage you all to go see Adam's talk tomorrow. There's some really interesting differences between no deep, which has no parameterized deep convection, and a new parameterized deep convection scheme that Adam's been working with, and you should go see those results tomorrow. And I'll just say here quickly that when we do look at gravity waves launched by convection, these seem to have there are differences. So to separate, first step is to separate large scales from small scales, and that gives you your waves. I don't want to go into a lot of detail because I take 20 minutes just describing this slide, but the basic approach is to take the high resolution grid, which is here the MPass grid, to coarse grain it. That essentially gives you the large scale flow. That's the background for the waves. So it's been coarse grained to 2 degrees any 16 in SE parlance. And then you prolong you sort of re-spread this background to the high resolution grid, which I've mislabeled here as NE240. This is the MPAS grid. And you calculate fluxes and things on this high resolution grid. And then you coarse grain those conservatively to give you sort of 1 degree more or less scale momentum fluxes that are the actual momentum fluxes explicitly resolved by the high resolution model. Then these are used in combination with the large scale fields, also coarse grained to 1 degree, to do sort of parameterization type analyses. This shows a field of, this is the log of absolute momentum flux, which is defined down here at 10 kilometers. I'm going to use 10 kilometers as sort of the entry level for the stratosphere. And these little plus signs are events, really simply identified as just maxima in this absolute momentum flux field. So these events are, what we're looking at. In the first analysis here, I'm confining the attention to the events between 40 south and 60 south over ocean. So anything close to land is also eliminated. So what we have here is already kind of a regime. We're looking at Southern Ocean, winter. This is August, the Diamond 1 protocol. And yeah, so Southern Ocean, winter. That's what we're looking at for the initial test. So we define 40 cubes around these events in time and space. They're plus and minus 5 grid points on the 1 degree grid, so it's a big cube. And we go back 3 time steps, and these are the predictors that we're going to use in some form for the machine learning. This is just an example of a cube here in the Southern Ocean. The very difficult to see blue and red shading is vertical motion at the 3 kilometer grid, and the contours are this coarse grained absolute momentum flux at 10 kilometers on the 1 degree grid. So questions are, can we learn something about sources for gravity waves, jets, cyclones, using ML techniques, and do any of the insights gained over the last decades of gravity wave research provide any insight that might give machine learning an advantage? And I point out here that already by isolating to a particular regime, we've done some human intervention. And then the last test that I'm going to talk about is transferring what we learn over the Southern Ocean in winter, that is August. I'm going to transfer the same neural net model to the Northern Hemisphere, also August, to see if it works at all in this other, in sort of a different sort of regime. So have we actually learned something that's more applicable than just to the Southern Ocean? So these are potential predictors for gravity wave activity. There are, the meteorological fields, stability, relative vorticity. This term I'm calling tilting, which is really just the vertical component of vorticity multiplied times the vertical shear and then squared to give you a magnitude. And then finally there's the, one of the frontogenesis functions that have been used for have been used to parameterize frontal sources in gravity wave parameterizations. And just everything's calculated from the 1 degree fields. So this is a quick diagram of our neural net designed by Will Chapman. It's, I can say the words, I won't read the words, but they're there. It's big, and it's big, from my standard, but it trains very quickly. Within a few minutes, we've got a trained neural net with, input of about 20,000 events. So what I want to, just draw your attention to is we then provide the neural net with a bunch of different predictors, starting with just the baseline, just the MET fields. Then, MET field U and V, except we replace stability, and then we add various other these derived quantities that I discussed earlier, tilt, frontogenesis, vorticity, etc. So we do the sweep, and we see what happens. And these are, I'm going to be pretty quick here, these are the results. Overall, we get, I think, pretty good correlation coefficients. If I just ran a parameterization in sort of, let's say, forecast mode driven by analyses, and I had some data to compare it with, I got correlations of 0.7, 0.8, I'd be happy. Oh, am I already running out of time? Oh boy. Okay. 90 seconds. Okay. So this is the test all over the southern hemisphere, and then this column here I think is the more interesting column. This is where we transfer the model learned over the southern hemisphere to the northern hemisphere. And what you see is that where there is kind of, let's call it, reasonable transferability, the predictors all include this tilt variable. That is the product of vertical vorticity and, vertical vorticity and vertical shear of the horizontal wind. So these are just some snapshots of the predictions. Here is just the prediction of absolute momentum flux compared to the actual absolute momentum flux diagnosed in the run. Here's the transferability. Maybe it's not so much to write home about, but over here, why doesn't this work? Over here is the best transfer, correlation about 0.57, and this is the baseline. Boy, there we go. And, at least we're starting to get some tilt in the ellipse. So, I'll skip that. This is a more traditional view, just doing composites, and you'll see that, what you see here is that the variables we looked at do kind of grow out as the amplitude of momentum flux is increased going from left to right. And so summary, it looks like, you could parameterize GW sources using some sort of machine learning approach. Questions are, how much memory and spatial extent do you need? It looks like this source analysis does get some benefit from sort of the things that we've learned about gravity parameterization over the last few decades. And I just want to leave you with, the last bullet here, which is that I have started looking at even simpler sets of predictors using vertical averages of things the way a gravity parameterization actually might. And those results aren't bad. We're, not at 0.8, but, we're close to, I think it's still useful. So thank you. I'll just stop there.
Question for Julio?
Like that.
Alrighty.
All right.
But since we are running a little late, let's reconvene at 3:05. Alrighty, let's get started here. So Paul Farron from ETH Zurich will start out. He's going to talk about mixed-phase clouds. Take it away.
Yes, hello everyone. Thanks for giving me the opportunity to talk here. And so today, the idea is that I kind of present you what I've been doing so far during my PhD. I'm working with Ulrike Lohmann and Diego Villanueva at ETH Zurich. And so, today we're going to talk about mixed phase cloud thinning. So for those of you who are not familiar with the term, basically it's a radiation management method or geoengineering. And so I think to kind of start the presentations, well, because I guess not everyone's necessarily familiar with that, I can start introducing what MCT is about. So, yeah, I said in the name, basically you care about clouds, right? So what you want to have is a cloud before seeding, and it kind of looks like that, right? So you have, it's important that you have some supercooled liquid droplets, and then what this cloud is going to do is that, well, you're going to have some long-wave radiation that escapes from the Earth, and then these radiations are going to be absorbed, scattered by the cloud, and then emitted as a function of the hydrometer's temperatures. And so the goal of MCT is to then do something called and so this overall leads to a net warming at the surface. And so what you want to do then with MCT is something called glaciogenic seeding. So what you do is, well, you add some, you seed the cloud with ice nucleating particles or INPs. Here in that case, we're going to talk about mineral dust. And what these INPs are going to do is, well, they're going to freeze the cloud droplets, right? And then once you have that environment where you have a mix of supercooled liquid droplets and ice crystals, well, you trigger a process called the WBF process. And so what that tells you is, well, the ice crystals are going to grow and they're going to deplete the surrounding liquid droplets of water. And so you end up with very large ice crystals, and eventually these can fall out of the cloud. And so if you look at your cloud after seeding, well, you see that you're going to have some large ice crystals here. And then if you look at the long-wave radiations, well, you decreased the cloud optical thickness. So it's not capable to trap long waves as much as before. And so overall, that leads to a net cooling at the surface. So this is the goal of MCT. And so basically, I'm doing that in CSM2 with prognostic aerosols. So I added a new source for accumulation mode mineral dust in CSM2. Then I designed some new MCT experiments, and finally, we look at, okay, how do the cloud change and how do the radiation changes as well. So first, we're going to look at the experimental design. So basically, we're trying to answer the question, okay, when and where do we want to seed? So for this, we look at something called the cloud radiative effect, which is, or CRE, which is basically a measure of, how much a cloud is going to warm or cool. So when it's positive, it has a net warming effect. When it's negative, it has a net cooling effect. So this is average for November to February, and you see that there's this area here where you have net warming here. So now you could look at the average CRE in this area, and this is what you would end up with. So you see that from November to February, it's positive, no surprises. Here we see that it's red, and then for the rest of the year, it gets very strongly negative. And this is due to interactions with shortwave radiations. So far we only talked about long-wave radiations, because this is how the clouds have a net warming effect. But then once you start looking at shortwave radiations, well, the clouds actually have a net cooling effect. Okay, so we know that we want to seed this area, get rid of the clouds in the area here. And then we know also that we want to do it from November to February. Then next step is, well, we can define some different altitudes at which we want to seed. So here we picked 3 different altitudes called high, mid, and low that you can see. So high in green, mid in red, and low in blue. And once we have this, basically we going to see that these 3 different altitudes, we're also going to add a new experiment where we see that the 3 altitudes combined. And we finally picked 4 different seeding rates that ranging from 1 gigagram to 1 teragram per seeding season. So this is cumulated over the entire area. So basically if you would sum up everything from November to February over the whole area, then you would end up with these numbers. So overall we have 16 experiments. Okay, so this is now what the dust mixing ratio looks like. So you see that we have some net Yeah, okay. Here you see that you have some maximum values here for the high at the seeding altitude, and same for the mid and for the low. So you have a maximum dust where you seed it, which makes sense. You also have a lot of vertical mixing. And then finally, in gray, you have here the combined experiments here. So you see that the amount of dust that you have in the combined experiments is not as large. This is because we wanted to have the same total seeding, right? So per layer, you divide by 3 the total that you put. Okay, so now we're just going to look at we're just going to take the combined experiments here that you see, and at the 4 different seeding rates, and we average over from November to February, and we look at the clouds. So first thing, we can look at the clouds as a function of the cloud top temperature. Here, the solid lines, you have the liquid water path, and then ice water path for the dashed lines. And so what you see here is basically you have this area here where you have some sort of decrease in liquid water path and increase in ice water path. Then if you look over that, well, you have you start to have homogeneous nucleation. And basically you have this area here where you know that dust is very efficient at nucleating ice. And you see that you have this mass transfer from liquid to ice. So this points toward the WBF process being active. So it looks like the clouds are being glaciated. Now you could also look at the total water content. So now on the y-axis it's the pressure, not the cloud top temperature anymore. And you see that you have a net decrease of the total water content. So this includes both liquid and ice. So what does that tell you is that, well, so not only you have this mass transfer from liquid to ice, but the total mass that you have is also reduced. And finally, you can look at the cloud fraction, and you see that you have also less clouds here. So yeah, basically, if I had to summarize the changes in clouds, well, I would say the seeding actually, triggers glaciation and cloud thinning. We have a reduction in liquid water content, a reduction in cloud fraction. And then we also know that higher seeding, well, I didn't really say that, but as you can see, kind of see still here, well, the more dust you put, the larger the effect is going to be. Okay, and then finally some results that I didn't show here for lack of time, but basically, if you look at what happens at the different altitudes, well, the difference you're going to have between, sitting at low altitude versus high is in fact very small. What is really important is first the seeding rate, and then it's the altitude second. Okay, so we looked at the clouds. Now we also want to look at the top of the atmosphere radiative balance. So again, this is average over the seeded area, and again during from November to February, and this is what you end up with. So you see that, well, first of all, you have very high interannual variability, but you also see that you have somehow the cooling that emerges at 100 gigagram per seeding season and 1 teragram per seeding season. However, if I just give you this point here in blue, and I tell you that you have this this difference of -2 with this very high internal variability, well, you don't really know where the signal is coming from, right? Because we just added aerosols to the model, but aerosols, they don't only glaciate clouds, right? They also do something. Yeah, so they also have a direct effect. So they directly, sorry, the slide got changed a bit here, but basically they directly interact with radiation, so that can be shortwave and long wave. And then you have a bunch of other, okay, here it's got cropped, but basically you have an indirect effect on mixed phase clouds, which is what we're interested in. Then you have an effect on warm clouds, and finally you have something called the semi-direct effect. But basically what's important for us and what we checked is that these two are likely the most important ones. And so we can again look at our top of the atmosphere radiative balance, but this time we can decompose between the direct effect and then the clouds effect, and this is what we end up with. So first thing is, well, it looks like the interannual variability was actually coming from the clouds. And we also see that you start to have an important direct effect at 1 teragram per seeding season. Another important thing is, well, the direct effect becomes more and more important for high seeding, right? So the higher you put the dust, then the stronger the direct effect is going to be for both shortwave and long wave. So for different reasons, but basically for shortwave because it can interact more readily with the radiations from the sun, and then for the long wave because of the temperature difference between the ocean and the aerosol layer. And so basically, So basically, if I had to kind of quickly summarize mixed phase cloud thinning with prognostic mineral dust, well, I would say, so we saw that the dust can actually trigger glaciation and cloud thinning. So the physical process works in the model. And then we also see that there's somehow there's a net cooling that emerges at about 100 gigagram per seeding season, although we still have this very high interannual variability. And then finally, we also saw that the direct effect starts to be important at 1 teragram per seeding season. So when you add a lot of dust, well, the dust is going to start to do other things than just glaciate the mixed phase clouds. And with that, I'm happy to take any questions.
Questions for Paul?
Well, nice talk, and I think I understood it a little better this time from when you presented in the Polar Cloud Collective. I was really curious about this result about the direct effect, and I wonder, given that you're getting so much response from the direct effect, what would happen if you seeded in the summer? And would you potentially get an even bigger impact from the same amount of mass seeded?
This is actually, so the answer is not so easy. So it depends on what size of aerosols you disperse. In that case, it's accumulation mode mineral dust. So it's going to scatter more than it's going to absorb the long waves. I mean, the net effect is going to be a net cooling in that case. But I mean, you could argue that in the case of real dispersion of mineral dust, the aerosols would likely be larger. So I'm not sure that I can confidently say if you do MCT during summer, you're just going to have a net cooling. I mean, of course, you're going to have interaction with the clouds, but then it's completely different processes. Yeah.
Thank you. So next up is Joseph Ko from Columbia University, who's going to talk about ice microphysics schemes.
No, actually.
Top on your point.
Okay.
Forward.
Got it. Thank you. Hello. Thanks for having me. So my name is Joe. I'm a postdoc at Columbia, also part of the LEAP NSF Center. And this work is in collaboration with Hugh and Truda from NCAR here, as well as Marcus and Kara at Columbia. And I'll be talking about this work in the context of microphysics, but I hope that you'll find that some of the things I discuss are more broadly applicable to PPEs or perturbed ensembles and parameter estimation overall. So this is just kind of a big picture view of what we do with perturbed parameter ensembles. Essentially, you run a bunch of simulations for whatever phenomena you're interested in. For us, we're focusing on in situ cirrus clouds. And then we have a bunch of different inputs that you want to vary. For us, these are the parameters within the ice microphysical parameterizations. And then you look at how this perturbs the output. And then you would fit some kind of emulator of your choice, some regression. In our case, we just use a neural network, and you map the input parameters to the output that you're interested in. And then this allows us to do some downstream tasks that are listed here, such as sensitivity analysis, parameter optimization, quantification of uncertainty, as well as detecting some structural error. And just a big picture overview of just microphysics in general, or just any parameterization, right? You want to know what happens between time t and t+1 for whatever state of this subgrid phenomena you're trying to parameterize. And more broadly, there's two different types of errors. One we call structural error, and these are the uncertainties associated with the functional form of these parameterizations. And then two, the parametric uncertainties associated with these unknown parameters, theta. So for our experiments, what we did was for the ice microphysics parameterizations, we looked at two different structures. One is a more traditional ice microphysics parameterization where there's a discrete separation between the ice and snow determined by this threshold called the DCS parameter. Essentially, when the ice turns a certain size, it's automatically just converted to snow. But we know that this is not really physical, and there have been there's another more recent parameterization we would call unified ice on here, where there's just one class, a single class of ice, and we don't have this artificial partitioning between ice and snow. So these are the two structural variants we're looking at in our PPE. And then for the parametric uncertainty, we have, I won't go through this list, but 5 different parameters within each of these structural variants that we will vary. And what we do is we basically, for these 5 different parameters for each of the variants, we will take a Latin hypercube sampling within this high dimensional space, and then for our case, we have 500 members of using the NCAR single column atmospheric model, or SCAM. And then, like I mentioned earlier, we fit an emulator from the parameters to the output that we're interested in. And then we can do these tests here, which I'll discuss a little more coming up. So specifically, I'll be talking about the Spartacus campaign case study, which is an in situ cirrus cloud case over the Great Plains of the US. And on the left here, we're looking at some of these structural uncertainties that I mentioned, where the red and the blue are those structural variants of the microphysical parameterizations. And from the top left, that's ice water path, and then precipitation. And the second row is long wave and short wave cloud forcing, and the bottom is total cloud cover. And we see for some of these output that these distributions are not even overlapping, like the mean precipitation in the top right. And this is purely due to these structural differences of the ice microphysical parameterizations. And for these parametric uncertainties, we can essentially characterize how sensitive the output is to these different parameters that we varied. And what we did here was use something called the Sobel sensitivity. Essentially, it quantifies how uncertainty in each parameter contributes to the total uncertainty in the model output. And I'm just showing 2 different examples here with the ice water path on the left and long wave cloud forcing on the right. And this is just to illustrate how now we can kind of diagnose more closely how these parameters are affecting the output that we might be interested in. And what the different colored bars are showing are these both the indirect and direct effects. So in the blue are the direct effect of these parameters. The orange is showing the total effect of these parameters, and then the green is showing the difference, which is the secondary indirect effect, essentially the interaction effect of these parameters on the output. So that's all good and well, but what we ultimately want to do is constrain these parameters with observations. So I already kind of explained these first 3 steps, but then how do we do the last step, which is optimizing the parameters to the observations that we might have. And essentially, one question that we asked is like, what should this Z be? Z being the statistic or metric that we're trying to optimize to. And this is where we started experimenting with latent metrics using machine learning. And I'll get a little bit into that. So you can think of this as a 2-stage process, where first we're learning this condensed Z metric with the data using some kind of algorithm of your choice, like dimensionality reduction, some linear decomposition, or ML-driven compression. And then you optimize on that lower dimensional representation of the output instead of some crude metric like the mean or standard deviation. And then in step 2, you'd use that with some kind of random walk, like the Markov chain Monte Carlo, MCMC, and then you converge into the posterior distributions of your parameters that you're interested in. So, so what we did for our experiment was we, as a baseline, used PCA to find the first 32 linear decomposed components of the output. And this is like on the order of 10, we're reducing from the order of like 10 to the 5 in dimensions to 32 components. And then second was using a variational autoencoder. You can think of this as a nonlinear dimensionality reduction method. Essentially, the encoder and decoder are just two different neural networks with the bottleneck in the middle, and you can prescribe how big that bottleneck is, and we use a Z dimensionality of 32 to match the 32 principal components, so we can have a side-by-side comparison. So now just getting on to the experiments with a perfect, like a perfect known truth experiment, where we select one of the members of the ensemble as our known truth, and then what we're showing here is the posterior distribution of these 5 parameters using the crude statistic of a mean. And then here on the middle and the right is using PCA components, and on the far right, the variational autoencoder latents. So you see that the median of the posterior distribution is a lot closely aligned to the solid blue, which is the ground truth, and also the 95% credible interval, which is like a metric of kind of uncertainty. That uncertainty is getting constrained a lot more, and this is just a closer view comparing the mean to the VAE, just so you can kind of see a little bit better. And the scale of the axes are kept the same, so you can really see how that uncertainty is being shrunken a lot. So this is, of course, just an experiment, but it's very encouraging. And the next step we want to do is actually incorporate real observations. And we haven't done that yet, but because that's a little challenging with the single column model, because there's like a big scale discrepancy between the observations for like the ground-based radar and like, 100-kilometer scale of the single column model. So we have to do some sub-column generation so that those comparisons are apple to apple. But just to show, to mention that we're working on that for our next stage. And the main takeaway for this is that perturbed ensembles can be used to quantify uncertainty and constrain parameters, and using emulators and latent metrics can help. And hopefully this will be, get the point that this is more broadly applicable than just ice microphysics. Thank you.
DD model, or are you going to stay in single column?
Yeah, so I think the idea is to use a single column model to like shrink kind of the space of plausible parameters, and then we want to use those, the subset in like a fully coupled model, for example. Yeah.
Next up is Chen Liu from CU Boulder, who is going to give us an update on karma.
No. You point with the other one. Okay. Okay, thank you. Hello everyone, this is Chen Liu from CU Boulder. I work for Brandtune, and I'm also a visitor at NCAR ACOM, whose host is Simon. I'm going to talk about the new insight from a sectional cloud microphysics model, which we call Karma Cloud in the CESM2. We use different cloud microphysics between the current cloud model, which hereafter MG, and the Karma Cloud. For example, MG assumed 2 size modes for cloud and rain. Sorry? Okay, 2 size mode for cloud and rain separately, and it uses Bank microphysics. While Karma Cloud predict size distributions within spanning from cloud drizzle cloud, cloud drizzle and rain in one single size distributions. From the mass size distributions, we find MG separating cloud and rain miss significant mass from 20 to 100 microns, showing these panels on the left. So those particles could be some large clouds and some drizzle. And on the right panel, we have the same plot, but with the y-axis in log scale. So from this figure, we find MG miss some particles smaller than 1 microns, and also miss some large particles greater than 1 millimeters. For the ice particles, MG parameterized snow mode, which is larger than karma, like the figures showing the panel on the left. MG assumed size mode is larger than karma, and the same in the log scale on the y-axis. And we also find MG miss some particles greater than 3 millimeters, so those could be some large snow. From the 2-degree monthly output, we find local particle size distributions in karma cloud show cloud, drizzle, and rain modes in different regions. So in karma cloud, they are highly variable in different regions, showing the panels on the top and on the middle, and the panels in the bottom shows those samples in different regions. So, for example, we have cloudy regions over the Asia and we find one single mode smaller than 30 microns, so that's cloud mode. And if we look at some other regions, like the drizzling regions, in the remote oceans, we have significant drizzle mode in the size range from 50 microns to 250 microns. And if we look at some other regions for raining, and we also have the third mode in about 250 microns. Those are the raindrops. Karma Cloud also have some insight on satellite observations, like for MODIS, which is not sensitive to particles greater than 30 microns. And from our simulations, we find about 16% of cloud mass and about 31% of total mass in liquid particles greater than 30 microns is missed. Showing the figures below, we find, for example, if we cut off karma cloud like here for the 30 microns, and we find there about 69% of mass contribute to the total liquid particles. So that means about 31 is missed above 30 microns. If we include particles up to 50 microns, which is the definitions of clouds in the AMS definitions, it contributed to 85%. So those particles could be missed by MODIS, like it cannot detect particles up to 50 microns. Those fractions could be 16%. Besides, we also find if we include particles from cloud to drizzle, which up to 250 microns, the total mass contributed to about 97%. That means only 3% of mass is remaining in the raindrop sizes. MODIS effective radius is sensitive to cloud size distributions and also the assumed gamma distribution. Showing this figure, we have the probability density functions of effective radius over the ocean on the left and over the land on the right. We have karma in blue, MG in green, and MODIS in orange. In general, we find if we cut off karma analysis to particles smaller than 30 microns, it is agree with MODIS data around 14 microns over the ocean and about 12 microns over the land, while MG has some biases compared to data. However, if we include particles up to 50 microns in karma cloud, we find there are a lot of grid box have particles greater than the observations by MODIS. We find karma raindrop diameter is within the uncertainty of GPM data. Showing the panel on the left, we have the PDF of raindrop diameter. So karma and GPM data is consistent with the peak raindrop diameter around 1 millimeter. And from the vertical profiles on the right, karma is within the uncertainty of GPM data. We find karma simulated global albedo and liquid water pulse is very sensitive to aerosol cloud interactions. On the top, we have albedo in three cases, and on the bottom, we have cloud liquid water pulse to 3 cases. And the blue bars has comparable albedo compared to series data around 0.29. To reach this case, we need 2 adjustments from karma cloud. One is to tune the aerosol activations, and it decreases a little bit relative to the case used in this study. We also find it's very sensitive to cloud coalescence kernels. So in the red bars shown here, the albedo is lower than data. But here we use the laboratory data for coagulation kernels, which is observed in the early of 1980s. So this sensitivity test suggests that there might be something uncertain in the observed coagulation kernels here, which has not been measured for more than 40 years. And it could also mean that our model has some numerical diffusions, so we might need to improve the algorithm in the future. So here's some key insight conclude for this talk. We have developed a sectional cloud microphysics model in a global climate model. And karma cloud predicted size distributions have greater mass between about 20 to 100 microns than MG. On global scale, karma cloud mass size distributions has about 16% of cloud mass and about 31% of total liquid water mass for particles greater than 30 microns. And MG and the MODIS liquid effective radius is sensitive to the weights of cloud size distributions, which we find highly variable in different regions. And lastly, global albedo in karma cloud depends on aerosol cloud interactions, and we have to adjust 2 parameters to make the model agree with data. Thank you.
Hi, nice talk. I like the comparison between karma and MG. I want to know, is there any computational power increase in comparing karma with MG?
Yeah, of course. So here's the computational cost comparison between karma and MG. So the blue lines are karma and the green lines are MG. And so notice that the y-axis is different on the left for karma and on the right for MG. So basically, MG is 10 times that of karma cloud, if they look the same in this figure, because the y-axis is different. So in general, we find mg is 10 to about 12 times that of mg. So it's pretty expensive, but we find it's mostly due to the complex of cloud microphysics.
Thanks so much. So it's hard to compute supersaturation at coarse resolution, long time steps, subgrid scale, updrafts, that kind of thing. And I'm wondering if you think that's a big problem or an obstacle for getting accurate results out of a bin type model like Karma. Or is that just not, you don't have a big sensitivity to the calculation of the supersaturation?
Thank you. That's a good question. So in Karma, we have a sub-step, in which way we can reduce the time step. So currently, the time step in Karma is 10 minutes in the mechanic loop, consistent with cloud. And we have a sub-step which can further decrease the time step, which avoid the supersaturations in one grid box, changes the sign. So if the sign has changed, we further automatically decrease the time step. So in that way, we avoid the supersaturation to have some like change the sign or change too much in one time step. And we also use the same configurations in Karma and MG. So we activate aerosols from MEM4. So those all settings are the same. So hopefully that will also answer part of your questions.
Thank you.
Thank you.
Thanks. Next up is Hyun-Jan Sung from Pujong National University, and he is also going to talk about microphysics. You point with the top one and then back and forth here. Can I see the slide? Pardon? Can I see the slide mode? No. Yeah, like that. Just go back and forth. Sorry, can I bring slide? Yeah, sure. Okay, sorry. Good afternoon. I'm Han Jun-sung from Buyong National University, and today I'll talk about the impact of heavy-weighted ice microphysics on high-latitude cloud properties in CAM6. First, why focus on ice crystal habit? In observation, ice crystal takes various shapes depending on temperature and supersaturation. Recent ALS studies of Arctic mixed phase cloud shows that this habit changes the liquid and ice property. However, the bulk scheme used at larger scale simplifies supposed ice shape as a fixed habit for efficiency. W6 assumes a single bullet and Morrison's MG2 assumes spheres. It's a reasonable simplification at the time. In this work, we just try to consider the effect of various habits. We bring ice crystal habit into the MG2 scheme by weighting, as shown on the right, rather than resolving each habit explicitly. Oh, sorry. We weight by the fraction of each heavy column sphere, plate, and bullet rosette, and see it over the high latitude where mixed patch cloud many exist. Before adding the habit weighting, let me establish our baseline. MG2 was updated in 5 ways in PUMAS. Of these, we adopt the two that concern ice nucleation and number, the ice number limiter and the reduced aerosol number over ice nucleation, because they directly affect the ice number. We apply these to MG2 and treat it as our control. This is the main approach of the heavy weighted ice. We leave the MG2 size distribution unchanged on the sphere diameter axis. The fractional diagonals from temperature and surface saturation. Inherent growth ratio in channel length applied in the warm region, and the barely and hard diagonals in the cold region, and reverting the MG2 default below under minus 40 degree. Small ice below 60 micrometer is treated as sphere. Here is the experiment design. We conduct for experiment. Default is the standard CESM2 with Chem6 MG2. MG2 some sphere, but for velocity considered as a known as an empirical bulk cloud ice, and control as the two PUMAS correction, our baseline. The next two are designed to isolate the heavy defect. The sphere run is the same as control except the sphere for velocity, and heavy weighted. The heavy run is the heavy weight ice applied over minus 40 degree, where capacity and ball velocity and effective radius are all heavy weighted. And this let us decompose heavy sphere run minus control is the ball velocity reference change, and the heavy weighted minus sphere is the purely heavy weighted effect. And the heavy weighted minus control is the combined response. All runs conducted as a FHISCOM set during 2006-2012, and the analysis on DJF. Now the result, default shows a well-known Chem6 bias over the high latitude. Cloud ice is too little over the Arctic, and the liquid is too much. And in the control, this pattern quite reduced, but increased ice over Atlantic and Bering. And the heavy run shows slightly more increased ice over the Arctic and reduced over the two sea Atlantic and Bering. And the liquid showed differently over the North Atlantic, showed the increase of liquid and decrease over the West Siberia. And next term row shows cloud fraction and the surface downward long elevation. This liquid difference pattern is same to the cloud fraction. Control shows rather about 30 watt per meter square over the Siberia. It's Siberia for downward long elevation. The heavy run shows quite reduce of this, and we focus on these two areas, Siberia and North Atlantic. here is what the weighting actually produced in our two regions. And this is also determined. First, temperature is different. North Atlantic start with above freezing, and the West Siberia start above about minus 10 degree. So in the warm region, these two areas has a different weight and go higher above middle level. Cold region shows slight difference and further goes higher below under minus 40 degree, composed by Multisan Getman 2. The next is the cloud fraction at the West Siberia. Ice shows increase at the high but decrease at the middle. And at the North Atlantic shows just decrease at the middle level. And the slight increase bottom. Liquid is deeper, the heavy land decrease more than control, but increase liquid and North Atlantic. This different pattern maybe comes from maritime and continental. We changed many things. So check the region. We compare that to the sphere line. In the decomposition, the sphere line shows a reduction of high-level ice and increase at bottom. And the heavy line shows opposite pattern, but liquid is deeper. Liquid decrease by spherical considering, and heavy also decrease over the West Siberia, and but over the North Atlantic, it shows it caused mainly spherical change, and considering sphere also. Sorry. Over the North Atlantic, considering spherical ice mainly increase of this liquid, this area liquid. As a summary, we add the heavy weighting to Chem 672 and change the capacity for velocity and effective radius by weighting, and consider depends on temperature and supersaturation. And sphere pulse decomposition reveal of maritime and continental contrast. The North Atlantic liquid response is the for velocity difference, while heavy may reshape the ice profile. And heavy rate long evaluation is regionally reduced, controls the positive bias over the West Siberia. And this is an ongoing study, so please many comment welcome. And next calls I call anchored pure heavy run, and further I want to conduct heavy growth in MG2 as similar Ishmael. Thank you. Are there any questions? Thank you. The next up is Brandon Duran, who is going to talk about diagnosing the liquid water path adjustments in Chem 6.
Okay. Great. Yeah, hey everyone. My name is Brandon. I'm a PhD student at Scripps. And today I'll be talking about diagnosing the liquid water path adjustment in CAM6. And thanks to all my collaborators listed on the screen. So I want to start out with these two figures that present somewhat contradicting results. And hopefully by the end of the talk, I'll have resolved the differences between the two. On the left, this paper from Ed Griesbert showing that we can predict the magnitude of the liquid water path adjustment in models just knowing the absolute change in liquid water path in CMIP5 and CMIP6 models. So there's just this linear relationship that should give us this nice scaling. But then this paper from Song and a few others at the University of Wyoming showed that actually increasing, an increase in the change in liquid water path with the addition of aerosols in CAM6 did not result in increased cooling from aerosol cloud interactions. So these two results are kind of in contrast with each other, and they're going to motivate these three questions that I hope to answer. So first off, should we expect the liquid water path adjustment to scale linearly with the change in liquid water path? Is radiative saturation, which is found in Song's paper, evident in variations in the strength of the adjustment? And can we predict the simulated adjustment from simple cloud properties alone? So to answer these questions, we have a perturbed parameter ensemble using CAM6, where we've perturbed 19 different aerosol and microphysics parameters in the model. And so we have a total of 162 simulations, fixed SST, atmosphere only, with pre-industrial and present-day aerosol forcing. And the way we're going to diagnose the adjustment is using these joint histograms of liquid cloud fraction that are generated from the MODIS satellite simulator. And what's really important here is that these histograms give us information about the distribution of liquid clouds, not just a grid mean quantity. So the first result I want to land on is we find that the liquid water path adjustment in CAM6 is driven by fractional changes in liquid water path. So what I'm showing here is just the global mean change, fractional change in liquid water path across these 162 simulations plotted against the global mean adjustment. And what you can see is this nice relationship that emerges where the bigger your fractional increase in liquid water path, the stronger cooling you get from the liquid water path adjustment. And importantly, we find that the mean state liquid water path and the change in liquid water path alone do not explain this spread in the PPE. And why is this the case? We can kind of look at this very simple relationship between the liquid water path and the cloud albedo. And so essentially what you can see from this concave profile is that cloud albedo becomes less sensitive to increases in liquid water path as mean state liquid water path increases. Put another way, the same change in liquid water path perturbs cloud albedo more efficiently for thin clouds rather than thick clouds. And so to answer this first question that we had, should we expect the adjustment to scale linearly with the change in liquid water path? We find that the answer is no, but I'm going to put a pin in that and return to it at the end of the talk. And so now that we have this nice relationship at the global scale, we wanted to understand if we could bring this to a local perspective. Can we predict the adjustment spatially just from simple cloud properties alone? And so we start with just this simple expression relating the liquid water path of the cloud to the cloud albedo. And what we can get is we can get a relationship for the liquid water path adjustment that is based on three variables. How much liquid cloud do you have? What is the cloud albedo of that liquid cloud? And what is the fractional change in liquid water path with the addition of aerosols? So we have this very nice clean expression just based off simple cloud properties that we're going to seek to apply in this PPE and see if we can predict the adjustment at the local scale. And so this is the results. So to orient you, the top left is our truth diagnosed from the joint histograms. The top right is when we apply that simple model that I just showed you at the grid cell level. And then the panel C is the difference plot. And so there's two important notes. First off, if you look between A and B, our simple model actually does a really good job at capturing the spatial pattern of this response to aerosol in CAM6. But notably, if you look at the difference plot, it overestimates the amount of cooling we get almost everywhere. And that's reflected in this bottom right panel, which shows that the simple model predicts too much cooling for a lot of the ensemble members. And so, returning to this question of can we predict the adjustment from simple cloud properties alone, we seem to be able to capture the spatial pattern that is observed in this PPE, but we can't get the magnitude right. So one of the key reasons we've found for this is that the use of grid mean cloud properties results in an overestimation of how susceptible these clouds are to liquid water path perturbations. And so the way to interpret what we're looking at on the right here is essentially, since we have these joint histograms of cloud fraction, we know how the distribution of liquid water path is shifting at each grid cell. And so what the blue line is telling you is that in cases where the shift in the liquid water path distribution is not uniform or not translational, the simple model performs poorly. And that's because we're relying on grid mean cloud properties rather than having information about how thick clouds and thin clouds are responding differently on the subgrid scale. And I just want to point out that this was something that was found in an earlier paper where looking at MODIS observations, basically using grid mean cloud properties resulted in the same type of overestimation of cloud susceptibility. And so the last thing I want to end on is there ever a case when the liquid water path adjustment should just depend on the change in liquid water path? So that result that I started with from Ed Griesbert, when does that linear scaling emerge, or does it not ever emerge? And essentially what we find is that the reason we don't see that relationship in the PPE is because we've generated such a large diversity of mean states. So we're perturbing a lot of different parameters such that we have some simulations that have almost no liquid cloud in the mean state, and we have some that have a lot of liquid clouds relative to observations. And so if you break down the whole spectrum of the PPE into slices where you essentially have this roughly the same amount of liquid water path in the base state, you get this reemergence of this linear relationship. And something to highlight is that if we go back to thinking about that concave curve between the liquid water path and cloud albedo, that the steepness of that curve is sharpest for low liquid water path, because those are the most susceptible clouds. And so the way that that pops out in this plot is that this purple line, which is showing the group of ensemble members that have the lowest amount of liquid water path in the mean state, result in a large variation in the cooling that you get from the liquid water path adjustment, even over small perturbations. Whereas when you shift to this light green color, those are simulations where your cloud albedo is very saturated in the mean state. And so even though you generate large variations in the change in liquid water path, that does not translate into large variability in the liquid water path adjustment. And so returning back to this question that I asked earlier, should we expect this linear relationship to emerge? I would say that it only emerges if you're focusing on simulations where the mean state is quite similar. Once you build this into a PPE framework where you've generated a vast diversity of climates, you wouldn't expect this relationship to fall back out. And then finally, is radiative saturation evident in variations in the strength of the liquid water path adjustment? I'm going to say the answer is yes. And the way to think about this is that you can get the same amount of cooling in different simulations for different changes in liquid water path just because of variations in the mean state. So with that, I'll leave these 3 questions that I started with on the screen and hopefully the answers to them. I'm happy to take questions.
Very interesting. I'm just curious, that really smooth curve of the sensitivity of albedo to LWP looks like analytical. How do you calculate that, or how oversimplified is this?
Yeah, so like this curve is just, it is analytical and it's just assuming like a certain effective radius So this is more of a schematic in a sense. But in terms of, like, I guess it's more that it provides the framework of, when you go back to this final plot, basically, right, like these purple groups, or the ensemble members in the purple group, are somewhere on that very sharp kind of part of the albedo liquid water path curve, and that's kind of not really sensitive to how you define, right, that shape. So you could alter, the effective radius, and the general profile of this concave relationship still should emerge. Yeah. Thanks.
I like the nice, simple physical reasoning in it. I'm wondering if you, say, deleted half your parameters and redid the whole, all the analyses, would you get the same answer? Like, is it sensitive to which parameters you're perturbing?
It's a good question. I would somewhat assume so, and the reason I say that is we perturb the exponent on the cloud droplet number in the warm rain autoconversion scheme. And that, so what this plot is showing is at every grid cell, what parameter explains the highest variance in the adjustment across all these simulations. And the blue color here is that ND exponent, which is controlling the droplet number response in the autoconversion. And so I think if you shrunk the range over which you perturb that parameter, this graph would look different. I think the general relationship would still hold in terms of fractional changes explaining the adjustment, but the range of cooling that you get would not necessarily be the same. And I guess another way of thinking of this is you could run these simulations also using CAM7, and where those points fall on this grid would be smaller, because the autoconversion process has been slightly tweaked. But yeah, hopefully that answers your question. Happy to chat later too.
Then next up is Rich Neal, and he's going to talk about deep convection sensitivities in CAM7.
Okay, thanks, Peter. Thanks for foolishly giving me a slot. Yes, that's UX. All right. So, given we're nearly there with the CAM7, I thought it was a good opportunity to do some simulations and confirm, or not confirm, the role that convection and the changes we've made has been in the model. So, really two and a half things I'm looking at is what was the convective response to changes in the vertical resolution? L32 was, L32 was CAM6, L58 was CAM7, and we have a couple of other different resolutions that we'll look at, and I'll explain why soon. And basically, we had a couple of motivations. Other people have additional motivations, but the reasoning was to enable better resolution of propagating gravity waves, and also aspects of resolving the boundary layer. And then we found out there were problems, and so we implemented some modification to ZM to address this. And there are some combined issues when you put these two aspects together. Vertical resolution in the model, where are we? Where were we? So we were at CAM6 around 32 levels, pretty coarse, so this is level thickness around the x-axis. And progressively, in a couple of steps, we went to the CAM6 Plus. No one called it CAM6 Plus, but essentially it was 48 levels, increased resolution through the troposphere, and then 58 levels through into the boundary layer. And then my green one here is a CAM-X, CAM11 or something. But it's a test harness to look at the sensitivities. Essentially, the great sensitivities that we see relate to the resolution of these near surface layers, and we can see what they are in meters here. So we can say we went essentially from around 130 down to 43-ish meters in terms of the thickness of those lowest levels. So, and the second piece is we had to make these modifications of convection. I've been through this before. I won't belabor the point as I've shown before, but I'll just essentially say we made these changes in the Zhang-McFarlane deep convection, which was very level dependent, very level sensitive, and intended to kind of bias the properties of the atmospheric column near the surface. And we made a modification that kind of mix these properties over a certain length scale. It happened to be some fraction of the PBL height. That's all you need to know at this point. To demonstrate these sensitivities as they exist right now, I have a number of single column simulations. So that's over 3 regions here. So we have a kind of continental convection arm site, a couple of sites here. These are the typical cases that people use, and then a couple of tropical Atlantic Pacific cases. So essentially, lots of words here, but I tested all of these resolutions, vertical resolutions, with essentially 3 versions of the model. Where we are right now, CAM7, essentially where we were, so it's not quite where we were, but it's the physics of CAM6. And then this is just backing off, essentially, of that necessary change, and you'll see why it was necessary, essentially. I'll show 2 or 3 of these, and it's essentially just to illustrate this sensitivity. So what I'm showing here, the 4 case studies, so 2 ARM case studies here, and a gate and a Toga core one. The color is the essentially the versions of the model, CAM6, CAM7, and then this version that essentially backs off to a CAM7, a CAM6 configuration with deep convection, and the symbol sizes are the resolution. So you look at this for precipitation and think, great, there's no resolution sensitivity. But of course, precip is easy to get right in single column simulations. If I now go something like CAPE for all those type configurations, and basically, you know, what to take home from this is CAM7 is where we are right now in the orange. So for each of these case studies, for CAPE here, convective variable potential energy, there is not too much sensitivity in these particular cases. Whereas if we go to what CAM6 used to be in blue, and also the piece of that puts CAM7 back to CAM6 convection in green, we can see there is significant sensitivity. And this is what we were trying to remedy with this convection change, essentially. So, and you know, and the blue and green comparison essentially is to say that it's just this, really is this delta associated with the new part of the convection scheme. That's pretty bad, and so that's moderated that. You know, the main piece of why this was kind of bad was if we were to look at the mean forcing, the mean temperature tendencies near the very surface in each of these cases, over the period of many weeks of these IOPs, we were getting very strong in all the cases, essentially, apart from R95 of 40 Kelvin per day from the deconvection scheme. So that was not desirable. So that's single column, and now look at some CAM simulations. So in a similar vein here, I'm trying to populate the kind of phase space of model version and vertical resolution. It's a little bit more complicated here, but essentially now we're looking basic CAM7, which was 58 levels, is 58 levels. I'm trying a 32 level version. CAM7 without this ZM boundary layer modification, which we know is the lion's share of this change. And I want to look at the level sensitivities that still exist there for these 3 levels. And these following ones are just kind of a step change in the confirmation that we're looking at CAM6 physics. So it's CAM6 as it existed in reality back in essentially a CSM 2.2 tag. And then this is what we use for CAM6 within CAM7. A lot of complications there, but hopefully in the next few slides will give you an indication of what I'm talking about. So the next few I'm showing, top line in each of these cases is going to be up. Oh, sorry, it's because I haven't got my glasses on, so I'm standing back at old man distance. Apologies. It'll just be blurred for me then, that's fine. So the top one is trim observations, 05 observations. The next line is a confirmation that we're, you know, comparing the same thing for CAM6 in 7 and in CAM6 to the physics, very similar. And then the bottom 4 are kind of the key ones, which is what happens to precipitation if we in CAM7, and then CAM7 32 levels. And then if we do the same there, but we turn off this boundary layer modification. And a little complicated, I agree. But essentially, There is a vertical level sensitivity, but that level sensitivity is greater if we do not have this boundary layer pulsar modification on. So just to reiterate that in the bottom right. Mean precip is a little boring, and it essentially does not show some of the major reasons that we did this. And there are some good things, some bad things. Overall, the precip is not quite as good as Cam 6, I think, with the final Cam 7. But if we start to look at things like variability, so standard deviation, exactly the same setup here, just focus on, really the bottom 4 plots here, and we can see that when we added, if we were to add, for example, Cam 7 without this boundary layer pulsar modification, we haven't done that, but that is, we could have done that with just 58 levels. We added this, and we get real serious problems in terms of excessive variability. Now, there's 2 pieces to that, which is, if you just do that and go back to 32 levels, it looks pretty good. Don't use that. But if you go back to Cam 7 with this boundary layer modification, then that is better. It's not. I'm not saying it's like as good as observations, equal to observations, but there is a moderation, and it's essentially the version we're using right now. And so again, just to reiterate, there is a level sensitivity and a PBL parcel use sensitivity. You can go even further, what you use models for. This is kind of like the 99th percentile. And I think it's good news, really, because Cam 6 was a little too weak in those most extreme events, compared to TRIM at least. Cam 7 may be overplaying it, but I think on the equator and south of the equator, it really is an improvement, I think. But we did not want it to go without this boundary layer modification. So that's a good summary there. If we were to jump another way of viewing this, if we're looking at the PDF for precip, and this is the PDF amount, so what is the relative contribution at different precipitation rates that we see along here? So this is around about 1 through 100 millimeters per day. And we can see, just to reiterate, this blue one here is this going to 58 levels without this boundary layer modification. We can really see this is somewhat of an outlier compared to all the others. It's too excessive contributions over land and over ocean, particularly over ocean from these precipitation rates. But the red is where we are, which is Cam 7, 58 levels, and on the whole, it probably is, if you believe TRIM, it's probably one of the best compared to interim versions back to Cam 6. So I think we're in a good place for variability, better than we've been in that we're kind of mapping better to these higher precipitation rates. What's the next one? And a couple of things here. Let me start on the right. And so there are good things, bad things. One of the things that has been noticed is it's very obvious, I think, is convective precip depth, cloud top depth, is probably too shallow. Again, this blue 58 levels, Cam 7, no modifications, a huge outlier. We would have like really deep convection all the time. And that goes back to that high cape that we saw in the single column model. And then the red arrow there is like, this is where we are with Cam 7. And it is below, the kind of frequency of having the mid to low level cloud depth. So that is a concern. That's been noticed in a few things, QBO, for example. Interestingly, if you look at the PDF of 500 millibar height and focus on the simulations that have high vertical resolution, those that are Cam 6, there is a significant shift in, if you look across through the tropics, what the distribution is of the vertical velocities at 500 millibar. So there is a very tangible response to changes in stability, changes in mass flux associated with deconvection, particularly in this region. We can see here, this again, just another reflection of how bad approximation, how bad a model the L58 Cam 7 without this convection modification would have been. Last slide. One thing we've noticed recently is, gradually seeing that we've had surface fluxes, surface latent heat flux over the ocean are excessive, and they've always been kind of excessive, positive bias, but going from Cam 6 to Cam 7 really was an increase in the bias, depending on what you determine to be observations. Let's just be generous and say this one here, which is reanalyses. We kind of doubled the bias from there, going from the kind of tan, low tan color to the red color. And if you look through these interim simulations, you can kind of see the changing vertical level, and obviously the lowest level thickness is really the the lion's share of the change there. And I don't think we've really understand exactly that sensitivity. We did some experiments, but it wasn't clear exactly how to remedy that or exactly the source of that. So, and there is some due to this boundary layer, this ZM parser modification too. So I'll stop there. I'll leave that up. I'm hoping we can make some time up. So thanks.
Thank you for the nice talk. Can you tell us a bit more about how we determine the height of the PBL for this ZM parcel?
It's a scaling factor. I went through it quickly. It's a scaling factor of the boundary layer depth. So you look at the boundary layer depth and you say, what fraction of that boundary layer depth do I wish to mix the parcel properties in order to determine the parcel. Sorry, in order to determine the kind of launch parcel properties. It can be anything, but like in CAM 6 and before, it was always the lowest model, not always, but most of the time over the ocean, the lowest model level properties, which if your level thickness is like that compared to like that, that's a bad vertical grid dependency in the model that should not be in there.
You left out some of your successes with getting the latent heat flux down. Do you quickly want to mention that?
Do you want to give me another 12 minutes? Yeah.
Despite that it didn't work in coupled.
Success, I mean, 10 seconds is the vertical. So over the ocean, it's a Mononobakov-based flux calculation for latent heat flux, and sensible and turbulent momentum fluxes. And there are some approximations that go into that. That are kind of based on the surface value, the model's lowest model level values, and so it's pretty coarse approximations, and there's a way you can kind of approximate that differently to have big movement on those latent heat flux biases by tens of watts. Yeah.
So next up is Meg Fowler, who has the second longest title in this session, so I'm not even going to try and read that at this late in the day.
Thanks, Peter. You hit the button? Okay, awesome, thanks. Okay, well, we made it to the end of the day. Congratulations, gold star for everyone in the audience. I have a very long title. In short, the idea is we're taking a look kind of behind the curtains of CSM3 development to look at how we evaluate the El Nino Southern Oscillation, or ENSO, during development simulations. And I just want to take a second and acknowledge my co-authors who are listed here on the screen, especially Rich Neal, who really was the driving force behind a lot of this work. So I realize this is somewhat preaching to the choir, but I like to start these talks with some emphasis on why we care so much about ENSO. Ultimately, the reason I care in particular is because it is such a dominant mode of internal and interannual variability within the Earth system. So this is a nice figure from Alizada in 2023, just highlighting in given ENSO phases, whether warm, El Nino on top, cool, La Nina on bottom, where do we see warm, wet, dry, and cool anomalies? This is really critical, right? This drives a lot of our predictability when it comes to looking at subseasonal, seasonal, and multi-year predictions. So to give you a bit of an idea of where we stand right now with climate models simulating ENSO, it's not the prettiest picture in the world. There's some well-known biases. So the ENSO amplitude continues to be either too strong or too weak in most models, so a bit of a Goldilocks situation. We can't get it just quite right. ENSO diversity is limited. SST anomalies also tend to extend too far into the West Pacific, so the spatial pattern of ENSO can be a challenge. And all of this is complicated by the fact that we have relatively short observations. And I want to highlight this, as I think it's shown nicely in Wittenberg in 2009. What you're seeing in the figure here is a bunch of colored lines. Don't worry too much about what they are. They're the Nino 3 spectra. But what I want you to pay attention to is the spread. So if you look at the panel with all those red lines, those are 20-year time slices of a long-running CM 2.1 simulation. And what you'll notice is that you get a lot of different answers depending on which 20-year slice you're looking at. If you look at 100-year slices in green, there's still a fair amount of spread around that center black line. And it's not until you have 500 years that you start to really hone in on the power spectra of Nino 3. And we'll come back to this throughout the talk. So the question I want to pose is how can we evaluate ENSO characteristics during the development of a coupled model, in particular CSM3? This is a challenge. When you're developing a coupled model, you're not necessarily running simulations for 500 years at a time in order to test how things perform, especially for something as noisy as ENSO. So today we'll take 3 parts to the talk. 1, we'll identify the metrics that describe ENSO in observations to give you a baseline. Then we'll assess the variability of those metrics in simulations of varying lengths. And then we'll get to the fun part, tracking the evolution of metrics across CSM3 development simulations. So starting with observations, I want to give you just 3 individual ENSO metrics. We looked at a few more, but for the purposes of today, we'll just focus on these. So this is drawing on Hadley SST, and what we'll look at first is the ENSO amplitude. So this is showing you the seasonal cycle of variability in SST anomalies in the Nino 3.4 index. And what I want to do is kind of draw this down into just something more digestible. So from a plot like this, you can come up with the maximum of the Nino 3.4 SSTA variance and the minimum. You can also come up with a mean, but then instead of having to look at a seasonal cycle for every single simulation, you can look at just a series of numbers. Next, we'll look at the ENSO duration, and in particular, I'm looking at the event transition time. So what this plot shows you in observations is the autocorrelation of Nino 3.4 SST anomalies with themselves. And so you're looking at the transition point where the sign flips, so roughly where you might go from an El Nino to a La Nina or vice versa. And observations, this is about 10 months. So again, we'll simplify things down to just one value. And the last thing to highlight is ENSO extent, so how far SST anomalies actually extend into the West Pacific. This is the correlation between Nino 3.4 SST anomalies and then SST at every other point. So the strongest we should see within the Nino 3.4 region in this black dashed box. Good news, that's what we find. And then we can look at the extent of the strongly positively correlated SST anomalies, which is marked with a green square, and the extent of the positive SST anomaly correlation, which is marked in a circle. So hopefully that gives you a broad idea of what we expect to see in observations, but there's an important theme that's come through in a number of talks today, which is the fact that sometimes we need long simulations to really reliably estimate some of these metrics. So what we've done in our case is taken the long-running pre-industrial simulations for CSM2 and CSM1 that were submitted to the CMEP archive. So here you have about 1,200 years of CSM2 Nino 3.4 index. What we can do then is break this up into individual slices, just like we saw in that Wittenberg study. So here I'm showing you 20-year non-overlapping ensemble members, so we have about 60 different ensembles in this case. And looking at the bottom, you can see the Nino 3.4 index for just 3 different ensemble members that I've pulled out. You'll notice they look pretty different. Member 48 has a pretty long-lasting La Nina event. Member 29 has a pretty strong El Nino. And member 3 has kind of low variability across. So it's really important to note that by sampling a long-running pre-industrial simulation, we get some estimate of internal variability. Now, the goal here is to also look across metrics. And so what I want to introduce now is a way of doing that. We've cut up the CSM2 and CSM1 simulations into a range of different years. So 20 years on the left, so you have 60 different ensemble members, all the way up to 200 years, where you have 6 ensemble members. And then a range of different Nino metrics. So these are all on the y-axis, and I'll draw your attention just to the top half because we haven't talked about the bottom half. And the metric I'm going to use so that we can look across all of these different metrics is the coefficient of variation, which is the standard deviation of your ensemble members normalized by the mean of those ensemble members. So big numbers would imply that you have a lot of variability relative to the mean. Low numbers mean low variability relative to the mean. So if we look first at just this Nino 3.4 SST variance annual max, what we find is that in CSM1 on the left versus CSM2 on the right, there was more variability in 20-year samples from CSM1 than there was in CSM2, but they all kind of start to gradually reduce the amount of noise in the ensembles as you move towards longer and longer ensemble members. And if we look across all the different metrics, this is a slide you probably saw earlier in the day from Dave Lawrence, the idea is that some metrics don't really vary much, even if you have just 20-year samples. So if you look at the western extent of positive and strongly positive SST anomalies, these top 2 rows, all the colors are dark blue, so the variance is pretty small relative to the mean. If you look at something like the skew of Nino 3 SST, which again I haven't defined for you, just trust me, there's a lot more noise in that particular metric relative to the others. So this gives us a sense of how long do we need our simulations to be in order to assess ENSO performance. So in order to do that, I'm going to show you just a couple results and a few caveats, but we've decided that we need simulations to be at least 45 years in length. We throw away the first 5 years, that's really the main transient period when you're spinning up the model, so we want to eliminate as much of that as we can. These are all fully coupled simulations, pre-industrial forcing. I will also note it's not linear improvement. This is something that comes up a lot as you look across the timeline of what we've done with CSM3 development. It's not like you can necessarily say 315 follows directly from 316 and it's so much better. Model development is not that simple, right? There's a lot of tests that go into it, whether you're testing different parameterizations, tunings, et cetera. So just keep that in mind. And I'll add CSM 1 and 2 for context. So looking at the monthly NINA 3.4 variance, again, this is the plot where we had the blue bars and you're kind of looking at the seasonal cycle. What I've done here is just reduce that down. So your annual maximum, your seasonal maximum is with a downward shaping, downward pointing triangle, your minimum upward pointing triangle, and the mean in the middle. So CSM2 relative to observations was biased a little high. We tended to have pretty strong seasonal maximums of the NINA 3.4 index SST variance. CSM1 was a little bit weaker than CSM2. Now, if we look across all the different, a subset of all the different CSM3 development simulations, we're moving across time as we move along the x-axis from run 38, very close to the beginning, towards a recent run, run 316. There's some trends that pop out in this analysis. But one of the exciting things to note is that overall, in the most recent simulations, we are back to something looking really good. There were some hiccups along the way. Things got really low, which was a little bit of a concern, to say the least. And then things got really high. Again, a little bit of a concern. This happened when we were doing the club diffusion experiments for anyone of interest. And if you want to talk more about that, I would strongly suggest talking to Adam, not me, just for reference. Vince, many options in the audience. One of the more stubborn biases that we came up against in CSM3 development is really the Western extent. And I want to note this isn't something that we were necessarily setting out to improve, but it is something that was really hard to move the needle on. So here you're looking at the longitude of either that square or circle that I pointed out in observations, the extent of strongly positive SST anomalies, or just the extent of positive SST anomalies. For the extent of positive anomalies in particular, these blue dots, they barely moved during the first 100 or 200 simulations. And that's kind of surprising because there's an entirely new ocean model in CSM3 compared to CSM2. And yet, this is not a bias that responds really strongly to that. There were some encouraging signs for the extent of the strongly positive contour. This is a little bit more variable, which is kind of exciting. But again, I would note that this is a bias that's persistent across previous versions of CSM, CSM1, CSM2 relative to observations, and it's really persistent across most climate models. So it's not really that CSM is an outlier in this sense, just that we haven't solved the problem yet either. So I just want to wrap up. Sorry, I spoke as quickly as humanly possible. So how do we evaluate ENSO characteristics during the development of a coupled model? One thing to note is that it requires accepting uncertainty. Ultimately, you don't have 500 years of simulations in most cases, which means that you have to take into that account when you're looking at which metric of ENSO is most important and which can you reliably estimate. And not all biases respond clearly to model changes. So the spatial extent barely moved throughout the development process, but we saw changes in the NINA 3.4 annual maximum, minimum, and mean. And I also want to note, I've shown you just a couple of metrics here, but one of the interesting things about ENSO is that it's characterized by a number of different metrics. So if you choose just your favorite one, you might miss changes that are happening in another. And so really taking a broad approach, I think, for this metric when you have high internal variability is really key. And with that, I will thank you for your time and happy to chat.
Hey Meg, thanks. That was a lot of work, and thank you for that. It was a great presentation. Good job. This answer might be no, but have you looked at other modes of variability in terms of what's the optimal number of years in ensembles?
I love that question. I have not, but I think that would be really awesome as a way to characterize it as we move forward in development. Yeah.
SST versus PSL based or something like that.
Yeah, that'd be cool. More heat maps.
Okay, that concludes the oral AMWG session. Let's thank all the speakers. And then don't forget to check out all the posters. I think the poster session starts now, as well as the information exchange.